3. OBS, YouTube. Keep talking, keep talking. I'm going to keep talking. Testing 1, 2, 3. Check, check. 1, 2. Stream audio 2024 MOC Alliance Workshop. AI Alliance. I need more slides. Opening remarks. Gloria Waters, Vice President and Associate Provost for Research, Boston University. Event overview. The cloud has transformed research and innovation.
All right, let's all move to the front if we can. Hey, Heidi, come on. Well, it's obviously a terrible day for commuting here in Boston. Thank God we're actually recording everything professionally this time. But hopefully more people make it. I was told somebody spent an hour on the T today, just. So kudos to you for actually making here. So actually to kick us off, we have Gloria Waters, who'll be saying a couple of words. I decided not to talk about her accomplishments as an individual, but about the role she's played. Like, none of this would have happened. While this is a multi-institutional, multi-industry, all these industry partners involved in it, it's actually university getting behind this and using the credibility of the university and standing up this and championing that we offer this internally and talking to the peers. None of this would have happened without your support, Gloria. So thank you so much.
Great. Okay, I think I will go on with that. Okay, just do this here. Everybody can hear me. Yeah, a little easier here. So, Oran, thank you. Really great to have this event here at BU today. So, welcome everybody to the 7th Mass Open Cloud Workshop. And as Oran and I were just saying, you know, the whole idea of this open cloud, I mean, it was a compelling idea a decade ago, really, when people started to think and talk about this. But it is really amazing to see how it has developed over the years and how it has really exceeded our expectations. It's had its ups and downs, and it's taken a lot of work on Oran's part and that of many others in the university and beyond. And I'll just talk about that a little bit. But it's just amazing to see that we now have production cloud services offered by university IT groups. And it's really supporting researchers from many different universities. And then there's also developed a really robust systems research computing group of people studying the behavior of the cloud, which is an important part of the academic mission of this whole endeavor. So I really appreciate the role that the Alliance is playing in presenting opportunities that really help computer systems researchers engage with industry and also open source community work on really important problems. And it is also providing a really unique and cost-effective resource for our researchers across many different universities, and that is really appreciated by the researchers and by the universities. So I think you know, the MOC is really helping impact many different areas of academic research, and it's really had an amazing effect in that regard. One particularly innovative research partnership that we definitely have to highlight is that with the Red Hat Collaboratory. This is really a very unique collaboration between open source research community, and also it is helping impact real at-scale production infrastructure and services in the open cloud. Red Hat has been an amazing partner, and over the past 2 years, the Collaboratory has funded more than 35 projects. With research, this resulted in papers in top journals, and also it's really had a major impact on open source systems. So it's really a nice kind of collaboration for universities to have with industry. One of the things that has been announced recently is the IUCRC, a National Industry University Research Partnership Center, which is funded by the NSF and was just approved. And it's also an innovative research model, which is very similar to the Collaboratory, and is now engaging additional industry partners and universities around the open cloud. So I think that's something that we're really looking forward to and looking to see how it will really enhance even more of what the Alliance is currently doing. So we're really happy to have many of the companies that are a part of the IUCRC at the workshop today and tomorrow. And it's amazing to see the diversity of companies that are actually involved in the IUCRC, everything from software developers to chip manufacturers and others. So I think a really important partner in all of this has definitely been the region's research institutions. This is a collaborative of many institutions, industry partners, and also especially the MGH-PCC. And that has been a really important component of this. And then the Mass Tech Collaborative has really stepped up and supported and championed the Mass Open Cloud at very critical junctures. And so we're really appreciative of that support. So all of the research IT departments in the universities that are a part of the Alliance have played a really important role. I want to just especially call out at BU Wayne Gilmore and Tracy Schroeder, and then at Harvard, Scott Yokel and Clara Jelenkova, who've really played key roles in driving production cloud services, but also in engaging the research IT departments of all the other institutions to have people come together around this really important effort. I think that, the Alliance has really been a unique opportunity, and it's been really successful so far. And it has really helped us engage with industry in a way that we never really thought to do before, and in really, I think, mutually beneficial ways. Other aspects of it are just the courses that academic departments are able to put on that allow students to engage in collaborations with industry partners. And I think that's beneficial both for industry and also for the academic institutions. So that's been a really important part of this also. And it's just a great model for future private-public partnerships, I think, and something to be pursued in a university setting that not very many, I think, organizations are doing at this date. And it has also validated the importance of the MGH-PCC and the role that it plays in this as a really important resource for the whole community and a shared resource. So I think we want to, first of all, thank all of our partners, the universities, Harvard, MIT, Northeastern, UMass, Boston Children's Hospital, and also especially the MGH-PCC, which we all belong to. There are many industry partners that are a part of the Alliance and now also of iScale, and they've given really valuable resources and technical support. So Red Hat, 2 Sigma, Intel, AMD, G Research, Wayfair, Broadcom, VMware, Cloudware, Flax Advisors, Lenovo, and Schneider Electric have all been really important to this whole project. And I think we especially want to thank the Commonwealth of Massachusetts and in particular the Mass Tech Collaborative for helping drive this vision into reality. They've really been with us from the very beginning and really provided the critical seed funding initially for this whole endeavor to start. And they continue to give us really important guidance and support. So that's really appreciated. And then I think, we want to thank everybody who is a part of the Alliance community because you're all playing a really important role. So I would say that BU is really thrilled to host this important multi-institutional project and to provide the support that we can for it. And I think we're really incredibly pleased with how this has come about over the past decade, and I can see only good things to come. But it has been an amazing ride to see this from the beginning to where it is now, and just really, really appreciate Oren's leadership and the work of all of the folks who are working on it to get us to this stage. I think it's been really mutually beneficial for everybody who's participated, and so thank you all for being a part of this. Thank you.
Thank you so much, Gloria. Sorry. I didn't have to wear glasses when I first came here. So, so the cloud's transformed research and innovation. For domain researchers, it's the new place where library, where data is discovered. It's the new laboratory where innovation is done. Still can't see this. There we go. And for system innovation, this has enabled very, very rapid transition from research to experimental services to production services. where you can be informed by real usage, where you can you can incrementally make changes and rapidly deploy that innovation, where you can have availability scale. Problem is that the public cloud today, for domain researchers, it lacks the facilitation that has been so critical for HPC to let it be used by a broad set of users. It's unpredictably expensive. It locks you into a specific cloud. And for the system innovators, that most of the academic research community, the open source community, and much of industry, we're kind of locked out of what's going on in the public clouds. There's no visibility into the real usage. We don't have the ability to incrementally deploy innovation like the cloud providers do, and we don't have the access to scale. So back in 2013, we had this really crazy idea that we create our own cloud. This was made possible because of the MGHPCC, this massive data center that was shared by all the universities. And the idea was that we would actually have a real production cloud, services that domain researchers would use. We could use that to inform the systems research, and then we could take those ideas and incorporate them to open source, and then make those available in our own production cloud. So, in other words, what we wanted to do was to open up the rapid innovation that was happening in the public clouds to the broader community by creation of production cloud for academia. It worked. I mean, it's kind of shocking. This is really the first workshop I feel I can seriously say that. We now have a whole series of projects that are standing up production cloud services that are actually operated by research IT, enabling that research to actually impact open source and transitioning that impact back into innovation that's actually affecting our own cloud. We have major projects now that are actually run by research IT that reports to CIOs with responsibilities to the whole university. So we need to have a real structure around this, and that's what the MOC Alliance has become. It's the sort of organizing body around all these different projects where all the kind of real work is happening. And really critical from my perspective, we now have a billing model. At the end, cloud is about actually having a revenue that you can grow the thing as self-sustaining rather than just free services. And that was a really critical thing made possible, again, by the MGHPCC, so that we can grow this thing in a self-sustaining fashion based on people doing their research and education. Now, I'm told I shouldn't really talk about the prices of this too publicly, but I'm going to do it anyhow. For research and education, this is incredibly less expensive than the public cloud today. It's only there for research and education. We're not trying to compete with the public clouds. We have no egress costs because we're on top of a national network, and we're charging the real cost of what it's taking us to deploy this. So the capital, the equipment amortized over 3 to 5 years, the cost of the data center, the energy costs, are our real operations costs. But today it's already substantially less expensive than the public cloud for research and education. And as the scale's larger, it's going to drop significantly in costs. So MOC by the numbers, we have over 1,000 servers with more than 30,000 cores and 5 terabytes of memory, which we've allocated some of them statically right now. You'll hear more about that later, and a bunch of this elastically so we can move between the servers. We just had our first model of an industry provider providing infrastructure into us where they continue to own it. So Lenovo and NVIDIA have worked to put 16 servers that just became available in the data center with 64 A100 GPUs, where it's co-investing. We have over 50 petabytes of production storage, and 133 petabytes of tape and NESI. And then we also have a large storage infrastructure that can be used for researchers that want to do research and storage. NERC is now being used by over 65 PIs from 11 different institutions with more than 700 users. We have actually courses now being operated on this. My own students are using this every single day. So this is actually rock solid support infrastructure. I could have said it never went down until last week, but but it's actually been rock solid and incredibly, the students love that they have this environment with reproducible containers where they can actually do all their work. And so its value for education is huge. There's incredible amounts of system research happening. First of all, the Open Cloud Testbed, which is this national testbed for systems research. The Red Hat Collaboratory, which is a huge, well, actually I'll talk a lot more about that in a second, but this is a major investment by Red Hat to sort of make this whole thing real, which involves both funding for research, but also an engagement with Red Hat engineers. And I'll talk more about it in a minute. But that's supported, as Gloria was saying, over 31 projects, 20 different faculty, hundreds of students. In fact, a whole bunch of undergraduate students that have done their own proposals to this that we funded with Red Hat or academic mentorship. This resulted in over 44 publications in just the last couple of years, and also real impact to open source software and a number of the innovations that are going into our cloud. And as Gloria said, we were just approved for a new National Center for Cloud Research. The kickoff meeting is Friday with more than 10 companies participating in this. And that's actually based on the same model that the Red Hat Collaboratory did, but just expanding it now to more companies and more institutions. So that's just talking about some of the core projects. There's the Open Storage Network, Coliseum, BioGrids, Dataverse, and Chris that you'll hear more about over the session. So it's turned into quite an enterprise, kind of shocking. I tried to, and I'm sure I missed people, but hopefully you can all read this. This is the sort of governance, the organization, and all the people have made substantial contributions to this effort. Researchers involved in it, their students and alums of the project. But I want to kind of focus on sort of this core part of it right now, although I'm not sure everybody would agree this is the whole core, but this is, you know, the leadership here. It started with Peter and I, and I don't know if Peter's around right now, but I mean, I still remember we stood up the first environment, and Peter ended up sort of diving into it for a 20-hour stretch and figuring out it was a kernel bug, which was the reason why the OpenStack wasn't running on the hardware we had, with a couple of new college graduates. And it's gone from Peter and I kind of kicking this off to now, oh man, I haven't even started. So now we have sort of this whole team, Heidi, who leads Red Hat Research US, John Stumpf, John Goodhue from the MGHPC. They're the kind of people where if I can convince them an idea is real, I actually believe it myself, and actually then go and execute on it. We would have never had the building model if it wasn't for the key role John's done. Michael, who's leading our engineering team, and Nancy, who's adding a degree of professionalism to the whole organization. Larry, that keeps us pointed in a vision of real innovation. And this incredible team of engineers. So these are engineers that are not just working on sort of the near-term efforts. So there's a big part of this are working on near-term efforts for NERC, making a production, for all the capabilities that we have, for the billing and everything else. But there's also a whole bunch of engineers that are engaged in working out of research projects that were sponsored by the Collaboratory that we're now transitioning into things that can actually have an impact in the not-too-distant future. That's an incredible involvement of professional engineers. And then there's the staff from Harvard and BU. And we have now a team with real users, a team to engage with them, made possible because of the support of the MTC. Everything we have here is, Tara's here somewhere, and Ken, who've kind of kept this organized, and of course I have to thank Jen, who was the one-woman show when it was sort of Peter and I before this thing scaled up to this level. So this is the agenda for the next couple of days. Previous years, this was all about potential. We were talking about what we could do. Now we have a real cloud. I want this event to be really an opportunity for people to be stating not only what they've accomplished, but the problems that they have. This is our chance to sort of fix what we're doing and sort of figure out what our strategic efforts are in the next couple of years. We decided to have 3 major sessions. AI is such a driving use case, so the first session today that we're doing now is that AI and AI Alliance, which is a new effort being kicked off. The next session is about how we can do something unique and novel, combining the data and the compute in our environment to solve problems that can't be done in a public cloud. And then this isn't just about creating a cloud. We want to create a cloud with a new model that allows innovation by a broad community. So the third session tomorrow morning is about creating an open cloud, what that actually takes to do that. And then finally we have a session where all of those three groups, the leaders from that, and several other kind of crucial initiatives are going to have give a quick pitch, and then we're going to have an hour of discussion to really figure out where we want to go with reporting back to the larger team. There's a lot of time for discussion in this, both unstructured time and structured time. So the next couple of days we have 11 hours for to kind of come up with decisions of where we're going to be going with things. Yeah, so the first session is actually going to be Jeremy, who's leading Red Hat's efforts in the AI Alliance, talking about it. Sanjay, who talking about research that we've been doing that's having a real impact in controlling systems. And then Eshed actually talking about federated learning, which is kind of a really interesting use case. A big demand in our region is for medicine. And so Ellen Grant and Rudolph Paneer are going to be talking about a capability that they've been developing on NERC, specifically to radiology, but more general than that even. And then we're going to have David. So Two Sigma's a real innovator in Wall Street. They're doing computing and pushing the boundary in a way that very few companies are. So they've both been a supporter of this and a collaborator in all of this. And so I'm really excited to sort of see the kind of innovation that he's talking about and why they want to collaborate with us in doing this stuff. The next session is about how we can do this new innovation. So that includes Larry, who's our chief scientist, kind of kicking it off with sort of the vision, and I'm already over time. Then Wayne is going to be, and Emery was talking about the capabilities we actually have today and what we enable. Stefano is going to be talking, this is all about the data, and so Dataverse is this capability for hosting large data, and Harvard Dataverse is perhaps the largest data set repository in the world. And so the new innovation by bringing Dataverse into the MOC that we can do about the compute. Rory's going to be talking about the RSpace, their new model, kind of a SaaS thing that they're going to be working on top of the MOC, but also how we can create a data commons for the larger region. Mark will be talking about some of the new capabilities that they've done at Two Sigma that I think are going to have a huge impact for academia. Collecting, being able to explore the provenance of the relationship, being able to memoize compute when different groups are doing that same kind of computation again and again. And finally, we've been building for a number of years now capability to create this community cache where things are cached near to where they're being accessed. This is, we're going to have Matt from IBM talking about how this is all being upstreamed into Ceph today and working with us, and then we hope to actually make this an experimental service this year on the MOC. John, who joined us recently from heading infrastructure at Two Sigma, and before that global services at Johnson & Johnson, is actually working with us on this open cloud vision and talking about that. And then we're going to have a bunch of our engineers talking about the key capabilities we have today that enable this. And Adam from MIT will be talking about how we can use a real cloud to drive innovation, to drive systems research in a more realistic way. Cloud Lab using these elastic capabilities. Do you really want a test bed where everybody has the same publication deadline, is working on a common infrastructure just for you? This allows us to make the test bed elastic with everything else we're doing. And a key part of elasticity is storage that's elastic. So Peter and Isaac will be talking about storage capabilities we developed, motivated by the problems we saw here that are actually now going in production. And then finally, Chris is going to talk, you know, if we want a large-scale federated cloud, we need data all over the world. We actually have, with the Open Storage Network, 1 petabyte data lakes distributed everywhere. Each of the different sessions, we're going to have people just discussing what they want to, what the kind of vision of these things are that we want to discuss, from governance, how we can do facilitation, the efforts around system research, and the key efforts that we've been working on to enable this to be used for education. And so each of these sessions will then have a large discussion period that will come back. And now we have a change in our scheduled agenda. Hugh, could you come up? So I'm going to talk more about Hugh and the role he's played in everything we've done in the reception tonight. But none of this would be possible without the incredible leadership that Hugh, leading Red Hat research, has actually given the project. He convinced Red Hat that our crazy vision of creating a production cloud for education is possible and drove not only major financial investment, but together with Heidi, has created an engineering team that has been critical not just to the production services, but helping transition the research ideas into open source that can then impact our cloud. So I still haven't forgiven you for stealing Jen from me, but other than that, Hugh's been an amazing partner. And I think you have a little announcement for us.
Thanks, Haran. I'm trying to remember. I'm hesitating because I'm trying to remember the first time I stood up here and talked to people. It was a while ago. Yeah, so we've built a thing. It's been good. It is continuing to be good and getting better. When Lars and Min and I came over and started the MOC engineering thing, working with Christy and Navid and all the other great folks on the MOC team, I'll admit that we were not at all sure it was going to go. when arguing with Rado about whether the Puppet manifests were the right ones or whether we should use ones that actually were shipped by Red Hat, was kind of it was an event. But we got there. You know, we got a stable OpenStack deployment at the MOC. We now have a stable OpenShift deployment at the MOC. It's growing. It's in production. Frankly, if you told me we would be where we are now in 2018, I would not have believed you. And that's, just to be fair, that's the power of Haran. Haran makes stuff happen. And we're very, very lucky to have him driving this. It has been also a transformative thing for Red Hat. We have probably the first really scaled out OpenShift on bare metal deployment, the first scaled out OpenShift AI on bare metal deployment. I am sure of that. We haven't done these things in other places, and we've learned a ton doing it, and under Heidi's leadership, we're sort of blazing a trail there for how we really do this. So I'm sad about all of this because, as many of you know, I am leaving Red Hat. This is the last time I will stand on this stage as a Red Hatter. I have taken an opportunity at Equinix, the data center company. After 22 years at Red Hat, I figured it was time to go try something different. And so this will be, it's bittersweet for sure. I'm super excited about the new opportunity, but I am really, really proud of what we've built together here, and I'm going to miss it a lot. However, I won't dwell on that anymore because I'll just get maudlin, so I won't do that. But I do have what I think will be a nice parting gift, courtesy of my friend Damien Eversman over here, who is the Red Hat Chief Architect for Education. This week, we were able to get a commitment from our senior leadership, Matt Hicks, the CEO, and Mike Ferris, who is our strategy chief working for Matt, for the pricing levels that NERC needs in order to be successful and scale on all Red Hat software. And that's going to be not a gift. It is going to be an actual subscription deal that is actually on paper and makes NERC a real paying customer. And we've got a commitment from them that they will set the pricing, whatever it needs to be, in order to ensure that NERC is successful. And that is, the funny thing is, I've been holding off asking for that because I was like, there's no way I'm going to get this. It's going to kill me. And it was like pushing an open door. It was the easiest thing I've done in a long time at Red Hat. And that, I think, is a testament to all of your success in making this into a real thing. There is going to be some engineering and some program building to make this into a lasting and permanent thing. Damien, with a lot of help from Lee Griffin and Heidi, are going to take point on making all of that happen. To ease the transition in the meantime, last night I was able to ensure that all of the current MOC subscriptions will be extended for free for another 6 months. So that roadblock is out of the way. And in the meantime, we will get this program in place, and we'll be on a good foot going forward. It's going to be a going concern, and we'll be able to federate it and scale it up and do all of the things that we have wanted to do. So this is very exciting. And thanks again to Iran for making me go ask for it. Because I just want to say the last thing. I don't know how many Red Hat folks we have in the room who came through this program as interns and are now with Red Hat. I see a few. I know there are a great many more. I am really excited to know that that program is going to get rolling again any day, and that we're going to have the same kind of pipeline into Red Hat and into building the Red Hat of the future coming out of BU that we had before. And if there's a regret I have, it's that I won't be around to help build that. But as I've been telling people, I gotta give myself a minute to introduce myself over at Equinix, but after that, I think I'll be sniffing around here again. So thank you all for all your help and all your hard work over the years, and I'll see you around the conference. And thanks again to Iran for everything.
Thanks, Hugh. I just want people to understand what this means is that we're going to be the one academic cloud in the world with a sustainable model for offering production services. If you talk about Scott and Wayne, they want to offer production services on top of supported software. It's a really critical thing, and licensing has always been a sort of the third rail, sort of like space in a university. So the third rail for in the relationship. And we're going to have a unique relationship where we can now build a sustainable cloud, and it's everybody else in academia, they'll join us to create this shared thing rather than doing something, rather than sort of diversity of things that can never scale. So thank you, Hugh. That's just incredible what you accomplished. That is the best. I'm sad you're leaving. I wasn't going to say it till the reception, but I'm sad you're leaving. You've been an incredible partner, but that is the most amazing parting gift I've ever seen.
Okay, folks, how we doing? Maybe one more round of applause for Hugh, 22 years. Awesome. Okay. Well, good morning. My name is Jeremy Eater. I'm a distinguished engineer and chief AI ML strategist at Red Hat. Thanks for having me. My first time with you. Today, I'm going to go through a couple things that are on my mind, Red Hat's mind, as we try and sort of democratize the field of AI. What I want to pitch to you today is three things. One is the major systemic challenges to democratizing AI and how the research community and academic community can do some real damage against those problems in a good way. How Red Hat is currently thinking about these problems, or at least getting the ball rolling. And one thing I should say is that a lot of this talk is going to be mostly focused on generative AI. And that's not to say that traditional machine learning has no place. It has tremendous applicability, and I think my colleague Sanjay Arora will take you through some of the systems level use cases for that just after I'm done here. So tremendous agenda that I saw Oren go through a few minutes ago. I'd also like to take you through what the AI Alliance is, which is an effort between Meta and IBM to gather industry together to make meaningful progress against some of these very, very thorny and sometimes expensive problems to solve. I'll finish up the talk proposing to you how this team can get, and your extended teams can get involved today on some of these projects. Cool. All right, so Gen AI. I've got a young daughter. She loves unicorns. Who doesn't? I love unicorns. I asked ChatGPT to draw me a picture of a unicorn. Pretty good. Majestic, even, I would say. Oh, there's a clicker. Love it. But, this isn't the unicorn that she wanted. She wanted to color it. But, have you ever seen a unicorn? What color is a unicorn? I don't know. Let's ask the machines. That's the reference implementation for what a unicorn looks like, I guess. Right? Some might argue that's a hallucination of the model. But here's what I'm trying to get at. Show me another technology, right, that can, with an access from your phone or your computer, okay, help with schoolwork in any language. Generate product ideas for any industry. Beyond text generation, we can also generate images. You probably already saw generating video from text a couple weeks ago from OpenAI. Rapid prototyping of ideas. Couple that with 3D printing, and the engineering cycles are getting tighter and tighter and tighter. Traditional software development. IBM has a thing. We have a widget called Watson Code Assistant. You might have heard of GitHub Copilot, other similar implementations. The claims that traditional software development is on its way out, I believe, are over-exaggerated. I believe for code generation, assistance is the only thing that will happen in the short term, especially for system software, where it requires nuance and detail, and cost is a major factor. Not anytime soon, but largely can be assisted by the technology that exists today. If anyone has another technology that has this level of potential, we should be looking into that too, but this is where we're at like now. It's a major, major step change in productivity for the human race. Personally, I think we should apply it towards, as much as possible, towards good, AI for good. The fact that we can do disease research and healthcare research and safety research and trust research in such tighter loops is going to help move the needle well beyond the IT and software development and AI technology practitioners to folks like my daughter who just want to color a unicorn. You may have heard Jensen say this on his recent earnings call about in the last week. He might have some motives for it, but he's pretty close, I think. I just tried to argue the case for him. This field we're just sort of walking through the door, and I like the analogy Hugh just said. He's like, this just pushing an open door is kind of what's happening now. And we are going to walk through this door into Willy Wonka's chocolate factory, ideally, where the promise is limitless. A limitless promise using this technology. How do we, as human beings, reorient our thinking around these new capabilities? It's hugely important. Before, I used to go to the dollar store and try and page through, or Amazon, and try and page through coloring books to find a unicorn. Now, I just ask the machine for it and print it out, if I can get the printer to work. So what I'd like to propose here is that while it may be opening doors for a new industry, we won't maximize the impact until we as the leaders, you as the leaders in this industry, reorient your thinking to harness these truly revolutionary generative AI capabilities. Red Hat's a for-profit company, subsidiary of IBM, for-profit company. So we do intend, I don't want to bury the lead here, we do intend to productize some of this stuff eventually. You have OpenShift AI, as I understand, 400 students using it daily. Absolutely love that sort of thing. And I hope you're successful using it and providing us feedback where there's sharp edges or we could do better. Absolutely love that, have to capture it. Red Hat's strategy isn't going to change for Gen AI necessarily. We're pushing in open source significantly. We're sponsoring, Kubeflow is a major component of OpenShift AI, and we're sponsoring Kubeflow Summit. We just got somebody elected to the steering committee. We've got dozens of committers over there, and that's just one component of the whole stack. So we're going in and doing, that is kind of like the table stakes product level stuff. There's also forward-looking stuff that we're getting involved with, and VLLM is one of those things that we're looking into. OpenAI Triton and Vulkan for GPU abstraction to kind of insulate developers from, we hope, the diverse hardware ecosystem that blossoms over the next year or two. Okay, so you don't have to necessarily change your app every minute, depending on what GPU you land on. Let me get into some of the challenges that we see. Currently, there's haves and have-nots. The haves are generally hyperscalers, folks that can afford massive compute to use this technology, and that have access to the educational resources that it takes to begin leveraging those components. 2 weeks ago, I had the opportunity and privilege to brief some of the North Carolina Congress people on their thinking for legislating AI in the sort of just after the executive order you may have seen drop a couple months back. And one of the folks that I met there was a Duke University professor, and his job was to push education down into high schools. He may have wanted to be more aggressive than that, but that was his first step. So that's one person who's taken among themselves to continue to push education in the way that they can in academia. You folks are doing the same. So I feel like this challenge is right up your alley, and we need everybody to understand that to open the door to Willy Wonka's chocolate factory, we need the talent and the passion of young folks to drive this industry forward. I started to think, what is keeping people on the sidelines from participating in generative AI adoption? Quite honestly, what it comes down to a lot of is like, there's ambiguity right now. It's a gold rush time. Licensing is ambiguous. What are the permissions on the data? Was it sourced permissively? And when you release a model into production, can you trust its output? Is it going to return the name of your competitor? Maybe not ideal. And most importantly, we don't let hate, abuse, profanity escape into these models. These are things that Red Hatters are currently looking into industry-wide. This is a major point. I would call it a gap and a challenge. This is an area where I was mentioning Kubeflow as an upstream component of OpenShift AI. Red Hat Engineering has developed a widget called Trusty AI, which is an open source project that attempts to implement some of these guardrails. Y'all are welcome to participate in that development, by the way. Open source Trusty AI on GitHub. It does remain, that's not a solved problem, not by any stretch. It needs work, and these are areas where I feel like the whole industry will benefit if we get more and more people off the sidelines by solving these foundational kind of first principles problems. Developer participation. So I just talked about kind of the broader industry adoption. Let's talk about you folks and your extended teams. If you ever watch a model developer, their experience is, let's just say, suboptimal. And compared to cloud native development, DevOps, things that have had 10 plus years to bake, we're just opening the door towards improving and democratizing that experience and making, removing some of the sharp edges. There's a ton of room, and I'm just thinking about tooling here, like developer tooling, but there could be hardening that gets done in production around tools. And right now, access to those tools is tied up with I mentioned the haves and the have-nots earlier. Access to some of the world-leading tools are tied up in closed source. You can pay for it. You can have it right now. With that comes some costs. With that comes some lock-in, and your ability to contribute is zero. So this is a major problem or major challenge for you folks to participate in as well. So I hope there's some of my colleagues from other hardware vendors here. I think maybe Intel, AMD folks might be in the room. I don't think anyone is going to be successful or should be thinking that we're successful if there's one hardware vendor at the heart of this entire new industry. That simply won't work. We saw what that did with Intel. They had a massive lead, and then there was sort of over time some competition came in. We need to encourage that. And I understand that the MOC is working with those vendors and maybe others to potentially provide those types of hardwares to develop, that type of hardware and software stacks to developers. That's tremendous. That's tremendous. If nothing else, access to this hardware right now is tough. It's tough. These cards are 10 grand a piece sometimes, right? List price, of course. That's a lot of money for a kid learning to tie up for any period of time. So there's cost pressure, there's access, like can you even buy them kind of a thing. And whether or not we agree that one vendor is the solution for this space and fully democratizing it, I think that's what's up for debate. So competition in this space is huge for users. Red Hat being kind of like a Switzerland company. We've been working with AMD and Intel and NVIDIA and others to make sure that OpenShift AI provides equal access to that hardware regardless of the vendor. We want a first-class experience through OpenShift AI, plumbing the best of those hardware vendors' capabilities up to you. Now, this is my favorite one. You may have seen an announcement just last week or the week before from the Allen Institute. They released a model finally with all of the data, weights, training data, and the model itself under a permissive license. So that's the first. That's a good thing. We need more of that. And we're not going to get it from the folks who have already tied up the value, who are lobbying our government to essentially create a firewall for themselves and basically establish themselves as a monopoly. That's not going to work. Our industry needs to get towards open models as a standard through which everyone can contribute. This is important work that needs doing, a significant challenge, and needs the brightest minds in academia to make a dent. Last one. I mentioned talking to the couple of Congress people a couple weeks back. I don't know if you folks are involved in talking with those folks, but they need help. And I will give you my personal point of view here. I don't believe that legislating the technology is the right move. I believe legislating the application of the technology is the right move. For example, you wouldn't put an LLM to the flight control systems of an airplane. At least not for a long time, right? But drawing coloring books for unicorns, fair game. So when we talk with our legislators, and IBM has been at the World Economic Forum along with many other leaders and in Davos, and I think we're doing an event today with Axios, which is bringing together a lot of politicians to try and prove the point that the technology itself is no really more quote unquote dangerous than other innovations in the past. Significant challenge, a lot of ambiguity. I'm forgetting the acronym, but there was a national, was it NIST? There was a national group that put out a list of like 50 questions that the president and his team wanted answered around AI. These are the types of, this is where we're at when it comes to legislation. Like the policy frameworks in the EU are far more understood. In in the North America, South America, far less legislation for us to lean on at the moment. And the idea here is not to throw the baby out with the bathwater, to make sure that we don't stifle innovation due to basically a lack of understanding. So if you folks have the opportunity to talk with legislators, that's sort of the mindset we want them to be in, is that the technology itself is broadly applicable and can be made safe while also not stifling innovation. Okay, so let me just try and round these things out. The AI Alliance is that, a way to harness open innovation. We have about 85 members now, including the MOC, and including Meta and IBM and many others. The idea for the AI Alliance is to bear down on the 6 challenges that I just shared with you across industry and try and make meaningful progress urgently across all 6 of those domains. Some of them are more relevant, I think, to the MOC, but that's the problem space, at least the initial problem space that the AI Alliance is working with. So I put this little "you are here" icon because the key piece here is that we are bridging, the AI Alliance is bridging academia and industry and bringing us all together in the same forum to tackle these really thorny shared problems. If you wanted to participate, what would you do? First, there has to be a strategy in place for how you engage. The AI Alliance holds meetings regularly across all of these work streams. This is announced in December and just kind of getting ratcheted up towards the end of January. These various work streams are still getting cranking. I think most, if not all of them, have already met at least once or twice. I mentioned Trusty AI, and you may be familiar with Open Data Hub, which is our it's our free version of OpenShift AI, free and open source. That's deployed here on the MOC, and I believe is involved in many of the projects that Oran was talking about. Those projects can be innovated on either in the open source community or you can work in the AI Alliance to do that. There's plenty more projects that are being donated. These 85 plus industry participants are each coming forward with new and interesting ideas that they think make a dent against one of those challenges. And so it's a tremendous kind of groundswell of enthusiasm just by creating sort of a lightning rod for cross-org and cross sort of industry and academia, bringing all of those folks together. A tremendous opportunity. So not only do they have existing participation and existing projects, anyone can bring a new project or a new idea. If you're willing to build it, willing to work with people, this can be a place where you bring your bright ideas, your innovation, and share it with the world. Tremendous microphone. Lastly, the larger community of the AI Alliance also needs help, just like the MOC Alliance needs help to grow, and Oran and Hugh have done a tremendous job over the last many years doing that. The AI Alliance can also use that same sort of enthusiasm. This slide is supposed to be hidden, and it's not. What are some of the specific things that the MOC Alliance members can do? Right here, these 2 things talk about how we rapidly evolve the tooling space. So I think that was challenge number 3. I understand, as I mentioned, that there's many other GPU vendors that are going to come into the facility. I love speeds and feeds, by the way. I was in performance engineering at Red Hat for 7 years. So that was, and I did high frequency trading, performance tuning and stuff like that. So I love the speeds and feeds. I don't necessarily like storage because it's too slow, but the speeds and feeds of the MOC are impressive, and you have done a tremendous job in getting all that gear together for this innovation. I believe that you can harness the power of the MOC to help us more rapidly turn around and rapidly innovate on those, at least half of those challenges. I think 1, 3, and 4, diverse hardware being the 4th one, it's just right up your alley. It really feels like it. And then the last bit is the students that are getting access to this gear and just the skills gap that I mentioned earlier, and how do we inform what those people need and what tools need to be developed to expand adoption, right? All of that can be done on the gear that you've got right now. There is literally nothing stopping you from doing this. You can do it from your laptop right now. I love the potential of the MOC Alliance and AI Alliance together. This is my proposal to you. Feels like the right moves. Leaving it to all of you to figure out what the right next moves are, but to me this seems really obvious where the Venn diagrams are kind of almost entirely overlapping. And the fact that there's going to be like a Dataverse instance over here, and so you don't have to like worry about access to data to kind of demonstrate your proof of concept and innovation is going to be huge, absolutely huge. There's a Chris talk coming later today, AI applied to medical. I personally mentioned that. I mentioned that I love the AI for good angle. There's a story that I'll just leave you with one anecdote here. Rural hospitals, very underfunded. There's a technology that can turn a 2D ultrasound, which most of these rural hospitals have, into a 3D ultrasound using machine learning for graphics. Huge benefit for those mothers who now have access to better technology or better imaging technology than they would have otherwise had, and those hospitals don't have to outlay huge amounts of cash for those additional equipment. That's the type of stuff, it seems so simple, right? But it improves the lives of so many people through those efforts. It's just tremendously inspiring. Those types of innovations, I get teary-eyed because I love to see humans helping humans. Okay, so last thing before I tie off. This is roughly how we innovate. So I mentioned all of those different communities. I mentioned Kubeflow and Trusty AI. There's so many more. Kserve is a really interesting one where VLLM support, I believe, got added to Kserve 2 weeks ago for inference serving. PyTorch, massive investment in PyTorch from IBM, hundreds of people working on PyTorch right now. So that innovation, if you work in the upstream or work in academia, whatever, it eventually bubbles into OpenShift AI on your systems in this, Open Data Hub in this flow, and then ultimately into our product. That's how that works, in case you didn't know. I wanted to say thank you here. One last thing. Thank you to our audience. Thank you to our hosts here at Boston University. My first time here. Apparently, lots of stuff going on with OpenShift AI and Red Hat and AMOC and Boston University. Absolutely love the facility. Thank you so much for having this conference here, and thank you so much for having me. Oh, we can do questions, sure. Let's do it. 2 or 3 questions, maybe? Please. Aw. Sure, I left something out. Let's crack open those laptops and work on one of those challenges together then. Okay? Awesome. Thank you.
Let me just test this out. Perfect. So hi, everyone. I'm Sanjay Arora. I work at Red Hat, specifically at Red Hat Research. And I want to talk about learned software systems. So let's dive in. So as most of you know, if you look at system software, operating systems, compilers, cloud systems, they're full of heuristics, which are handwritten rules. And these heuristics guide decision making. So some examples are schedulers in an OS, so in the Linux kernel, schedulers for Kubernetes. If you look at compilers, compilers have a bunch of heuristics that we'll talk about soon. Think of circuit design or combinatorial problems, optimization problems in general. They have a bunch of heuristics too. And then if you crack open an OS, it has heuristics for very specific subsystems. So for example, the NIC, the network interface card, has a heuristic for what's called the interrupt delay. Or CPUs have heuristics for dynamic voltage and frequency scaling. It's called DVFS. And imagine you had to write a heuristic. What would you look at? So you might want to optimize something. You might want to optimize performance. You might want to optimize resource consumption. In general, it's not possible to optimize everything you want to. So there'll be some trade-offs, and you have to make them in a judicious way. And the important thing is, if you write heuristics in a lab on some workloads, on some hardware, they ideally are generalizable. So if you deploy this, you push it out, and suddenly your system sees a workload it has never seen before, it shouldn't catastrophically fail. It might not be optimal, but it should at least perform decently. And there's a term which is not very creative. It's called ML for systems. And that refers to finding better heuristics using ML techniques. Okay, so finding better, instead of handwritten rules, can I find better rules for a system using some machine learning techniques? Now, if you want to do this, you need some infrastructure. And you broadly need two things. You need to be able to observe what your system is doing. So that involves several metrics and frameworks. So for those of you who are familiar, frameworks like eBPF are great for this. There are various tracing technologies that access low-level hardware counters, for example. So you need to observe your system carefully. And you also need to be able to intervene in your system. You need to be able to change it. So there are, again, various quantities that you can tune or manipulate. So you say, OK, I want to learn heuristics with machine learning. And I have some metrics I'm going to observe, and I'm going to go and change a few knobs. But where do you start? So there are two types of problems. First, on the system front, you need to identify what subsystem you're going to work with. You're going to identify what metrics you're going to collect. How will you observe the state? And this is tricky, because you ideally want to observe everything, but you don't want large overheads. You don't want to change how your system behaves just by observation. Then you also want to pick the knobs that you will tune. How are you going to intervene? And that takes substantial system expertise. And even if you get all this right, then you need to make careful measurements. And in our experience, most of these problems where you're applying machine learning to optimize a system fail because the measurements aren't done carefully enough. It's very easy to get a lot of noise. So controlling the noise in the system, doing the right type of cleanup. So when you do repeated measurements, you're actually getting independent measurements. All of these are crucial problems on the system side. And then there are a bunch of statistical and machine learning problems. Maybe the primary one there is the question of sample efficiency. So if you run experiments on a machine, they can take several seconds to even several hours or days. Large benchmarks can take a long time. And if you have some technique that needs thousands of evaluations or hundreds of thousands of evaluations, that's never going to work. So sample efficiency is extremely important, and that often governs the type of techniques you'll use. And then there are specific questions like the scalability of techniques when it comes to the number of knobs you're tuning, the kinds of, the amount of noise you have in your system. There are some techniques that really want you to sequentially do measurements instead of parallelizing measurements. So those are the kinds of questions that one has to address, but this is still a bit too abstract. So the main takeaway is you can't just throw machine learning at systems problems. You need to really understand your system and carefully design your experiments. So instead of talking abstractly, let's look at one specific example. This is joint work between Boston University, so Professor Jonathan Apawa's group, and Red Hat. This is Han Dong's thesis work. And the setup is very simple. So you have this stack, you have the hardware, you have some OS running on your hardware, and you have some application. Here there's an application called memcached. And essentially you have requests coming in from the outside world, which is the external load. And your job is very simple. Requests come in, you do some computation, and you return an answer back, and you have a time limit. You have a time limit in this particular case of 500 microseconds, half a millisecond. To be more precise, it's the 99th percentile latency. 99% of your requests should go out in half a millisecond. So very simple setup. Someone's asking you questions, you have to answer within some time frame. And the question is, can I do the same work while minimizing the amount of energy that my system uses? So you say, okay, what can I control? Now, there are many things you can control, but let's pick two things. One thing I can control is as requests come in, I can ask them to queue up. I can say, I'm not going to serve you right now. Please stand in line. And then at some stage, I, as the system, need to decide when to answer your query. And the other thing you can control is your processor frequency. So you can slow your processor down. You can say, everyone, please queue up. I'm going to slow my processor down. It's not doing any work anyway. And then when I'm ready, I can wake it up and start doing the work. And so we said, well, let's control these two mechanisms. Let's ask request to queue up. That's controlled by a knob called ITR, or interrupt delay. And let's modulate our processor. That's through that knob called DVFS. And these are two very busy plots, but let's deconstruct them. The x-axis is the same on both of them. The units are different, but it's the same. It's 24 hours. The y-axis on the left plot is the energy consumed by the system. The y-axis on the right one is that latency. How much time did I take to respond to, for the 99th percentile? And if you look at the two curves, two plots, they both have a red curve. It says QPS, that's queries per second. How many requests are coming in per second? So as time goes on, through the day, the number of requests you get varies with time, which is natural. That actually reflects a real workload at Twitter. Well, I should say X now. And you can see the blue dots on the right side. That's the latency that Linux performs at by default. So by default, even though you need to respond to requests in 500 microseconds, Linux tries to minimize that. It responds in 100 microseconds, so much faster than you need to. And on the left side, the blue dots again show you the energy consumption on Linux by default. And of course, without having some intuition about this, one doesn't know if that's high or low, but it's pretty high. So you're responding very fast, but your energy consumption is high. And so a natural question is, can I maybe respond a bit slower? Can I maybe pay a price in latency, but reduce my energy consumption? And so we tried that, and on the right side, you'll see the green stars. Those latencies are when you tune ITR and DVFS, the two knobs you have, to their optimal settings. And what you see is they go up, latency goes up, but it's still within the limit that you need to have within 500 microseconds. But on the left side, you see a dramatic saving in energy. The green stars go down compared to the blue dots. And in some cases, you get something like 40, 50% energy savings. So if you zoom out, even if you forget the details of what I said, the main takeaway is just by carefully designing your experiments, without changing your application, without changing your operating system, by changing just two knobs, you can get dramatic savings in energy by trading off some latency. And this story repeats across all system software. You have a lot of room for improvement without really rewriting any code, just by changing the knobs that are exposed by developers. Another example, and I won't go through this in detail, is compilers. Compilers have something called optimization passes or phases. They take code and transform code into other code, and they do this in the hope of making the code more performant. All of this is automated. It doesn't change the meaning of your code. The effect is the same. And a natural question for compiler writers is, I have all these optimization passes. So imagine n optimization passes, and you need to apply them to your code. And the order in which you apply them matters a lot. That can have a big impact on your code performance. So a natural question is, what order do I apply my passes in? And I have a link to a paper where we use reinforcement learning to try and learn that. And again, depending on the source code, you can get significant performance improvements. And as before, you're not rewriting your compiler, you're not rewriting your application. These are all existing capabilities in system software where you have potentially huge improvements in resource consumption and in performance. And the price you pay for it is you now have to use some machine learning to try and find these solutions. I can't say anything about ML without mentioning large language models. I'll probably be fired for doing that if I didn't mention LLMs. No one can deny that there have been huge advances in LLM capabilities in not just the last year, but the last 5 years, last 6 years. And these are no longer just LLMs. They are multimodal models. They can process text, speech, so audio, video, and text also includes not just human text, but code. And so we have tried these for a few problems which are not traditionally systems problems, so problems like generating unit tests. And while you do need to manually tweak what comes out, and you need to filter the results, they are extremely promising so far. Now, there are a few papers that claim that their LLMs are great for combinatorial optimization. I personally don't think these are replacements for, let's say, reinforcement learning or Bayesian optimization. But when it comes to code generation, they can be extremely powerful. But like Jeremy said, when it comes to system software, like kernel code, you want to be a bit more careful. And lastly, I'll just summarize what I said and give you a sense of what we are working on at Red Hat Research. So the main takeaway is that even with existing software and existing hardware, there's a lot of room for improvement by tuning systems without rewriting any code. And most of these experiments, when we have seen them fail, they fail because of bad design of experiments. So it's very typical to set up some experiment, throw some ML at it, say it doesn't work, right? It doesn't find any solution. And as an example, I remember once looking at someone trying to tune one parameter, and they said, oh, I can't find a better solution. So we said, let's do a brute force search. And there was so much noise in the measurements that the noise was basically washing out any differences in the tuning parameter. So you can't just throw ML at it. You do need to design the experiments carefully. And these are, of course, not all the projects we are working on, but we are trying to extend that NIC tuning example with ITR and DVFS to noisier settings in OpenShift. So what happens when you have OpenShift or Kubernetes running and trying to allocate pods to resources, to hardware? We are also doing something that's a bit more experimental, where instead of learning a large language model for code, can we learn a large graph neural net on code? So instead of looking at code as tokens, as text, can we look at code as control flow graphs and data flow graphs? And can we, just like LLMs, in a self-supervised way, scale the training up to learn very good embeddings or representations of code? So that's an active area of exploration at Red Hat. And of course, we are working a lot with compilers. So not just ordering of optimization passes, but can we automatically insert pragmas into code? Can we pass the right command line arguments? Yeah, hopefully we'll make progress over that, or on these problems over the next year. But if there's one takeaway, that is that if you look at the machine learning community, we focus a lot on computer vision, on natural language processing, on video processing, audio processing. Those are great problems. I would like to add one more to that, which is machine learning for systems. There's a small growing community around this work. There's a workshop every year at NeurIPS called ML4 Systems. But we definitely need more people to work on this, and we need more systems researchers to work on these problems. So that's all from me. Thank you. Any questions? I'll be around too, so if anyone has specific questions, please just come and talk to me. Otherwise, I think we have a break. Question? Oh, please, yeah.
Yeah, when you're making the trade-offs like the power and the latency,
Yeah.
is it reasonably well established how to reason about like layers of application? Like if the system service is increasing the latency by this much, and then there's an application layer and another layer, middleware, and so on. Is it reasonable? Are there now ways to reason about that kind of end to end to know what the final application gets, or is that really still just a matter of art and people just have to try it out and see how bad it gets or how good it gets?
So at least for us, the latency measurements are across the whole stack. And it depends, right? So that comes back to the question of what state are you measuring? When we were doing this problem, we were treating this as a black box. So there are specific black box optimization techniques like Bayesian optimization, which say, can I, in a sample efficient way, if you do accurate measurements of latency and energy, find the optimal ITR and DVFS. If you do have some fine-grained profiling or tracing, then one could absolutely say, you know, I would like to, for example, minimize the latency in this layer. I don't care about the other ones. I don't know if that's exactly what you're asking. I'll add one more thing. All of these techniques do let you characterize the trade-off between energy and latency. So you can actually answer the question, if my latency is 100 microseconds, you can quantify statements like the following. I can increase my latency by 2%, but I'll save 5% energy. So you can get these trade-off boundaries, but they are in aggregate across all the stacks, across all the stack.
Hi. So one of the things I love about that work is that it shows the value in customizing and tuning the environment for the application running on it.
Yes, yeah.
And if you look at some level, what we've done with Kubernetes and OpenShift is we've sort of said, yeah, kernel is just a commodity. You know, we're running all these different applications on top of it and just looking at scheduling at the high level in terms of packing these things together. These things seem in conflict with each other, are they?
So I know there's a lot of work on customizing system software, like the unikernel work. And there is always, so again, from a mathematical perspective, there's always going to be more potential improvement if you optimize or tune across the stack, right? If you do it layer by layer, that's a local optimization, but not a global one. So ideally, you would do it across all the knobs. And there are open challenges that we have. For example, if you were to list all the Kubernetes knobs, all the kernel knobs, and there are thousands, and if you said, OK, now go and do something, that's troublesome from a machine learning perspective. There are too many knobs, they're correlated in their effects. So we are forced to retreat to one layer at a time right now. But eventually, our hope is we'll do exactly what you're saying, which is you say, OK, look at the whole stack, optimize across everything. But that will take a few years, probably. Cool. So I think we have a break now, right? Oh, yes.
Okay, thank you. Thank you, Sanjay, very much. And again, thank you, Jeremy. Okay, we'll take a short break here now and ask that you return and be in your seats at 11. And Assistant Professor, BU faculty member Ashed Onbar will present at that time. Thank you. We're ready for our next speaker. Great, thank you. Folks, next up is Eshed Onbar, BU Assistant Faculty, Assistant Professor. Thanks, Eshed.
Hi, everyone. I'm Eshed from BU ECE. Thanks for Red Hat for inviting me here today and giving an opportunity to share with you some of our research in scalable AI systems. So we call this project the CoOps project. CoOps is an open source platform that is designed to enable anyone to participate in collaborative training of large AI models. Before I start, I want to thank an amazing team of collaborators at Red Hat, industry, and of course an amazing team at BU of students. Without them, none of this would have been possible. And introduce you to Evelyn. So this is Evelyn. She comes to her office one day and she starts pondering. So she thinks to herself, we have amazing computers in our pockets, powerful computers more than ever before. We have people in space. But somehow every year, over 1.3 million people die in traffic accidents around the world. And so she decides to investigate this problem further.
Whatever we can get off of the vehicle as unmodified.
And she finds out
NavLab 5 was a stock minivan, complete with laptop computer and multiple television cameras for front, side, and rear vision. Alvin was replaced by a more sophisticated neural net system, Ralph, which could handle lane change.
She finds out that 30 years ago, a car, 30 years is a lot of time in computer time. 30 years ago, there was a car that drove mostly autonomously, 98.2% of the time, from East Coast to the West Coast. And then fast forward to today.
Then another. It was just insane. Like, they need to get better at seeing where each other are positionally and lining up. I mean, all of them are like facing sideways in the street, trying to navigate around each other, even though they're all part of the same network.
Matthew Seiler.
So we have these cars, many of them getting stuck at intersections, causing traffic accidents. This has been pretty slow. This development has been slow and riddled with challenges. These prototypical type vehicles that, maybe Tesla is a level 2 out of the 5 levels of autonomy still today. Waymo only operating in 2 cities, San Francisco and Austin. And other companies struggling. So Uber, Cruise recently halted their operations, Apple. So Evelyn decides to do something about it. So she looks online. She can't find a publicly available model for this task, but she can find some open source code that's pretty clean. And she wants to train a model. But she can't because data is very costly to collect in this space, often with sensors and curation. And most of it, because of that, is kept private and centralized, so concentrated in just a few key players that also have the most compute, like Tesla and Waymo. So she realizes that on her own, this might be difficult, but with the help of her friends, she might just have a chance. So for decades, we've observed this really slow and inefficient development in this space, and that's why we wanted to approach a more collaborative framework that can be used to rapidly collect tons of data distributed from all over the world, all the time, and share computation with the ultimate goal to develop an open source, transparent model that can be rapidly improved and iterated upon. So that's the goal of co-ops. And we've been working on building a scalable framework in a step-by-step approach for edge AI here. So tackling fundamental challenges such as learning from really diverse data like dashcam videos from the web, adapting to different geographical locations, learning from feedback about what's safe, what's unsafe, different traffic rules and social norms. And ultimately, as the data is being streamed continuously and the world is changing, updating the model in a never-ending process where data is sorted, thrown out as needed, and retained in order to remember important experience. Much like how human drivers do when they start from novices and they turn into experts over a process of many years. So let's look at the model. Actually, the task is very simple. We want to go from the left side, which is observation image, to some decision, driving decision. And the problem is we, on the left side here, it's not just pixels and data. It's actually humans with different behaviors, different social norms, different locations. And so you really need an expressive model that captures this. So we designed a new type of model that can adapt its decisions across locations. And we evaluate this model over all of the publicly available data sets we have today, which is 11 cities, shown here, all over the world. Now you can train a model in a centralized manner by storing all the data in one place and training over it through many iterations. And you might get an error of 1.05 in meters compared to the how human drivers drove. And you can see that the distributed approaches, we call these federated approaches, are actually quite poor at this task. So the errors are high, but for our model, we actually find that we not only outperform all the federated baselines, but we also outperform this centralized baseline. So this means we're doing something right. We trained this model over very diverse data from the web, dashcam videos from all over the world, freely available data that's being uploaded to YouTube every day. And then we test it on this 11 city data set. So you can see how the model, by watching YouTube, learning to drive at night in a complex maneuver of overtaking a parked vehicle on the shoulder, driving in the rain with poor visibility, and even driving at night in Miami, so different locations. So this is a type of scalability we're thinking about here. And going all the way across the world to Pittsburgh and then to Singapore, which will be shown next, where people drive on the left side of the street. One model for everything. So I just want to mention that even though there's very diverse data here, so there's diverse human data, diverse drivers, and diverse videos that we use to train. Humans don't really learn in this manner, so they don't really just watch how people drive, but they actually learn from feedback, how to improve and why. And I still have these memories of my sister yelling at my dad to slow down, to drive slower, giving him feedback, and my dad yelling at my brother to avoid the potholes. So this is usually how we learn. We designed this feedback-based approach for training the model. And this is really powerful because anybody can give feedback to the model in this manner through language. So again, we have the same framework of going from an image to a decision shown on the right in future goals. And in green might be what the human would do, but in gray might be what the model predicts. And so we can then give feedback to the model where we tell it, you're going to collide with something in 3 seconds, so this is why it's a bad decision. And when we give it that type of feedback, it's able to learn much more effectively. So we update it with this feedback. This approach outperforms all LiDAR-based approaches just using RGB. So the baseline model, we test it extensively in simulation. The baseline model tries to make a lane change, but collides with this police car. Not a good idea. And our proposed model, we're able to say this is unsafe, and successfully completes this complex maneuver. So no collision, and driving okay in this intersection. So we validate these models in simulation as well. Here is another complex scenarios with puddles. So the baseline model stops for the cyclist, but doesn't take enough turn. So gets stuck. And then collides with the pole. Whereas our model is able to seamlessly turn with enough radius to safely do this maneuver, while avoiding obstacles and the cyclist. So all these methods that I've shown you until now were actually trained on about 10 hours of video data where we test things. But there's thousands of petabytes of data being uploaded to the web every single day. So we design a system that can watch one video at a time, but sift through it. Highly efficient system. It never sees a video again. So it goes video by video, and removes useless information, irrelevant information, but also keeps in a memory buffer the most important experience so it doesn't forget it. And it's a continual, never-ending learning process. And for this framework, we can actually train, and it's still training in our lab right now. So we said to just keep letting it train over millions and millions of images in unprecedented scale. You can see some of the automatically selected buffer samples here, highly diverse. You have different weathers, urban versus rural conditions, and you can see that we outperform all other approaches in continual learning for this task. So we are the red curve, and you can see how the error keeps going down over many, many images. This is interesting. So these are some samples that the model selected to remove. So you can see these are automatically removed, and these are irrelevant frames with ambiguous cases where maybe there's a frame transition or anything like that. So we've been integrating this frameworks into NERC of both collaborative training and a collaborative community source repository for data for training and evaluation of these models. So this is running on NERC. Okay, great. I think I went kind of fast. So we discussed a path towards addressing challenges in closed source development of edge and AI systems. So there's still some key issues. One of them that I'm interested in is these agents that are participating in this distributed network. How do we incentivize them? So how do we make sure the system is self-sustaining and not something that just disappears? That is a really tough problem that I think would be interesting to tackle next. So here's my email. If there's any questions or any ideas on some of these problems, feel free to reach out. And I'll be happy to answer any questions.
Super cool. Thanks so much for that talk. So you know the classic problem that we all seem to be at the mercy of right now when we talk about open learning and open data, the question of an adversary wanting to corrupt our information source, right? Now, there are various things that one could imagine denial of service inspired like attacks on this versus, you know, at the YouTube level versus at creating enough false frames, things like that. Do you have any thoughts about that?
Yeah, thank you for the great question. So if adversarial data is really hindering to the model, actually, so in all these data collection efforts, they try to curate it as much as possible. Actually, even diverse data can hurt the model performance. So it's almost like a task where humans trying to remove data that might be too much for the model. But adversarial cases are difficult, yes. So, so one case could be in training time, where there is a data poisoning attack. And especially in this case, you would want to detect it and remove it. So there's ways to do this, but obviously this is a difficult problem. So one way would be to validate the model performance, and if they go down, if the model performance goes down, that maybe this data should be thrown away. Actually, there's a related problem to what you're saying, which is you know, kind of like nodes that don't really contribute, and maybe uploading junk data. So you want to remove those. So what I like about this framework, if in theory, you could use the model uncertainty to filter these samples, which is what we're doing here. But we haven't tested this with intentional agents that are trying to adversarial attack. But this is a bit like that, because somebody edited these videos and there's a transition, the model is confused by that and removes it. Yeah, so, but often adversarial samples are not even, may not even be perceptual to humans. So it's a really tough problem. But then in that case, this actually even motivates something like this even more, because then you would want some automatic process to remove these. In test time, adversaries are a very difficult problem. Yes, and I think that one way to solve it is through scalability. So imagine a proportion of data where as long as most of the nodes are, so it's kind of like a consensus thing, but as long as most of the nodes are uploading data, and actually the larger the network is, the less the impact of these adversaries, because maybe they are pretending that there's a traffic accident when there's not, but other people are also viewing it at the same time, and then you can say, okay, this is unlikely. But this is a really interesting point, so I think we should look into that. Does that answer your question, or?
Yeah, no, first off, I also want to be clear, like, I think this stage of work is phenomenal, right? Because we have to know that these things are even make sense. But actually it was that latter point that I was very curious about. Mm-hmm. Does this become an arms race of computational capacity? And are we back down to like all the other kind of money kind of stuff where it's like, look, everybody who would need to be able to corrupt this would have to operate at such a scale, it makes it impossible. And does that always place, quote unquote, us open source good guys, for whatever label that means, mm-hmm. in jeopardy of the big players, because they're the ones actually who have the computational capacity to launch serious attacks on the open source models?
That is, yeah, so another really great question, because that's very likely to happen, especially at the early stages. So we are, you know, kind of at, for these type of systems, AI, it's kind of like the early days of operating systems. You don't really have a collaborative standard, and there's a lot of resistance, actually, so especially from the big players. Yes, so actually, I went to a conference, one of the biggest AI conferences, and I went booth by booth, and I asked them, and they described this as some kind of a utopian view, but it is inevitable. It must be inevitable if we do it right. The world is constantly changing. It is. So I think the reason this has been so slow is because it's beyond any single player. So whenever they are ready to join us, they're welcome to. And there's good nearest neighbors to this approach. Besides operating systems like Linux, there's OpenStreetMaps, which was actually, are you familiar with that? So OpenStreetMaps is an effort that was mostly crowdsource GPS data that was uploaded for many years and often ignored by the Google. And then what happened is Google raised their price. And so others were looking for a cheaper solution, and suddenly Apple started contributing to this open source effort. But that is exactly what I'm wondering about, right? So there must be, oh, did I disconnect something? There must be some way to incentivize this so it becomes self-sustaining and explodes. And I think that is a very tough thing to do. But I think the simpler the framework, the better, more people can use it. Right, you ask a good question about the money side. Yeah, that is a difficult problem. There's a lot of money in this space. Whoever solves the problem first, right, so this leads to this race, and they don't want to share their data because of that, right? So, but then there's, so how can you develop efficiently? It's so slow, right? If it's just one company doing all so Tesla has been the main leader, the main horse in the race here. And is there by the way, I think it's going to run out of battery soon. It says, so I guess the quick answer is I don't know.
Elevate something that we as public academics can do here beyond, because I think what you've got, when we talk about speaking to legislators and getting involved in helping understand these technologies and the impacts they're going to have, to be honest, I don't want it to be companies who are the sole advisors to legislators and government bodies, but I think when you have such concrete work like this, that they can actually start to see what we're talking about and argue whether, look, maybe all is not rosy on the other side of the global AI fence. And these are the kind of things why public funding, public legislation, all of it can get engaged.
I think it's okay, but yes. So regulators, I think. So when I talk to people in DOT, I think there is lots of interest, but there is. It's so disorganized right now that right. But I think that it would have to come from something like that. But I really wish it was emergent. And in hindsight, it might be something that was clear. But today, right, it's so early. Actually, your question, leads to a lot of follow-up interesting questions. Like, there's especially in the adversaries areas, so we see, so people are in some areas are very resistant to this technology, and at the same time, actually, if you think about the development of this technology today, it's mostly done in like rich sub-areas of cities, so people may not be able to benefit from it either, right? So if you just leave it to kind of pure company-driven interest, especially, so that would just lead to what happens today, where you have one monopoly and they're doing something like that, right? But yeah, the open source route is always tougher, more difficult, but if we can pull it off, I mean, then AI will empower people in a way that, right, so that's the idea. So I think an open source model for something like this I think that means everybody understands it better, right? So maybe it works 99% of the time, but in some cases it doesn't work, and everybody knows that, and you can inform the user. So there's also the legal perspective, which is totally I would not be the best person to comment on that, but I don't know if anybody really knows yet. So it's thanks for your questions.
Hey, Eshad. That was a great talk. Really interesting project. I was thinking about other things besides videos that can be uploaded and shared and open sourced. And you didn't talk too much about how you keep track of where things came from. I mean, obviously you do to some extent, but how do you handle that problem? I'm thinking of an example called PerfSonar, where people who ran networks uploaded data about the latency and the throughput on their networks from different points all around. And the data got thrown away, so you knew perhaps the results of tests, but you no longer had the source data if you made conclusions. So it's similar problems in lots of different domains.
That's a great question. So how do you keep track of where the model came from? Where the data came from?
In your case, where the videos? So you said it's watching, you know, all the videos all the time, everywhere, and obviously not saving them all. So do you just say, I can't keep track of it, and I'll just go with other approaches for keeping track of what my model's doing, or do you try to keep track of what it looked at?
So actually, GPS data often is part of this video. So if somebody uploading GPS data is possible, you know, especially if it's something like a smartphone. This is usually GPS data. But then obviously this leads to a privacy issue where suddenly everybody's activities are visible all the time on this network. So in this geo-aware federated learning, you do not have to share your location. It's only kept locally. And it's something that you apply to the model once you download it, and then locally it applies it to some local location. But, and it only needs to be defined over regions in this. So we did cities in this specific thing. So it's not like exactly where you are. And it learns, you know, how to drive in different cities, you know, Miami versus Pittsburgh left. But anything that any metadata that we have on top of the videos would be super helpful. So there could be some ways to even encourage people to upload that, especially if there's something like OpenStreetMap where they are participating in uploading GPS data, and they then add additional things to that, and we integrate with that, then that would be one potential way to go about it. Does that answer your question, Heidi? Or?
No, I was just wondering how you managed it. And so, yeah, basically you have to encourage people to upload the extra data that you want to see for what you're doing with the research.
Right. The metadata helps a lot because so the current models, so most studies only evaluate over 2 cities when we do research. So they don't really think about this geographical distributed learning. But if we have that information, it will help the model a lot, yes, because the decision might be totally different. And if you're in, you know, some other city on the other side of the world, or in Europe, then you must adapt your driving decisions. So I think, so actually ideally we would have ways where we either say, okay, this is private, you can keep it local, you don't have to share this information, or you can share it and maybe share more of the raw data, and that actually is the best for the model. So that's always the best in the end.
Thanks.
Thanks for the question. Not sure what.
Hi. I really enjoyed the talk. I was thinking when you talked about keeping this going and open source, perhaps one venue that could be pursued to incentivize the private sector is to provide free dash cams to, say, Uber, because with Uber you have all that metadata about the quality of the driver and the routes and all of those things, and if you give free dash cams, then you can collect the data if they agree to that. But then also, I noticed in one of the slides, your car, when there was a cyclist that went in front of the car, it didn't decelerate necessarily. And so doesn't the quality of your source data matter a lot, and not just having, you know, people who don't hit pedestrians, but people who make pedestrians feel comfortable when they're driving?
Yes. Actually, I hope that's a really great question. Thank you so much. So again, this question has many questions within it.
Yeah, sorry.
But I'll try to answer it quickly because I think we have like 1 minute. And then if there's any other questions, let me know afterwards. So I'm hoping that this feedback-based approach, maybe you can specify ways in which you want it to drive, so you can adapt the model through that to different users. But right now, it just makes one prediction. So it's not predicting a diverse. So this mechanism of adaptation over like locations is very naive, I still believe. So because even within a location, you can have different preferences and maybe different modes of driving. So and I think that was part of your question. So I think that is that is tough. So you would ideally want to probably generalize this to include different preferences of how people are driving. So we haven't looked into that yet, but it's almost like the next question. So I really like that question. There's another aspect of this open source tools where students can now also tinker with the model and build on that. So I think tools like that are super important for education as well, that I didn't really mention. And both for users and for students and for any user pretty much. So
thank you.
Great, thanks for the question. Is there anybody else? Can I mention also diverse predictions is very important for safety. So if you you want to model like multiple outcomes in the world and then based on that make a decision. So maybe a kid can run into the street at any given time even though you don't observe anything. So that is another, that's why you need a lot of data so you can capture these cases. So maybe then the current models they can handle such things. So, thank you so much.
So I guess we're here to talk, Rudolph and I talked about the CRIS project, and Rudolph, as a chief architect, is going to lead off, and then I'll follow up at the end. Go ahead.
All right, I'm going to grab this microphone, because I might walk around a bit. Can you guys hear me through this, or no?
Oh, I turned it off.
Oh.
Okay, now it works. Cool. So, how does this work? Oh. Okay. So, AI in medicine, AI in radiology. I kind of want to say the problem is much more than AI. It sounds maybe heretical in a workshop about AI. It's also a lot less than AI. What do I kind of want to lead into? Well, first of all, before I forget, I want to give a shout out to my team back at Children's, because I would always forget. Sandeep, who's on a lot of the pipelines we're going to see, Gideon, the UI front end, Jennings, a lot of the core infrastructure on OpenShift with Helm charts and amazing visualizations, and Jorge with all of the back end databasing. So, okay, good. I did not forget to do that. All right. Without a fully deployed, a fully functional end-to-end deployment, no kind of computing, AI or otherwise, is really going to make any difference. So I've been in what I'm going to call scientific computing for, well, my entire career. I don't want to date myself. I did my PhD about 25 years ago, a quarter century. And it was in a field called reinforcement learning, which is one of the islands, right, or the continents in the ocean of AI. I'm going to try and wax lyrical. you'll forgive me, I'm going to put AI in quotes a lot of times in my talk, only to highlight the fact that AI is much more than just neural network-based models that everyone is excited about today. There's a whole field. In fact, computing is much more than AI as well. And I sometimes wonder to myself if people think computing just poofed into existence with ChatGPT. That before ChatGPT, computers did nothing. They just did email and Excel or something like that. But in my field, in scientific computing, software has been making changes for my entire career. I would even say 50 years ago, in the 70s, there were amazing software programs that were doing amazing things. So medicine is no exception. And I think the question that I often come back to is, why haven't we seen this amazing software make its way into medicine? I loved Eshad's talk, especially the first part when he said in 1995 there was a pseudo self-driving car that could get 98% of the way coast to coast. 1995. Not only has technology been around for a very long time, but it is very rarely used. So I think part of the problem that we should talk about first is what is AI. Before we can talk about AI in medicine, we need to talk about what is AI, what is computing in medicine. And more to the point, what is computing in radiology? Radiology is probably the most digital of all the medical disciplines. And I'm going to give a spoiler, it is not that sophisticated. It is shockingly unsophisticated. And I think this is a huge problem, or a huge barrier to adopting a lot of these technologies. So in medicine, in radiology, we have these amazing devices. This thing costs probably upwards of $3 million, this MRI machine. It has a ton of computing on board to do its only one function, which is to make a picture. It's like a glorified camera, right? And all it does is it stores its pictures in a database. And all humans do, or radiologists, is they sit in these darkened rooms for hours on end on these huge monitors looking at these pictures, and they crunch them with their human brains. That is the totality of radiology and computing. This is what has to change before any of the stuff we're talking about today in AI could make any kind of difference. So let's do a little bit of a quick schematic around that. We can just draw this. Here I'm going to make, in the middle is that thing called a PACS, a Picture Archiving and Communication System. That is the central thing. That is around which everything orbits. And this is what vendors charge astronomical amounts of money for. And all it is a database. That's it. Right, there might be tons of VMs around it and backup and bespoke machines, bespoke PCs that interface with it. But make no mistake, at the end of the day, it is just a database. So let's put a pause in that and talk about what we're trying to do with this thing called CRIS. So CRIS is something we've developed over the last couple of years. It's a platform for scientific computing. Kind of bringing it to the cloud, if you will. And it's a long-standing collaboration with great folks at Red Hat, at BU, at Northeast, and generations of students. Far too many people to give a shout out over here. But at its core, it's about scientific computing. Now, I've highlighted that over there because that is the angle at which I want to come in to talk about AI. So in the so-called CRIS way, all kinds of computing, including AI, run on the cloud in the same way as they would run on your laptop. And that might sound self-evident, but it's really not oftentimes how these things are deployed in a lot of large offerings with MLOps and DevOps. There's a huge change that has to happen from what a scientist like myself would write in the beginning and how it exists out on the cloud. And because of that reality, that's one of the reasons why we built CRIS, so that you as a scientist can run your thing on the cloud without having to rewrite it in Fast API or put it in a Python Flask or put HTTP requests around it. The kind of thing that scientists will never do. I've been around scientists for 25 years. You're dreaming if you think they're ever going to make a REST API call in their Python code. One or two might, out of 100. Most of them just want to write their app, read from files from the file system, and write files to the file system. That is how we do most of our science. So there are exceptions. What is scientific computing? I'm going to just skip over this slide and go to the next one because it's a bit more practical. But key points, scientific computing is always batch processed. I've never written a GUI in my entire life. Everything is CLI driven. Everything is a whole bunch of programs that you duct tape with spit and a prayer in a bash shell script, right, to do its thing. We wanted to change that and make it more portable and make it available on the cloud. Oh, and importantly, although it goes without saying, this is almost always some kind of Linux-based, sometimes Mac OS. I haven't really seen anyone doing anything else outside of those two environments. But let's talk about computing in science, and this is actually how we do computing in AI. I will have a program, I'm going to call it analysis.py, that I've written maybe with VI, well, these days I use NeoVim, but I wrote it straight up, it does its thing, and I run it always in a terminal. I might go to a directory, I might do a quick look, and I have my input and output data sources. And this is how all of our science is done. Inside my input directory, I have a whole bunch of files, there's nothing in my output directory, and I'm going to quickly activate my environment, and I'm going to type in a command line expression to run this analysis. And it will do its thing. It'll crunch, 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 and spit out an output. Everyone that I know in this field programs like this, and they work with these kind of models, quote unquote. Now, this is exactly the same in AI. If I was to do AI, like a training algorithm, I would write a Python app that consumes information from an input directory. It does whatever it's supposed to do, and it spits out, 9 times out of 10, a weights file. This is not a model. These are the tuned parameters for the model that only exists when my Python file is running. If I want to use this, it is just a program. Again, input, output. I'm kind of belaboring the point here. But this is how you would use it. You would read in the weights, you would read in your pictures, and your AI will do whatever it was supposed to do. And now it's done. It's finished. If I was a scientist, I would maybe analyze my output log file or the results to do a paper, to do something else like this, whatever the case may be. And let's look at how well this particular one did. Let's clear the screen. That was my input picture. And what did my AI think? Oh, well, it might need some more tuning. The point here is that to me, AI is no different to any of the other scientific programs that have been a staple in the field for a quarter of a century. It doesn't need anything special from my perspective. What it does need somehow is to bring this way of producing software to the masses, if you will, but to the web at the very least. So let's circle back, computing and radiology. So again, I had this picture. This is the be-all and end-all of radiological computing. And we can run this thing entirely right now on NERC using completely open source solutions. So here I have Orthanc PACS server, which we've deployed, containerized, thrown it out on a Helm chart, it's running. Orthanc is an open source product that, let's see if I can click on it. Okay, I don't know how to get out of this view. All right. Oh, okay, turn around and see it. So Orthanc, anyone can download it. I've seen Orthanc embedded deep within commercial offerings from huge healthcare companies in the US. It's certainly industry grade. Let's go back. Oops, where's mine? Clearly there's a user error. How do I get back to, I'll do this. All the way to the right of my screen. Oops, there's that, to the right. To the right, to the right, okay. Can you see it? Okay, all right, this is a bit of user error. I'll try not to do this again, because how do I get back to my first tab? Alt F1? No. Oops, sorry. Come on, come on, come on. There it is. Okay, there it is. Okay, so I'll try not to leave that, and I'll have to go back to slideshow. Okay, all right, sorry. Okay, I'm going to stand over here or something because it's not on the screen anymore. All right, so there's also a viewer, right? Radiologists live their lives looking at these things, an open source viewer from the Open Healthcare Foundation based out of Mass General. We've also thrown this on NERC, containerize it on a Helm chart. It's running out there. And we can now, I'm going to have to see if I can do this, click on there. And here we see, this is, I just want to go full screen. This is a viewer right now on NERC that is good enough, I would say, for radiology purposes, full screen. All of this data is anonymous or public. Anyone, well, you need the login, right? But in theory, anyone can interact with this data, take a look. Here is a typical image of a real anonymized CT scan of lower legs, which is going to be used in one of the pipelines I want to show you. Here is a problem, right, that exists in radiology today. I just want to know if those legs are the same length. And that's it. I just want to know if they're the same length. Why? Because if they are not the same length, there's probably something wrong. But today, and Ellen can speak to this as well, a radiologist will sit in front of a viewer like this and hit these tools and eyeball where this joint is. I'm not going to do it. They will choose a measurement tool in the UI, pull it down to where the knee is, and it will actually give the length in centimeters. And they'll write it down on a piece of paper. Rinse and repeat for all of the 4 parts of the legs. And then they'll quickly add them up, maybe in their heads, maybe in their phone, I don't know. And then they will see if they're the same length or not. This can take 5 minutes, 6 minutes, if you're tired, even longer. I think we can all agree, we don't need a radiologist to waste their time doing this. This is something a kid could do. This is something that, wait for it, AI can do. Right, so going back, I can just learn how to navigate this thing properly. Where's my? All the way to the right. There, okay. I'm gonna try and keep that to a minimum. Okay, so let's do a quick real world check-in, shall we? Because this is important as well. And this is not about AI even, but it's the real world. I just showed you we did radiology on the web, on NERC, and that was the totality of it. If you were a rural hospital, let's say in South Africa, I'll pick on South Africa because I'm originally from South Africa, hence the slight accent. So if I was a rural hospital in a province in South Africa, I might have $10,000 to spend on IT infrastructure, right? What I just showed you, a commercial package at a Boston hospital, costs about $3 million. But for 10K, I can buy 5 or 6 Dell PCs. I say PC. You wipe Windows, throw Linux onto it, throw OpenShift onto that, a Helm chart that I've just shown you, and wham, you have radiology on-prem on a cluster. I could use NERC, and the numbers might be a little bit higher than that, but let's say monthly cost of 200, maybe a bit more, maybe double that, let's say 400. It doesn't really matter. The monthly cost at a Boston hospital is 25K for that. My 10-year running costs, maybe another 10K over 10 years for my provincial hospital. NERC will be 24K over the 10-year period. 3.6 million at a Boston hospital for the 10-year running cost. After 10 years, my provincial South African hospital has spent 20K to have the same basic technology that Boston Children's Hospital would have at 6.6 million. There is no way that a provincial hospital is going to spend 6.6 million on this infrastructure, but they for sure will spend 20K on an in-house cluster. They can do this. If I say nothing else, if I end my talk right here, and I close the laptop and we're done, this will change radiology much more than anything else we're talking about today. Just this one slide. But, of course, I want to talk about it a little bit more. So let's combine these things together. That's the picture. Computing and science was this little blob. So what we do is we hook chains of this computing, firing off the PACS that lives there. Now, the commercial PACS I showed you in the previous slide has no capability to do this. But on NERC, on OpenShift, you are able to hook these things together. You are able to leverage data in one resource, pull it to another, and build these chains of computing. The database that these vendors spit out cannot do this. And if you've spent 6.6 million on that, you're going to be very reluctant to change that infrastructure. And of course, you need a little bit more. You have this whole infrastructure, which is part of CRIS as well. I wanted to highlight with that yellow or orange circle over there. Let's call that AI, right? If you want to. Without all those other circles around it, that orange circle is again meaningless because it needs this infrastructure to give it the right data, to convert medical images from one format to another, to convert them back, to put things around, yada, yada, yada. We all know the story. But this is oftentimes overlooked, I think, in the excitement of showing how great some of these bespoke computing things can be. Without the rest of it around it, you almost might not bother, except from an academic perspective. Okay, so I'm going to now shift to another tab and just show you some of these things very quickly. I'm going to show you let's start with the brain tissue segmentation, because this actually touches on the previous point, I think, that Ash had mentioned. Oops. I think I did something. Oh. I think it's rebooting. It's rebooting.
You want to give that talk from memory?
Well, it needs the visuals. But while it's rebooting, we might not be able to see all the nifty things we put together. I'm going to try very hard, depending on the time. And I want to be respectful for the next speaker as well. I was going to, at the end of the talk, say everything I'm about to show you, you can see right now yourselves. So maybe we should do a group thing here, perhaps, those of you with computers. Right now, you can go to the following URL, app, like app.crisproject.org. Those of you, you can do it on your phone. That will be a good test. That will take you to our CRIS instance user interface out on the web, out on NERC. And it'll take you to a public set of feeds. We call them feeds. You should see a table. And there should be one called Free Surfer. And if you click on that, you will see, it'll go to another display, and you will see this chain of computing, kind of like I showed in the previous slide. And those are the actual containers that have been strung together to perform some kind of computing operation. And one of those, I'm trying to think which one it is, says segmentation. And that is the one that actually takes a medical image and does volumetric classification. It takes a brain and figures out which pixel belongs to what tissue. And once it's done that, you are able to figure out stuff like, what is the volume of these structures? Are they growing? Are they not growing if you do repeated measurements? That Free Surfer, and full disclosure, I used to work with the Free Surfer team again years ago. They're based out of MGH. That does not use AI at all. There's no AI in that, just straight up statistical heuristics. It takes a long time to run, though. It takes about 10 hours. But it was doing this 25 years ago. But this entire infrastructure of computing and radiology, which is so geared to not allowing you to expand out upon it, has prevented a lot of these very useful tools from coming from the bench, from the research bench, into the clinical side. Now, there's another one of those feeds. It's called Fast Surfer. That is the Free Surfer with AI, and it will give exactly the same results. And that's kind of an interesting point, right? We tend to think that AI is going to give us stuff that we've never seen before, but oftentimes its most useful aspect is it can just give us the stuff we already need just a lot quicker. So Fast Surfer has been trained off Free Surfer segmentations, and it is able to do the same segmentation, but it takes about 5 minutes, while Free Surfer takes about 8 hours. But Free Surfer never made it into the clinical workflow 25 years ago. And we would be optimistic if we think that this AI version of Free Surfer will make it into the workflow just because it's using AI. I think the playing field needs to be rethought. And I think almost innovation is actually going to probably also come from places where they can do their on-prem OpenShift cluster for 20K, hook up their stuff, hook up this infrastructure, and begin to innovate on that as well. And, okay. Okay. Sorry, I did the wrong thing again. I know how to use computers, believe me. It's in Safari, oh. Oh, but I want it to be in Chrome, but not. Sorry, I don't know how to get back there. Back to this slideshow. I'm very embarrassed. I really know how to use this, trust me, but it's on a Linux desktop, so I'm a bit lost. Okay. So let me just go into, this is Safari, right? Okay, I don't know if it works in Safari, but we'll see. I just wanted a new tab. And whenever I hit Command T to open a new tab, it just throws me out of the whole. Oh, okay. 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 This is what I wanted to show, and if I can just do full screen. Oh, this one? Okay. All right. So this is the public CRIS that you guys can all see. You can even create an account if you wanted to. If you hit the plugins, you will see a list of all of the compute that we've made available already on this public interface. These are all containerized applications. Most of them are not AI, but you need all of these to make any kind of compute workflow meaningful. The new and existing analysis that I wanted to mention over here is a fast surfer pipeline. So this would hook up into that database that we're running on NERC. It will pull the data out, and then it would be able to run this kind of predefined computing workflow on that. This node over here is the actual node that contains the AI-generated results. And if I go to it over here and look at one of these, for instance, one of the segmentations, it will pull it down from NERC into our preview window over here. And it will show the segmentations. I'm just going to do this, put it into free surfer colors. So this is a brain that has been pushed up, the image is pushed up to NERC, pulled into our system, analyzed, everything has been classified and has been pushed back into the radiological viewer. The example that I showed wanted to show about the leg measurements. If you just go, this is a custom UI that is sitting on top of our system. Behind the scenes, all of those circles we saw are busy running. Now it's pulling an image from that workflow. It is running a scan across it. It's using AI to find where those joints are. And then once it has found the joints, there's a whole bunch of other computing that then goes and measures these lengths and actually draws onto the image a report, which we'll see now. It should be coming any second now. So those are the landmarks that it has found, and there's the report. And now it's pushing it back to the PACS interface where a doctor would look at it. So this can take a few minutes to run. By the time the patient has been scanned, it can be pulled automatically into our workflow. It can run, it can push results back into PACS. By the time the physician sits at their display, the data is there for them. And if they are okay with where those landmarks are, it takes a second for you to run your eyes and say, I'm cool with this, then you can trust that the measurements are correct. Within 1 or 2 seconds, you know if these legs are the same length, as opposed to painstakingly doing it for 5 minutes manually. All right, so I think I'm going to move on, and that's the end of my part. And let's do this.
Great. All right, and just wanted to point out that little, whoops, I put it in the slideshow, the little orange box that Rudolph was showing with an algorithm. There are so many algorithms like that we need in our clinical workflow. And the problem is if we buy each one of those from a different vendor, we just get overwhelmed by the amount of devices trying to connect to our PACS system. So it's impractical. Plus, when you work in a field where there's not a lot of people that have, say, the computational infrastructure that we have, or the people with talent such as Rudolph, you don't have people to write those algorithms that you need for the physicians at your hospital. Another example of these algorithms that we need is we do a lot of fetal imaging because we're a major fetal surgical and interventional site. But when you're imaging a fetus, their head moves, as you can see here, as you're imaging the fetus. So as a result, the images that I get to read are all this mishmash of angles in different directions. And so we keep chasing that fetus, trying to get it in the right angle so I can do a clinical interpretation and hope I don't miss anything. And we'll do it maybe 10 times. So I have 10 stacks of 15 images each that I'm working through, trying to put it all in my head and making sure I don't miss anything. And that takes a lot of time and a lot of mental energy. So we've worked with, this is an algorithm we've done with MIT, and you'll see it starts out when we get to the 0 as blurry, because we put all those images together into one coherent volume, and then we jiggle them to get them all coherent. And so we can, and this particular algorithm, which is actually an AI algorithm or a machine learning algorithm, runs in, you see, just a couple minutes. So I can take those images, and as they're being pushed to the PACS, they're being analyzed, put into a coherent volume, and then pushed back to me at the monitor, so I can actually read one coherent volume instead of 10 or 15 stacks of images that are in random oblique orders. So this is something that we're really excited about and have automated most of the pipeline on it, and we're going to make that available on NERC. And this is where NERC becomes important. We have this, but all the other sites that I know of, at least in the US, don't have this because they don't have the infrastructure. But we can share, and we're working on doing those kinds of sharing. Another thing, because we do a lot of fetal surgeries, we want to come up with more innovative ways to assess fetal well-being. And it's really hard with ultrasound to do that because the fetus, you only see a small piece of it with an ultrasound beam, so you can't get that global look on what the fetal anatomy is or on the fetal motion. So these are images that we've done, they're volumes that we acquire actually through the pregnant abdomen, and use machine learning strategies to track key points like elbows, shoulders, knees, hips. And we can track fetal movement over time and create these videos of what that fetus is moving like. And also I can get real metrics on how that fetus is moving. And why is that important? Well, I talked to you, want to understand the fetal health and well-being, but we're also working with a lot of surgeons at many different sites around the world that are part of this North American Fetal Therapy Network. One of the main therapies that's happening now in utero for malformation called Chiari-2 malformation, or a spinal cord, a defect in the spinal cord here, the skin of the spinal cord, is that in this defect here, you can see this elements of the spinal cord get exposed to the amniotic fluid. So the skin and the bones are not over top of it. So you have a sac with neural elements in it. And as a result of that, there's injury to those neural elements that decrease movement of the legs and feet. So what we do, and what is now standard of care, is the surgeons will operate on the fetus. This is the abdomen of the mother opened up. There's a little sac you see right here. And then they've closed it and put it back into the uterus, and this is after delivery. This is currently the best way to improve the outcome of the motor function of the lower legs. So what we want to do is continue to help these surgeons innovate on improving strategies for surgical management of this patient population. And here's an example of the movement of a typical fetus versus one that has a sac that's fairly high in the spinal cord, or spinal back of the spine. And you can see that the movement of the legs is much less and less of a range of motion than on the typical fetus. So now I've got numbers that actually can characterize that fetal motion, say how do surgeons do at our site versus other sites. Okay, we want to tweak the approach just a little bit and see if we get better outcomes. I can actually track after surgery, how does that change fetal motion? And it gets really important because the only way we do it right now is just look at how their legs and ankles are moving. And typically, as the fetus gets bigger, their movement decreases, so that you can't regress out normal. But now that I've got data, I can regress out normal motion and give them more accurate feedback on whether we're making improvements or not. So in pediatrics, we have many disorders with small numbers, and so industry is not interested. And I think that happens in a lot of different areas in medicine. So there's a need for a community to share images and like from multiple sites that I've showed you from these surgical centers, and to develop and share tools. And that's what we're really excited about. NERC and the CRIS infrastructure is we can say to now all these sites around the world, you can have your private enclave in this environment. Here's CRIS, go to it, go analyze your their data, use our tools, and we know it's going to be reproducible in terms of its performance on their data. And we work hard to harmonize the data acquisition strategies as well, too. So it kind of makes a community for us to work together and do really good science on how to improve medical outcomes.
Oh, all right. So quick take-homes then. We have built this infrastructure already. Today, it's running out on NERC. Those public feeds that you saw is what we would like to expand out to show all of these additional processing that Ellen just mentioned. Those public feeds, you can actually download the computing as well. It has links to the containers, or you can instantiate your own Chris on your own laptop and just run them straight up for about 1 or 2 clicks.
So as you've seen, like solving problems, particularly in this century, we have to work together. I see this true in adults, but even more so the need is in the pediatric populations. We need to work together across centers and big data from multiple sites together, and have a place that we can connect and bring all the data together to allow analytics on these data and to share our algorithms in a way that's easy to use. So for example, some of the sites here we work with are in Europe, and they don't have a team like ours. They can't even, it's really challenging for them for downloading an algorithm and set it up in their environment and run it on their data there. Here with the CRIS infrastructure and with NERC, we could actually set it up. They could do it like that, and it's no problem for them to be on the same page as we are in terms of access to algorithms. Sort of similar to what you mentioned before, Jeremy, about having 3D ultrasounds available to rural community. A rural community could, upload an algorithm. It could be a chest X-ray, and we could have an algorithm that automatically takes the ribs away, so you can look a little better and see if there's anything hiding behind the ribs. There's so many algorithms that are out there that we could put in this environment that low and middle income countries, small rural communities, as well as hospitals and other sites around the world could have access to.
And then the final thing when the rubber hits the road, again, the real world for us, at least in this field, is that there's this thing called HIPAA, which is the compliance regulatory infrastructure for any kind of sharing. And it's kind of the missing piece right now, I think, with NERC. If NERC were to be HIPAA compliant or have that title, then a lot of these other sites that I mentioned over here, these hospitals, their biggest resistance or barrier to wanting to take part would go away. And then we will be able to begin to fully connect these things together and begin to build this true open science, open source kind of medical processing environment.
Great, thank you. I don't know if we have time for questions because we're running behind. Should we see if there's one? Jonathan.
Especially since I've had a chance to see some of this over the years. So a couple of questions, but one, could you put back the chart of the cost chart just as a backdrop to the question?
It's near the beginning. Okay, that was a bit of a thumbs suck.
Oh, that's okay, that's okay.
As I'm not a...
That's okay. So a few things. First off, I was, throughout the talk, I was thinking about this last point you brought up, the HIPAA compliance. And I was thinking back to a class I taught in 2009 when I first got here about cloud computing. I invited lawyers to the class, and they said, hey, look, it really doesn't matter. Don't look to us for guidance. You do it, and society will force us to legalize it when it comes down the pipe. And that stuck with me because in the same way of what you've done, it's something now that society can actually engage with, see. So, because now you've demonstrated that, look, government organizations and legislators, it's all otherwise abstract, or they end up hearing a lot of BS from people in companies wanting to talk to them about what is not possible. But here there's an actual data center. There's a place to actually put numbers up and say, look, okay, you decide. Do you want to donate this amount of taxpayer dollars to save these lives or not? So I think this is just if nothing else, raising the bar of how the conversation engages is phenomenal. But now, actually, one of the things I was curious about, in terms of these costs, if you had your way, because I'm very curious about this cost trade-off to running it locally, what would you want to see go down in cost when it comes to something like a cloud platform? Do you have any sense of what you would want?
I guess my first want would be storage, because if you there's so much we could put, like we have lots of normative data that we share as well too. So be able to store data on the cloud and not have to incur large costs for storage could create an environment where people will come. So if we've downloaded probably 15, 20,000 data sets from around the world that are normative, for example, and we enrich it locally, we create teaching files of exemplars of unusual disorders. So having a place that you could put it where people could access and not incur large costs, because I don't think the processing is a lot. It's more, where do we put the data and how do we make that feasible? And I think when you're doing it with multiple sites around the country, we don't have to necessarily store their data there. It can be a transient, upload, analysis, download, and then wipe it out. But we still, even if that much we could get HIPAA compliant for a transient, would be a huge step forward. What are your thoughts?
Yeah, I mean, cost, money makes the world go round, right? I mean, let's say NERC, here I put 200. You can double it, maybe make it 48K over 10 years for a couple terabytes. Make it 100K, right? It's still going to beat a bespoke commercial enterprise sitting at a place like, Boston Children's. I don't know if that cost, in that space, I would see the competition more with other cloud providers. What does Amazon provide? I don't fully know. One of the guys on my team told me, oh, Amazon has this data something for open science where they give you free access, which sounded like news to me. I don't know if anyone else knows about that. But I'm reluctant to want to put anything like this on a commercial company like that. Amazon, you suck your data in. How are you going to get it back out? So the costs are important, but also what was important to me is also the fact that, and to maybe collaborators, is that you can put your data in and you can download it. There's no lock-in at all, right? I think that's super important.
Yeah, I totally agree with egress. Like, we need to put it up and get it back down, and the data governance structure is something, frankly, I think from a hospital point of view, we'd rather not have industry overseeing our data because you never know what it's going to do with it.
Right. And just one more on a technical front on the cost breakdown. So I really, your general approach to warning us that AI is not the most important set of letters in these statements when we talk about making computational useful. To that end, you did point out that a particular AI version of FreeSurfer was able to be faster, right? Now I was curious, when we consider the belief that NVIDIA is going to rule the world and GPUs are the way to get that win, I'm curious how these cost trade-offs, like, were you assuming that on that local install it was GPU based, and how do you run on the NERC side? What do you think of with respect to the GPU usage versus the CPU usage?
Okay, so that's a funny story. I mean, I don't know how many folks in the audience actually use TensorFlow on different GPUs and try to get things running. I want to say it's a shit show. It's really hard. So the stuff I've shown here aren't actually running on GPUs. They're running on Intel with AVX extensions. And it's not as quick, right? But sure, I'd be willing to have it run in 5 minutes and know it will run everywhere than have to maintain these 5, 6, 7 different 8 permutations of the same code base for different GPUs that maybe run in 20 seconds. It's just not worth it. So I don't know if that answers your question, but yeah.
Hello. Let's check slides. Oh, clicker. All right. Hello. I'm from New Jersey. I took the train here, Amtrak, and on the way here experienced a really interesting phenomena. I guess it was the not quiet car. 4 people around me were basically selling unicorn coloring books, or LLMs. Someone must have worked for Google, someone for AWS, maybe someone for Red Hat, not sure. And I kind of had an existential crisis moment sitting there, working on a talk, wondering, what am I doing here? Like, I've been doing this in this field for 10 years. Everyone is working in LLMs. Why am I going to Boston? What's the point? And I answered it to myself, but I can't say much more until I read you this legal disclosure. Nothing that I say should be used to make any trading decisions. This is not trading advice, and a bunch of other legal things. But yeah, don't take anything that I say seriously with respect to what you do in open markets. So why did I come to Boston? I could have stayed at work, and just done that thing. I realized over 10 years of my career at 2 Sigma, I've been really successful building compute systems by leveraging my network, both in academia and industry, and using that to inform what to build next. And I'm going to show you 4 different times where I've been able to do that. But it's 2024, and the truth is, I don't know what to do next at all. And I'm reaching out to this community and other communities to strengthen and build my network so I can learn from you all, and we can share ideas so that we can figure out collectively what to build next, because I'm pretty sure the scope has gotten so much bigger in the last year that it's not something that I can come close to figuring out. I guess that leads into about me, but first I'll do about 2 Sigma, because I guess I'm commingled with my work at this point. I think this is a screenshot from 2015 or 2016, and I thought it was pretty amazing. We've been doing machine learning at 2 Sigma since I've been there in 2011 in very advanced ways, and so much that this is at the top front page of our website. So we are a financial services company. You could call us a hedge fund. We do trading. It's all systematic. It's not what you may think of a trader making a decision surrounded by lots of monitors. I don't know that I've seen a trader in my tenure there in person, but I've seen thousands and thousands of computers, or at least have seen that they exist. But yeah, we really are using science, machine learning, and distributing compute to guide decisions that we make in financial markets. And that is so true to the core. And my role within that is, you can maybe look at this asynchronously, or if you want to look me up. I'm the head of IM platform engineering, and I've sort of had almost the same role for 10 years, just with increasing and increasing and increasing scope. I joined 2 Sigma in 2011, and within 2 weeks, my boss had said, okay, you own the sim farm at the time, which was 100 computers in Pittsburgh, New Jersey, that I was then responsible for. And I've worked to extend that sim farm from 100 computers, which was about, I don't know, not even 100 terabytes of memory, no, to what it is now, which is a petabyte scale compute cluster that we run to do all our model training. Thinking about this talk and my history, I wanted you to take 3 takeaways. One is that our platform, as I've seen it evolve over the last 10 years, is always a reflection of, or the rear view mirror view of what's happening now. So the platform we have today isn't really suited to the problems we have today. It's well suited to the problems we had 18 months ago or 2 years ago. And it's constantly evolving at the edges of it. As I'll get to later, it might be a little more uncertain now, but over the last 4 cycles, that's been fairly true. Something pretty obvious, but that I've seen, is that just throwing scale at the problem does work. So in 2013, we were using multilinear regression to solve forecasting problems. Today, we're using large neural nets, maybe some large language models. But the technique is less important than the scale itself. And as long as we continue to chase scale, I think we'll continue to be successful. It's just that the scale is so big now that we can't do it alone, which is the third point. The only way I think we can do this and to keep going as Two Sigma for the next 10 years is to double down on our collaborations, to double down on working with industry and academia to see around the corners and to see what's coming next, and continue to scale that way organizationally, as well as buying thousands and thousands of computers, which we also do. So yeah, what I wanted to do for the rest of the talk is try to give a sense for like what I care about, what Two Sigma cares about, what problems we're trying to solve, and then how we've used compute over the last 10 years to solve them. I've used these slides before. Sometimes they land, sometimes they don't. I'll give it a shot here. But really, everyone at Two Sigma is collectively solving what we call the learning problem. It's a learning problem just like in the last talk. They have the same learning problem. We all have the same problem. In grade school, you probably learned this as y equals mx plus b. Like there's a simple relationship between x. In our case, x may be the price of oil, y may be the returns on Exxon stock or something like that. And again, that's not advice, that's just a relationship that probably exists. In linear algebra, you learn that x is actually a matrix, and x gets very, very large, and y gets very, very large. Theta is your parameters, or your model parameters. And the whole point of this, of really being at Two Sigma, is to minimize that small epsilon. So x is all the data in the world, and y is anything that we can predict or trade on. And if we can get that epsilon to be 0, we can effectively predict the future and, I guess, print money, you would say. So how do we do that? We need a lot of computers. So we can specify this objective function. We can have 100 modelers work collectively to solve this, but then we need to do model training. And the learning problem looks like that in most places, but Two Sigma is unique in that we also have to run simulations on top of our trained models to see what would happen in the real-ish world, or at least our collected view of history on these models. So I think that's new and unique to financial services. I see a lot of people stopping at training and then deploying in the real world or testing out sample. But here we can see the real world effects of what we're doing. So we have a complex and layered problem that we're trying to solve. And now we'll talk about the 4 ways that I approach solving this, 4 generations of compute, and I guess 10 years of solving the learning problem. There's always a pattern here. We have some business problems. Something in this learning problem isn't working. We need to improve it. We have one kind of big idea, because we're not a huge company. We can't have 10 big ideas. We have one central idea that we're going to apply. And then we build out an architecture, and we use it to address that business problem, and we kind of rinse and repeat. And we've done this 4 times so far. So the first problem, and this is when I first landed at Two Sigma, was the simulation problem, which is that these sims were 80 gig JVM processes that needed to be distributed and run across 100 computers, and many modelers needed to run these at the same time. They were competing for resources using our primitive, at the time, job scheduler, where each modeler got 2.5 terabytes of memory that they could use. So they could only run a handful of jobs. But if we only had, let's say, one modeler in the system at any given time, like Saturday night at 2 a.m., the rest would be wasted. This didn't seem like the right way to approach using our computers, so I pulled on my peers. At the time, I was close with Berkeley Amp Lab and what became the RISE Lab. So Ben Hinman had written a paper on Apache Mesos. We were in touch, and we said, what if we built a Mesos framework that would allow us to fairly share resources across all of our computers, and even extend that into the cloud to overfill jobs. So this isn't a very deep and technical talk, but I'd rather leave you with some breadcrumbs. Please check out the Mesos paper if you're interested in systems. It's one of the best I think over the last 10 years, we've successfully used that to build out this system. It was a fair share scheduler that minimized waste from sometimes 60% waste down to even we were using our computers like to 90% efficiency. And that was great for a little bit of time until the next problem happened. The next problem was the X's, I call it, or just big features. This was the explosion of big data, 2015, 2016. You couldn't get enough data, right? There was alternative data sets were coming in. There was such demand, and the data sets had gone from being maybe 30 gigs to 300 gigs, 300 terabytes, and huge. And the only tools we had in our toolbox to analyze big data sets like this were like naive MapReduce that we had built ourselves. The innovation or the big idea here was pulled from Matei's paper, the RDD paper, Resilient Distributed Data Sets. I think he turned this paper into like a $2 billion company, which is good for him. For us, it was useful in that we were able to process a lot of data using basically a Spark-based system. Really naively, the idea is that you take your data set, which can be very, very large, you partition it into small pieces, and then you can run compute over pieces of that data. We got a lot of mileage out of this and actually built out our data processing kind of capabilities to the point where that was no longer a bottleneck. But then, of course, the next bottleneck arises. So this is always with systems. The next bottleneck continues to happen. So the next bottleneck was we had a ton of data. We had built a lot of models, but we couldn't actually deploy them because I think an earlier speaker also spoke to the same thing, is that modelers were writing these models in any framework that they can get a hold of. And in order to take them and productionalize them, we would have to go through a lengthy process of rewriting their code to be able to write this in a format that we can then deploy and scale out to production. So there was a great paper out of Microsoft, the Onyx paper. It proposes a standardized runtime for running machine learning models. We're able to standardize on Onyx, which is that middle blob, as a runtime that gives us a layer of indirection between the modeler's code and the deployment targets. And then so Onyx models can be deployed to run and do inference in real time. And this accelerated the pace that we could productionalize models. And then production's not a bottleneck. But now the big bottleneck, model training. And I think that's where we're going to be stuck with for some time. What we're seeing now is models that are sometimes millions, even billions of parameters because it's easier to create these models. And now 100 terabytes of even features. We're new at how we're approaching this, but the problem we had with shared clusters and shared compute clusters for doing this is that reliability of the clusters is just not there to have like repeatable, reproducible workloads. So we came up with the idea that we lifted somewhat off of the Ray paper, which is also out of Berkeley, is the notion of disposable clusters, that you can stand up your cluster at the beginning of a model training session, run it. It should be repeatable to run, and then tear it down at the end, where a model training session could be 2 weeks or 3 weeks of training. The Ray paper itself is sort of the platonic ideal of a systems paper, I think. It's a great reference on how to just build a distributed system and think about it from first principles. And we take a lot of ideas from it. I don't mean to say that like 2 Sigma is a Ray shop or anything like that, but we have lifted a lot of these ideas, especially the global control store and the object store for scaling machine learning. So this is kind of the recap. What I've experienced is this set of S-curves, right? So we have some new innovation, we accelerate really quickly, and then that problem becomes a problem in the past, but then the next problem comes up, and we're kind of flattened out for a while, and then we accelerate again. And we're somewhere around 4 here, and we know we're in a period of great acceleration, but definitely I feel different this time in that there's so much more uncertainty. I don't think there's one big idea that we can take away. There's not one key paper that one could pull from to get us through the next 2.5 years. it's a point where things are just exploding. And I really felt that in my experience on the train when everyone was talking about LLMs, and I was just sort of baffled. This is just a few of the things that we were thinking about and a few of the problems we have. So it's really sprawling out. We know these things are coming. We know that we're working on them, but we don't have nearly the size of people or enough people to put, each of these is an entire research agenda. How do we efficiently use GPUs and not waste them in I/O cycles? We want to build high performance algorithms for time series ML. There's so many things. I'll walk through some of the challenges that I have because I think I have some time. But again, I think it comes back to this point. Like, this is now too many things. It's too big for us to go it alone, and we want to collaborate. So that's where I think we get to the MOC plus 2 Sigma, I guess, value proposition here. I can come with lots of problems. Some people say, like, there's a paper idea a day at working at 2 Sigma, and I can kind of broker those out. We can share, we can find students, we can find opportunities. It's just a matter of how much we collaborate. The fun ones that I like to look at are GPU efficiency. How can we quickly get data to the GPU and use them efficiently and not waste them? We have amazing data. I call this class of data exhaust data. It's like, we can't share our 2 Sigma data. That's private, like financial data. We can't share our models. But the stuff that comes out of the exhaust of our systems, trace logs, GPU utilization metrics, things like that, I think are a great asset and a great wealth that we're underserving now and could share more of as we collaborate. High performance algorithms, it's pretty wild, but we still see common techniques that machine learning researchers are doing every day are like n-squared complexity, and just, it's right in front of you. And you can see opportunities to get down to like n log n or less. And it just takes time and work and analysis to do that, but the impact and the leverage is phenomenal if you can do it. We have a whole team dedicated just to doing this. This is meant to be there is such a sprawl of foundational models. If you looked at, like, I don't know, are there 20 released every week? Maybe there are 5 released every day. Like, how can we even keep track of these and compare them and evaluate them? It's a big area for research for us going forward. Fine-tuning models is another place where we're just getting started. It's pretty difficult to do this within 2 Sigma's firewall. And so having open source partners where we can do experimentation on synthetic data sets that aren't real but give us experience doing fine-tuning. We bring some expertise to the table to how to set these up, and we're looking for partners to work together to do things like this. And finally, just this baffling statistic or baffling number. Someone asked Sam Altman how much it cost to train like GPT 3.5 or 4. And he said, was it 100 million? He said, no, probably more. And at that point, like, you talked about money and like access to equity and who will control it, but not everyone can play that game, not even 2 Sigma. We're not going to train models that cost $500 million to train. There's diminishing returns. So looking for like low cost, low rank approximations, like lower precision ways of training, but we still know we want to train our own models, is another big research area. So I took a shot at kind of a matrix. I think Larry helped me work on this, but these are just my ideas of how we could work together. I mentioned it before. What I think you all have is on the right-hand side, and what I know we can offer is on the left. Like I said, we have pretty well-specified, reproducible problems with benchmarks that it's possible for us to share, and we'd look forward to doing that. And they're very unique, I think. Especially in the area of ML AI, where we don't really need proprietary data anymore. We're doing a lot with synthetic data sets. That's recent as of 2023, so we can begin to share more. The exhaust data that I mentioned, I think would be a great opportunity. And then finally, we do use cloud resources. We use Google or AWS maybe. And that limits us into the way that we can experiment with hardware. And so having a place where we can get more and look at the full stack of hardware and build training clusters that take into consideration storage, network, the full stack of the training solution would be a great opportunity for us in MOC, where I think we have not built out that experimental capability on our own. So that that's the call to action. That's my ask. I'm here all week, so we can talk about that, and please reach out to me. Thanks. Yep, I shut it off. Oh yeah.
Hi, super fascinating. It was really fun to hear that longitudinal look backwards over those 4 generations. And so this relates to actually, the question relates to that and 2 of the lines in your collaboration chart. So what I was struck by, and I'm always struck by, and Rudolph brought this up in the last thing, training, learning, the learning problem, looks a lot like scientific computation. Over the years, the US government has subsidized the construction of systems like Blue Gene and other systems, which have a much better density and interconnect fabric. But I saw a very consistent commitment to the hardware platform through those 4 generations. Do you think you've reached the inflection point where, okay, maybe now we have to consider something that is not considered just commodity, but can actually be towards, because I mean, we're moving in these very strange ways, right? A GPU is not commodity, except that now it's commodity because we made it commodity. A TPU is not commodity, but it's going to become commodity. And yet we're always stranded behind just, for bleep, interconnects, right? The interconnects are horrible. The connection to the density and latency to the RAM is horrible. And so I'm curious, do you think that that's one of the things forward? And then I'm really curious about the exhaust data. Like, what do we practically do to get access to the
You do that? Yeah. Well, luckily, I have peers here who are pretty closely connected. John Stumpf is here. Larry Rudolph, who I've worked with for, since he arrived at 2 Sigma, has been a mentor to me. And they can both help, I think, on the exhaust side. I know Larry and I talk about it a lot. We want to make it happen. So we'll have to figure that out. On the, the question, I guess the first part is like commodity. I feel like we've exhausted our ability to innovate on commodity hardware. I think that we probably spent that is like everyone in distributed systems has spent like the last 4 years building out abstractions that work together to like do integrated workflows, things like Kubernetes pods or like the best practices for building out these training things at the expense of optimization. And now optimization is the only thing we have left. So we can't really, if you saw like Altman's quote, we can't just scale out to like $100 million worth of computers and like get sloppy about it. Like if you can not be sloppy about that and you can do that full stack, we see like 10x, 100x improvement opportunities maybe, possibly. But we need a proving ground and partners, and we need people who can work on that with us, whether they're in industry or here in academia. But yeah, my hypothesis is we're kind of done, at least in 2024, on commodity hardware, unless you're doing naive things with like services or something. But even once you get into fine-tuning and other things, it becomes optimization. And so that means like retooling, rethinking much of what we built over the last 4 years, and then even skill sets, how we engage, and what we do going forward. So it's definitely a critical shift and a critical time, I think, in the history of distributed systems. Like if you look back the last 10 years, it really was kind of simple to know what to do. Like it wasn't rocket science to use an RDD. It was like, do it. Yeah, like find Mesos, Kubernetes, they're basically the same thing. Now, no, I think you really need like a much more deeper approach and to be much more scientific and rigorous about it.
This is great. I sort of see a lot of, like, it's been really fascinating for the last number of years interacting with you guys. And you've built a lot of also either bespoke or proprietary internal systems, not that you necessarily want it to be proprietary, but because in some sense your problems, or at least you thought your problems were unique. And then I look at, and a lot of those problems I think were just maybe a little bit in advance of other people realizing they had that same problem. So is there, like, I'd love to see exactly what you're talking about, that engagement of building new things with new characteristics in kind of an open place where we can innovate or bring in the AMDs and Intels and others with GPUs or TPUs and stuff and be experimenting with that. Is that something where, you know, we could imagine sort of you have the requirements, but then we build a new system together? Is that sort of external, developing it outside of Two Sigma?
That's what I really aim to do. It's you know, my next 5 years goal is to get to the point where Two Sigma is doing that. So when I opened the talk, I said that, you know, our architecture reflects the rearview mirror of the last 2 years. But like, what's looking ahead the next 2 years? We're a bit, you know, limited and reactive. I think through partnerships with the Alliance and others, we actually can do that. And we can do that, probably to your earlier point, is because like workflows are becoming commodity. It's about like data. If you can get synthetic data, which we know the distribution of our data, so we can build synthetic data sets, we can share a lot more than we could even back in like 2018, where we really didn't have our head around like what machine learning was going to be at that point. Now we have like very contained, isolated workflows. These are model training jobs that run on some, you know, maybe 400 to 4,000 GPUs at some points, but can also be like estimated at smaller numbers and taken down, where like students or people, you know, here can actually like get their head around them and work together to building out a reference architecture for like the next, you know, number of years. So yeah, that's really answers that existential question: is why am I going to Boston? Same reason I'll go to Berkeley, you know, in 2 months. It's part of like getting people together to work on this problem collectively.
And so if you just flip it for a moment, I mean, you're saying that in the past this was a proprietary advantage, but now it's not, so you could feel more comfortable building these new systems in the open? Is that?
Yeah.
Is there any difference? Maybe just.
I mean, there's going to be a line, right? And you know, we've built a lot of systems where we encapsulate the pieces of intellectual property that we still wouldn't share. But like, I guess we're computer scientists. We can build black boxes around those things. So whether we're using, you know, linear regression or something different, kind of the learning problem is the same. It just has a different profile. And we've learned, especially because we have interns, we have people who just work for their first year at Two Sigma. We don't give them access to like all the data and say, you know, go to everything. So we've learned as we try to onboard new people that we need to simplify kind of the problem and control access to what is IP and understand that better. So training, you know, a giant model at scale, even maybe there's some techniques we couldn't share the name of, but we can give approximations to those that have like open source equivalents or in the same family or model hierarchy.
So one last question is that, do you view, just looking forward, there being unique problems for you that aren't general? Like I remember talking to Mark way back when, and he was talking about how you wanted to retain the provenance and certain things like that. And I was thinking, oh my God, that would be so useful for academia if we could do those things. But I'm just curious, do you sort of perceive that there's unique problems you have that are either not interesting or that one wouldn't want in a general platform? Or is it, do you really feel like it's much?
No, there are definitely big classes of unique problems that we have. Training or techniques for doing like LLM style machine learning over time series data and treating like time series as language. is a research area that we would not probably be comfortable sharing. It's very like unique to what we do. Even the notion of time, when we start talking about like time in general, there are actually like proprietary ways that we think about time and bitemporality. There are things that we wouldn't share, but they're always encapsulated. That's what I found. And the organization is such that that encapsulation or that containerization is both how we build software and also how we're structured organizationally. And so I realized that that design actually does give us opportunity to now reach out and share more. And I just don't think that was apparent, or we had the right people in place to form those relationships in like 2018, 19. I remember I actually was here in 2019, I gave a talk, and then like pandemic hit and it all kind of got reset. So this is sort of me like saying, I'm over that, like we can start again. Yeah. But I think we're well better suited to do it this time. Cool? All right, thanks.
Great. Thank you, David. Thank you, Ellen, Rudolph, and Eshed. That concludes our morning program on AI and the AI Alliance. So if you'll enjoy lunch right now and come back, lunch will be served over here in the same room. And if you will come back around 2 o'clock to start our second afternoon session on the marriage of data and compute. And if there's anybody that has any allergies that had listed it, you can just talk with Tara at the front. Only a nut allergy. Everything else is labeled, but if there's a nut allergy thing, you can just chat with Tara before you grab your food. Thank you so much. Folks, if you'd come on in and take a seat. We'd like to get our afternoon session going, please.
And,
if you prefer.
And there's a clicker?
And there's a clicker, just so you.
And there's, I can stand here and talk, okay.
Yes.
Okay. All right. Should we just start?
All right, folks, let's head out. Let's start our afternoon session on the marriage of data and compute, and we'll start here with Larry Rudolph.
Thanks, everyone. And right, no one wants to come late to a wedding, so why don't we start? I don't know which is better. I'll start here. Hi, I'm Larry Rudolph. I'm talking about the marriage or the benefits of sharing and collaboration. It's really the intro talk or the summary talk of this afternoon session. So let me, I guess, first, I'm Larry Rudolph. I guess my current title is Distinguished Fellow of the Mass Open Cloud. I've been with Oran since its inception. I've been an academic most of my life, and I'm at 2 Sigma during my day job. And because of that, we're legally responsible to tell you, do not take any investment advice or any money advice from me. Forget about even the legal issues, just in general. Don't trust me with that. On the other hand, when I put on my MOC hat, the answer is I do want you to listen to me. So, you know, it's not going to be about that. But let me just sort of start. In the beginning, there was compute. At least that's, I thought, you know, we just had this whole machine to ourselves, and the machine was really important. There was data for the machine, and then we went on and we got on to HPC and simulated the world and all this stuff. And there was also data, and there were databases where, you know, data was important. And we built up data centers for it, and maybe even you can look at, you know, AWS is really for data. Browsing the web is just providing data, doing commerce and the like. So depending on your point of view, either compute is the king or data is the king. But they've really been in separate camps. And the obvious message is that that's changing. There still is compute world and HPC, and there still is database world. But there's this new thing, which is this combining between the two, which we often call a data pipeline. And the data pipelines come in all shapes and forms, but that's the thing. And there's compute, takes in data, generates data, there's more compute on it, and it's a big pipeline, some of which is shared. The nodes might be database, the data might be in a database, it might be in a CSV file, a data frame file, all those things, but that's what's going on. There's a lot of data pipelines going on all over the place now, in addition. So just imagine this world that, you know, before you can use data, right, you have to download it or make a copy somewhere, make sure you have enough space for it. You have to clean it, normalize it. You have to think about checkpoints and backflows and, all this stuff. And it's a big mess. And really, I tried to sort of define this big mess. We've heard a lot about it this morning, but it's probably messier than I described here. And sort of that's the world that we're sort of kind of in. The world that I want to get to, right, the world that would be nice, is you can immediately leverage related works. And it would even be nicer is whenever you did that, you were able to share the costs in some way. The more times you looked at things. That there should be easy sharing of data. It should be reproducible. If it's reproducible, then you can share data because you don't have to worry, and store it on some immutable storage. So you don't have to worry about sharing because people can't change it. And if it's reproducible, you can still regenerate things. It recovers from failure, it's more efficient. But the really interesting part is the cost of producing may be offset by the cost of from the producer by the cost of the consumer. So it's a different kind of sharing, but you make data and other people use it, you have to worry about the cost there, and you can sort of share those. So it supports a community culture, and the like. So just a quick example, we talked a lot about AI this morning, right? But consider how do you develop these ML pipelines, with the AI pipelines, but it's not just for ML. We see this all over the place, and certainly at 2 Sigma, we see this a lot as well. You have to do data collection. So what happens with data collection? You have to download it. You have to perform processing steps. You have to normalize it. There's all this junk that you have to do, and it's all hard, right? It's where do you get the data? Are you allowed to? Do you have permission for it? Are there new versions? Do you have to find code? Do you have to buy the code? Each time new errors are found, do you start from the beginning? And then you do stuff with it, and now you have to worry about the naming problem. So there's a lot going on. We heard a lot of the nightmares before. That's only the first step. There's a pre-processing step. The same kind of stuff is we're batching stuff, we're getting it. There might be errors. You might have to clean it up. So now we have to go back to the data collection step and do those things over and over. Oh, that came out bad. You have to decide how much you run. If you run many versions of the data, what do you do with that? How do you name it? How do you collect it? Where do you store it? Where do you share it? We can go on and on. Then there's the training part, which is also pretty bad, right? So there's all these steps. You have lots of decisions to worry about. Bugs can happen anywhere. I have to get these GPUs. They can be wasted. I do half the thing, and now I have to sort of change a version. So the costs really add up very, very quickly. So there's the big guys doing AI, and they can have sort of huge costs. And there's the small AI, which you can run on your laptop. This intermediate stage is where really all the costs are. And you get the point, right? It's just more and more and more. All these steps, they're all data pipelines, and if they're sharing, they're now DAGs, direct acyclic graphs, with the nodes and edges, crossing all sorts of domain boundaries. You may be sharing it from someone else. There may be different organizations and different hyperscalers. It's not only that there's human in the loop to make all these decisions, but you don't know who those humans are. Some decisions are made upstream, by the time things get downstream, you don't know what the downstream person, who is downstreaming, who's doing things there. How did you change, what do you do about bad data? Do you get rid of it? Do you turn it to 0? It really matters to the downstream person. Okay, so that's AI. The main point, and I want to say this the main point over and over to sort of build it into your heads, no application is an island, right? It all depends on other code going on. Similarly, no data is an island, right? Data is not just sort of sitting there. It's interacting with other data, there's other code. And similarly, no server is an island, right? It depends on your sort of point of view. So that the data, the pipeline, the hardware at scale, we now have all these weird problems, right? When you go up to scale, there are these emergent properties that come out. And, the number and size of data sets, the number of people involved, the number of data scientists, we see that in the data cloud. In the cloud, we figured out how to deal with that scale somewhat, but it's still, we're putting now all these pieces together, all of which scale, all of which weird things can happen that we know about. Part of it is, I think the solution is to share and collaborate, to share information, to share partial results, to share, and to share metadata and to sort of collaborate. Here's a picture of black swans, but there's actually lots of black swans. Yet another way of looking at it is this mess, is the fact that a tenant's point of view is they know their DAG, they care about their DAG or their pipeline, and that's the whole thing. And that's what they care about. And somehow you have to get that in the cloud, where the cloud is, just a bunch of servers and networks and storage, and that's all you sort of care about. On the other hand, from the provider's point of view, it's exactly the opposite. They care about congestion and packing up the servers and where's the storage going to be and how is things kept cool and how money is made and the like. And what do they get in? They don't get in DAGs. They get in, by and large, of just a bunch of jobs and just a bunch of storage. So, there's these two different views, and really, we need both things. We need to put two things together, right? The goal is to optimize it just the way we did it for running just the way we did it in the old days. When I had an application and a computer, I put the two things together. The Intel has a whole bunch of probes and counters and analysis to tell you what's going on, which can feed into the application, which can feed back into the... So there's this very close connection. We went to the cloud and we sort of put this barrier between the two. So I just want to stop here for a second to say that I've just described two different marriages. There's a marriage between data and compute, and there's a marriage between the tenant and the provider. And there's actually a marriage between the data and compute. So, it's a four-way marriage. I don't know, whatever we're going to call that anymore. It's a marriage between couples. I don't know. The analogy breaks down. Sorry. So now we can imagine, with all of this going on, just imagine this world where, there's like tons of storage, and any server can access any data, and the probes measure what's going on, and we have multi-level caching, and there's security and usage accounting, and anyone can try out new hardware. And there's no single commercial entity that's controlling everything, and profit is not the motive. Just imagine that world for a minute. Oh, wait, we have that world. We're all here about the MOC, which kind of is that world, right? So so really, if we think about that world, then we can start thinking about doing all these, how these marriages work together, right? So there's sharing data. Well, there's two talks coming on in this session right after me about, about Dataverse and the other data commons. Sorry, that doesn't come out well. They're going to talk about FAIR, the FAIR data principle. I'm sure they do. But it's also, I want to sort of emphasize that data without compute is like a day without sunshine. They're just sitting there doing absolutely nothing. There's no need for everyone to have their own copy if we have this immutable storage and we have some ability to share with the right protections inside. And I don't know about you, but my days, I'm old enough to know early days that Nokia used to charge you for downloading bytes over their internet. And when you went to a web page and you reloaded the web page, it would charge you for reloading it and downloading the bytes. Really, what was going on behind the scenes is they cached that page, and they just knew how many bytes it was, and every time you went to the page, they would charge you for more bytes, even though they weren't downloading it, until people found that out, right? The web, in the clouds, they're charging for storage. Are they doing deduplication? I don't know, but they're still charging for storage, right? So there's no need for everyone to redo the same data collection, the same pre-processing. We sort of have to figure out how to sort of not keep repeating everything over and over again, or turning on the lights. Okay. Trying to get them on or off? Okay. So there's also, I'm just giving a little quick advertisement, which we're not going into sort of real detail, but at 2 Sigma, we're looking at functional semantic types, which helps sharing data, because I may have almost the same data set as you have, but if I've named it differently than you, how do we even find it? Or I'm looking for some data set, and I don't know. Humans name things in weird ways, and it's not so easy to find it. So we're saying if we can give consistent ways of talking about semantic types of data, and I can export those, then I can input the data better and do quality checks and the like. Same thing about sharing this metadata with a hardware state. There should be this talk between the two. We collect provenance. Provenance really helps. I understand what's going on both sides, and it can exploit that. If we can sort of talk, we can learn the attributes of how to do better applications, and we can learn which data code is there. So this is all some sort of shared caching, community caching, all based on the fact that I know what's going on. I know the future. We run these pipelines or these DAGs, and they get run over and over again, so we can sort of learn from that. Okay, we can leverage shared memory. Another little, it's not being covered today, but I really like think about a rack, and there's a board there with tons of disaggregated storage, and any server inside and every machine inside can access that shared data. And if you're really smart, and it's going to be cache coherent, and it can look like real, just uniform non-memory access. Adam showed me a paper from Google which says, oh, we don't need this. In the Google Cloud, there's that CXL and having this shared data in a rack that doesn't help. That's because their workloads are not sharing. At 2 Sigma, we run tons of simulations, and they all start with a similar state. And if you're doing parameter exploration, it all has the same data sitting there. So why make copies everywhere? Why just be able to sort of get something that maps it in and out? Reproducibility is a key concept, and we're going to sort of talk about that. There's the Memento talk is going to sort of cover that. I guess you can't really see this. There's semantic cloud work that's coming out of Red Hat by Uli Depper, and he's not here today, but that's sort of part of that same idea. So during the data pipeline execution, the results of the data transforms may be memoized, and you'll hear that in Memento. In the future, when the same transforms on the same data, the same parameters in the same environment, there's no need to re-execute. So that's just another way of sharing. The vision is sharing. This is the last slide, because I think I'm out of time. So the place to be is the MOC, a nice phraseology. It's a production level system, and we have lots of data to share. And we have lots of talks today. I guess I missed D4N. That was another one of the talks about the shared cache. So researchers do want to share. They want to share with themselves when you debug and something crashes. They want to share with their colleagues in some way with the right attribution. They want to share with other organizations. So this whole idea of how do you share and collaborate means that we don't have to waste resources re-executing. We don't have to waste resources sort of having things sort of half executed on expensive GPUs and the like. There's a lot of work. We've heard some of that this morning. We're going to hear some of the pieces this afternoon, right after my talk. But there's a lot more work to be done, and I think that's the way of sort of driving down the costs. And the MOC is a good place to play for that. So thank you, and now it's sort of be time for like maybe the engagement party that comes on for the next sort of several talks. But that's sort of where I think we should be going. And I rushed through that. I put my New York accent on, talked fast so that we can leave time for questions.
When you say they want to share, I mean, I think a lot of people don't want to explicitly share. They don't want to know it, but they're willing to have the value of what they did sort of reflect for others, right? You don't actually mean sharing necessarily. Sharing, of course, happens in research, but it's more like they want to get value from what other people did? Is that what you mean by share?
So I think it depends on who you are and what level you are, right? The parameter exploration wastes a lot of code and start from afresh. and just change something. And so there's clearly you're sharing with yourself a lot, and you don't want to put that effort in, right? If someone else computed something exactly the same way and you don't know it, you should be able to get it, right? There's just sort of, you don't have to know it, it just should happen. Just the way deduplication happens in data centers. You don't know it's being what's being deduped, right? But in the same way, you can sort of say, well, I'm calling this, and it's available. Right.
So I think that's one of the, so this is happening in the public cloud, of course. People are building these shared services where if somebody does something, just like you said with deduplication, other people or they're getting the advantage of it, but they're probably still charging the full rate of the thing. What do we charge? I mean, I know what to charge for things where they're from scratch. We're trying to charge the real cost to users of doing it. Do we just charge the first guy and then make everybody else get it for free, or?
Thank you, yes. That was actually hidden somewhere in the slides, but yes. Right, so the idea is, no. Imagine the world where the consumer doesn't get it for free, right? We start sharing those costs among the users who've done it, right? And not, sure, there's shared services, and we know that, OpenAI says, give me all your data, and we're going to exploit it, and not pay you, not pay you nothing, but charge you for using it. That's not the way academics sort of generally work, and we should build this academic infrastructure that doesn't work that way, that says, if I get to use it and I didn't have to pay for it, then I should contribute something, right? If 10 different researchers all access the same data, the person who produced it should, in some sense, have only spent, whatever, P or D over N, and spread that among.
I love this, obviously. How do we, who builds it and how do we build it?
Well, the question is, what is it, right?
That's a good place to start, I guess.
Right, and so we're going to hear some talks today, which is some start, but saying we need to start figuring out how do they communicate. The communication is the hard part. How do we get the provider and those probes to talk to the applications? We're starting to get there. But there's a lot of little things that we can do to sort of start getting this there. Having metadata in the right format that everyone can read is another sort of big help, right? Having this ontologies, so semantic types that it can sort of find stuff and that may symbolically look different, but really underneath it is exactly the same. So these are just the first steps that we do, and just keep pushing it more and more.
I guess I see all of those things as necessary, but ultimately it's partly a user interface problem, right? The problem,
I think
the problem the data scientist or the domain researcher has is, connecting all of these things up, but also just a way to manage and deal with all of these data sources.
So one of the talks, Mark's talk, is all about naming, right? Naming is a systems issue from start to finish. So how do you name this stuff? And you'll hear it in talk a little bit about that, and I think that solves a little bit of the problem, which is more than just what you were talking about.
It's one of the 3 hard problems, right?
Right. Any other questions? I don't want to delay the rest of the talks. Great. Well, here's the thank you slide, and thank you.
Great. How's everyone doing? My name is Wayne Gilmore. I'm the Executive Director of Research Computing here at Boston University. And with me I have Emery, who's the Research Data Officer at Harvard University. And Scott Yokel, who's the University Research Computing Officer at Harvard University, could not make it today. He's feeling under the weather, but I'd like to thank him for giving me the opportunity to speak in his place and help him out here. So today we're just going to talk about a couple of the other building blocks, right? So how do we enable research computation for all the researchers at the universities that we support? And there's three areas here I want to talk about, is just generally research computing and what is research computing, and then sort of the transition that we're going through right now, and that is accelerating in terms of the shift between traditionally supporting HPC type workloads to supporting cloud workloads for the research community. And then where do we go moving forward? And arguably one of the big things now is data. What do researchers do with all that data? So Emery's going to talk about the Research Data Connect program at Harvard University that they're working on developing, that really works with not only research computing, but libraries and research administration. All three components are very important in helping researchers really manage that ecosystem of their data as they do their work. So many times people focus on hardware, compute, storage, and arguably those are super important things, and they continue to evolve, especially in the world of AI. But I would say that in the support of research, probably one of the most important things are the people and the facilitation that happens between the people on research computing support staff and the researchers themselves. And here is, you'll see that this is kind of formalized around 2014 with the ACI REF program that the NSF has funded, and it has grown into essentially a whole professional organization, so the Campus Research Computing Consortium, CARC, that essentially is a large virtual organization of research computing personnel that really are there to support each other in sort of move the process forward in research computing facilitation as a profession. So what do research facilitators do? And what they do really is they work very much directly with the researcher, and they co-learn and co-create with them. So many times a researcher will have a very interesting research problem that they come to us with, and they know that they need a lot of computation and a lot of programming and application support to do it, but they don't really know how to do it and how to figure it out. And a lot of times these research problems are very novel, so we have to actually work with them and learn with them and create with them to do these products. And arguably, the research facilitation field covers all the technical and support areas, right, of supporting research and research computing. So systems engineers, application developers, application support people, and service support people. And many times they have to all work in tandem with a researcher or a researcher's lab to help them solve their problem and move their research forward. So it was probably one of the most important things, and it very much differentiates research computing somewhat from traditional enterprise IT, although I would argue that enterprise IT is starting to fall into this paradigm as well. Whereas enterprise IT really just provides services to the masses, but research computing has to provide customizable services, right? And to really meet specific research needs. So here's just a slide sort of reiterating for most people that know what high performance computing is, right? And you know, high performance computing traditionally has been fixed computing environment that is deployed over a scheduled system. So researchers will submit their jobs, they have to wait for those jobs to run, they get results back, right? And typically command line interface, although nowadays we have extended the HPC landscape using products like Open On Demand to provide web front ends, right, to HPC clusters, which has been very well adopted. And very much tailored to parallel processing, GPU computing, messaging fabrics like MPI, and being able to move bits and bytes between nodes very quickly. So those are all kind of the traditional aspects of high performance computing. And you know, a good example is like a quantum chemistry field, right? So when you have a 10,000 by 10,000 matrix, that requires 10 to the 45th combinations of analysis. You're going to really need a parallel architecture system and application layer to be able to do those type of calculations. And this is essentially what very large-scale high-performance computing is doing for the research community today. And how has research computing grown? So this is essentially the work we do at BU. On the left here is 2013, what our HPC landscape looked like. And we had less than 1,000 researchers using our system, doing maybe 10 million CPU hours a year. And these starbursts essentially show the amount of usage on log scale by the different departments in the university, right? And in 2023, we're almost up to 100 million CPU hours a year, supporting 3,000 researchers. But more importantly, we've probably supported departments in every single college in this university. So that really speaks to the breadth of research computing, where you have people in fine arts, hospitality, and so forth, and they all need the cycles, they all need the computation, and they all need that facilitation expertise to really help get their work done. So this has really exploded across all research domains, and so it's going to continue to grow, and we're going to have to continue to support it best we can. You also see that we're servicing a lot of students, so increasingly faculty want students to use the same type of systems that they're computing on, whereas today, we're supporting over 50 courses on our cluster with over 2,200 students. But the nature of research computing is changing. We've done a very good job at trying to add additional things to the HPC framework so that people can do graphical work, people can use web browsers instead of command line interfaces. But there's going to be limitations to that in the type of environment that a typical high-performance computing cluster can provide. And so we need to adapt with the times, like everyone else. So why is there the shift, right, from HPC to cloud? And so, HPC to cloud essentially is how do we go from a, fixed computing environment to a very dynamic environment where researchers and developers can actually build analytic tools that could be used by not only one research group at a university, but shared and used by researchers all over the world, right? And instead of having to, use schedulers to submit your jobs, how do you really get on-demand computing and storage accessible to you so that you can do the work on the fly that you need to do. So there's very, and then there's also oh, sorry, that was the wrong slide there. Oh yeah, on the right, excuse me. There's always the basis for product development as well. The work we've done with Red Hat in leveraging their data science environments and providing that to researchers to be able to get their work done. So these are examples of the type of workloads, right, that aren't very well supported in high performance computing, but could be very well supported on cloud type infrastructure. And everything from burstable resources, so we only have so many resources here on campus. How do we burst into larger resources and be able to give those back quickly? How do we support systems and cloud research, which a large part of this workshop is about this week? Traditionally, that has been very hard to do, not only on HPC resources, but very difficult to do on commercial cloud resources because you're working in a black box. And then how do you support not only one data science platforms, but the numerous data science platforms that will come about and be developed over time that cater to very research domain specific communities. So, back in 2018, BU and Harvard Research Computing envisioned an open source cloud environment that we could work on, that we could put in production that researchers could use and serve research in the academic communities. And really, this is built on a very solid foundation that has grown over time. So as Gloria alluded to this morning, there's the MGHPCC, which was very pivotal, right, for the 5 institutions that are part of that consortium to really stage research computing, work on collaborative projects, and really start working on providing more shared services to the entire community, not just to one university, right? And then on top of that, we leveraged Northeast Storage Exchange, which provides us large data store, both in terms of Ceph data and tape archive data. And then on top of that, we have NERC, right, which is going to provide software platform, infrastructure as a service, data science platforms that can be easily accessible by researchers and the education community in a very federated way, right? So if you're at one institution, you can access these resources just using your login credentials for your institution. Another institution can do the same. So how do you make that access to those resources very easy to do? And then the interesting part about a production cloud service is that we can really leverage all of the work that the Mass Open Cloud Alliance and Red Hat has done over the past decade, right, in terms of development of software, such as OpenStack, OpenShift, and the Red Hat data science environment. And what we can do is, as those products are developed, we can actually start exposing those to the research community, provide valuable data back to the developers on the MOC Alliance side and the Red Hat side that they can learn from. And there's this iterative cycle on how do we continue to optimize sort of those products and really cater towards the use cases that researchers and academics need over time. So it's pretty novel in that approach, in that we can expose these technologies to the research community, and it's worked pretty well. And you know, this has essentially been backed by a lot of investment by a lot of parties. So we have the MJHPCC, which is really a $90 million investment by the 5 universities in the state. We have the NESI project was backed by a $5 million NSF consortium, and we're now self-sustaining in that service. And then also industry partners. Red Hat's listed here, but there's many more industry partners that have contributed a lot of additional things as well to make this success. And then currently, who's using NERC? So NERC is being utilized by almost 70 investigators right now, 11 institutions, and you can also see the breakdowns of disciplines. Right, so this will over time look very much like that Starburst, where we're servicing pretty much all domains on NERC to be able to get research done. And then a couple of projects that are leveraging cloud right now. The first one here is the PCAN, which is the Predictive Ecosystem Analyzer project. This is out of BU, essentially a science framework built on RStudio that runs ecological forecasts for students and professors. This is using the NERC OpenShift environment and Red Hat OpenShift AI platforms. You can see the components on the right-hand side here. And I'm going to turn it over to Emery now, who's going to discuss a project that's going on at Harvard and research data comments.
Thank you. Thank you, Wayne, for doing the difficult part of the talk. So I want to talk about a couple of things what we built at Harvard. But before that, I want to answer the question, which one is the king, data or the compute? I might be a little bit biased as the data officer, is that the answer is data. But a bit of minor footnote saying that the data you don't do compute on is trash, you are paying money to keep. So what are we doing with this data? This is NSAF group. They hold, last I looked, about 95 terabytes of data. They have data from air pollution, they have data from census, they have very highly regulated data from Centers for Medicaid and Medicare. They combine all of this to see people living in dirty air, does that affect their health? And their studies are one of the only explicitly cited studies in EPA policy change. EPA changed their air pollution policy because of this study. And it has been shown that this study increased life expectancy up to 7% for adults 65 and over living in polluted air locations around the US. So this is why we do this, right? We are doing this so our researchers come up with this research that actually affects real life. What they have is, they used to have all these flat files, 95 terabytes of flat files. But what they're doing is now they're using Apache Airflow. They put this into a database. They look at the database using Apache Superset. They pull data from this database. They do analysis on it. They do compute. And they come up with their results. So beyond the tech, why not we let researchers build everything? I'm sure there are researchers here, so sorry, but if I let researchers build all of this, it will be a mess. So we need to build this and give it to them. So what's the problem? What this thing that we are trying to build? If you think about a very standard data lifecycle, there is a lot happens before we actually start doing the compute, right? And we know that compute is the king. So what do we need to do to get to the part where we do the compute? We have to do planning. We have to do what data we are going to get, where are we going to get it from, who is going to pay for that data, is the data regulated, what are we agreeing to while we're getting that data, how are we going to keep it safe? If we don't plan these from before even the project starts, it's going to cost double when we hit the compute part. We need to make sure that we can store this data. We need to make sure that we can do data management on it. I bet $5 to anybody here, if you go to a researcher and ask what is their biggest data management problem, they will say that I don't have enough storage. And you tell them that's not data management. So we need to tell them how to better manage their data. It's been shown repeatedly that better managed data leads to speedier output of research. That is, researchers publish quicker, they publish more papers, which gets them more grant funding, which lets them publish even more. So we need to let them know that, you know what, at some point you need to manage your data properly, and naming things, for example, metadata, et cetera, et cetera. So the problem we see it is that we need to give them easier way to manage their large data set. Large data set, what means a large data set changes from research domain to research domain. We ask people, and if you ask a digital humanities person, 1 terabyte is a huge data set, whereas our astrophysics department has 20 petabytes. They think that, no, it's okay. So it doesn't matter how much data they have actually. You need to teach them, you need to show them, and you need to give them tools how to better manage their data, right? Even if you have 1 terabyte data, if it doesn't have metadata in it, you are not going to be able to manage that properly. We need to share this data. We need to make sure that it's reproducible, because one of the biggest crises in science right now is people cannot reproduce other people's research, even if they have all of their data. We need to get in front of that. Half of my job is dealing with retention compliance issues and dealing with the federal government. And we need to do this for the researchers, right? I never met a researcher who loves to do paperwork for government. And we need to tell our superiors metrics about who uses this data so we can get more funding to better build systems for our researchers. So the problem, and this is the vision we have in Harvard Data Connect. We changed it from Data Commons to Data Connect because everybody started using Data Commons name, and we didn't like that. It's a combination of services from different parts of the university. It's a combination of them with application, with tools. All of these needs to be integrated. And then we have offices at the university who does compliance, funding support. We even think that research computing should help researchers go find funding. And all of this together comes in this picture. We think that it should be service-oriented. That is, our system should have different services that can be plugged in when necessary. It needs to be modular. As you can see here, there is a lot going on in the background, but what the researcher needs to see is just one web portal, right? They need to log into one place where their data is, where they can do compute with their data, where they can search it, where they can share it, right? Because if you tell a researcher you need to go 5 different systems to do 3 things, they will not do any of that. And lastly, I wanted to show this picture of the vision that's put underneath the data lifecycle to show you that it takes a village to manage research data, right? Because for planning, you need help from, for example, libraries. Libraries are really good at user support. For compute, you need our HPC systems. For actually keeping this data when the research is done, for many purposes, we again go to libraries. Right? Libraries are really good at keeping information for a very long time. They did it with books for hundreds of years. Now they are retooling their systems to be able to keep data repositories where this research is deposited and kept for long times, right? So combination of all of these services, all of these people, and then all of these applications, right? We're going to hear from Stefano about Dataverse. Dataverse is a huge part of our vision because we need a very good data repository to keep all of this research data. And we need tools, again, we're going to hear our space, right? We need tools to be able to give researchers so they can have easy management tools for their data. Thank you.
I guess one thing to you've talked about what you're doing and what you know. I mean, part of this is we have broad community systems researchers and industry and stuff. What is it that we're not doing? What is it that you really need built from combination of industry and systems research from the MOC team? What is it that we can, there's big gaping holes in what you have?
I won't come out with the laundry list. There's lots of things that are needed, but you know, I think continued application development of platforms, right, that many researchers in many domains can leverage, that can be easily taken by facilitators and adapted for specific research use cases, right? I think those are probably the most important things going forward. And I think goes into the data too, right? Can you have common frameworks to manage data for the research community as a whole? Because right now, in the research computing space, we're chasing our tail, trying to figure out where all this data lives, right? And all of the different platforms that are storing it, some of which are no longer going to be free, and where do we put it all, right? And how do we manage that going forward? You know, to Emery's point, question, if you were asked a researcher, what is the data that you have? Most researchers don't know because they just let it collect over time, right? And so being able to better understand what data a researcher has, how it's being used, those metric types of frameworks are going to be very important going forward. So, and helps us to report up and get more funding, really is the most important thing. Hope that helps answer the question. Yeah, I can keep going. I mean, so one of the, I'd say, big impedance mismatches that we've had, you know, is the difference between research computing traditionally, you know, where you might have a compute cluster and a bunch of people get free use, and then you get buy-in if somebody has too much of it or something, versus coming from the world of cloud, I've always felt like we got to charge people for what they're actually doing, where they get out of their competitive grants and actual, rather than us deciding as an IT organization. You're now several months into kind of buying into this model now, I think, Wade, but I'm curious how you'd sort of relate that. Do you think, and actually for you, Emery, do you think that this model of figuring out how we charge people the real cost, not artificial cost, but the real cost of what things take, how important is that to what you view as the future of this? So I'll give my comments and I can hand it over to Emery. I'm a very strong believer in democratization of access to compute. And sometimes that means you have to give that away for free, or someone has to subsidize that use. We would not be where we are today if we did not have central subsidization to provide access to compute to the research community at the university. So there's always going to need to be that level. Who pays for it? That's another question, right? But yes, services do need to be paid for. They need to be written down, and they need to be put in a proposal budget so that the national funders can actually fund those activities. And what you're seeing now, right, with NIH, specifically NSF is going to follow in data management policies, is they're building these line items in where you can actually put costs to manage your storage and manage your data, which goes to Emery's point, right? So I think that is going to be important to be able to support those models that charge, but we need to be able to provide access freely to the community as well.
Thank you. Yeah, I mean, that's a great question, because at Harvard we built a highly regulated data environment, very secure. Sure, very secure. It took us 1.5 years to build. And our biggest problem right now is how are we going to charge people to pay for this, right? We had meetings after meetings for over 1 year, and right now, I think after 1 year, we are not even at the place where we started for making a decision. We are going backwards to make a decision who's going to pay for this. The problem is that, for example, when you build this, it's in cloud, right? We have certain fixed costs, right? We have people to run this, we need people to run this, we need software to put it on it, and then we have the variable cost of researcher actually using it in, charging compute. The variable costs are minuscule compared to actually running the thing, right? So I can run this without any researchers on it. It will cost as much as if I had 3 researchers on it, right? So what am I going to tell the researchers when they say, if I weren't on this, you are going to pay this still, you have to pay this to run this thing, right? So you have all these costs. So what I can pass on the researchers so that they can put on a grant is so small. When you tell that the researchers, it doesn't make sense to them, the scales. So what's remaining, I cannot charge the researcher for that because I have to pay this to run the service, even if they weren't on it. And they tell that then you need to subsidize this, right? And then I have to subsidize it with central funds plus funds from the schools. But then one school says, I have 1 researcher, and they say the school B has 5 researchers on it. Why am I paying the same subsidy as school B? So you have to deal with those issues as well. So it's a very thorny issue that we are dealing with, how to charge for this. And I mean, at the end of the day, one very good comment was that this is a federal requirement why we have to have a secure compute environment. If the government is requiring this from our researchers, why should our researchers pay for this, right? So then that's why I said at the very beginning, we are now behind the first meeting that we have to decide how we are going to charge for this. So I mean, basically, I have no idea how to charge for this.
Thank you.
Hi, so next it's me. So I've been introduced by Larry and Emre several times about a Dataverse. So one thing that Larry was mentioning in his talk is that, okay, we have a bunch of data, they're sitting there, now what we do with this data. And so the attempt that we are doing at Dataverse, like in many other platforms, is to bring actually computing close to the data, so where the data lives, in an environment which is a data repository. So just to give you an idea, for those of you who don't know Dataverse yet, so Dataverse was born as a platform for the social scientists, the few social scientists in the beginning of the 20s that want to use data, actual data, to draw some conclusion, let's say, rather than just qualitative analysis. And so it was born for the social scientists, and now, as you see, the data which is contained in Dataverse essentially goes across all disciplines, including astrophysics. And the whole idea of this repository is, of course, provide a venue for the researchers to share their data in a way that is actually discoverable, and this is the famous FAIR principle that was mentioned before, but also in a way that you can cite those data, like you cite publications. So every time you publish some data on Dataverse, you get a DOI, for example, that your work for collecting the data and sharing the data can be actually properly mentioned. So there is a network of now Dataverse, because Dataverse is an open source project. We have 115 installations that self-declared their existence to the network. There are much more out there. Just a few numbers. just to show the diversity of Dataverse. So we have, this is a small data world yet in Dataverse, but still we have 70 terabytes of data from all different types of disciplines, millions of files. And the ability of Dataverse is to make all these things discoverable and searchable and usable by the others. Just only Dataverse, Harvard Dataverse has 70K users, which deposit the data. And if you see this plot here, it's quite impressive also for us. Last year we got 53% growth in terms of number of new installation. And this is why. This is because, of course, it's an open source project, so the community grows in an endogenous way, but also because data sharing is becoming more and more important. And now we have AI, and AI is consuming lots of data. So this is the right place where you want to do some analysis. So about FAIR. So FAIR is the acronym for findable, interoperable, accessible, and reusable, meaning that there should be a standard to make this data discoverable. There should be a standard to describe the metadata from different across fields, because you want to do search across fields. And maybe using semantic types or other approaches, you want also to link data across different, say, disciplines. So there are lots of standards that we support and lots of so-called persistent identifier. Of course, you know DOI, you may know also ORCID, and so forth. So all of these can be attached to any part of your data. And then you have to ensure preservation. You need to be sure that because of interoperability, you need to be sure that you can actually retrieve this data for doing actually something on this data. And then you want to track provenance, which is very important. And Memento, I think, part of it is about provenance, and also versioning, which you expect from any repository. Okay, so that's it. But the point is that once you have this, then anyone can build their own search engine because you have very well-structured metadata. And so, for example, you go to Google datasets, and you can extract all information. You can do any type of query that you usually do on Google just for Dataverse or other repositories. You can feed Perplexity AI with Dataverse. I mean, we did nothing. They just scan Dataverse because it's fully open. You can ask open NLP questions, let's say. Or you can have repositories like DNH, which is just a portal to discover data in biomedical sciences across, say, the research spectrum. And we contribute, of course, along with other repositories. The other important thing that we support is fair posting, because it's very easy to create a crawler, but then once you have information about the crawler, you need to reverse engineer the content of the web page that you actually downloaded. So signposting is a way to inform, so there is a standard for this, is a way to inform which links corresponds to which type of content. So this link is about data, this link is about provenance, this link is about the author, and whatever. So you don't need to do this reverse engineering. And this all, of course, helps search engines to do their job. So Dataverse is not just a data repository. I like to see Dataverse as a more, I mean, as a citizen in the research data cycle plus more, in the sense that we do build services around Dataverse from, for example, you have an idea, you want to design your study, we can help you because we have experience about 1 million data sets which have been collected, and we know what you need to do when you want to create a survey, you want to collect data, and so forth. Then you use this before you start any research to see, like you search for the literature, you can search for existing data about the topic you want to explore, and so forth. So I'm not going to all the steps of these slides, but you can see secure data storage, persistent storage, all projects that are going on at Dataverse. And then there is another thing I want to highlight, is that Dataverse was born as a research data platform, but actually can be used also for administrative data. So administration produces endogenously data, and you can put them in a data lake. But then if you want to look for some administrative data, you need to ask the person to see where is this data sitting. So Dataverse can be the place or the interface between the user, which needs to use the data, and the actual data lake, whichever data lake you want to build, once you construct the metadata. So far, Dataverse, like any other repository, was about small data. Now we reach the large data, community. In a sense, we recently implemented Globus to actually manage the access to the NESI disk, so NESI disk and NESI tape for the petabyte storage. And this was part of the formerly called Harvard Data Commons, which Emre just mentioned. And essentially, Dataverse is able to, you can focus on the left-hand side, sorry, the circle here. So it can manage the access to different type of storage, in different ways. So authentication, you can control different accessibility and manage users and so forth, all within Dataverse, which talk to different protocols to the different storage types. So what I'm going to present now very quickly is that now we managed to reach the ability to compute directly on the data thanks to the MOC infrastructure. So putting together NESI and NERC, data now sits on, in this version of Dataverse, sits directly on NESI, can be NESI disk or NESI tape, and NERC can access NESI, say containers directly. And essentially, Dataverse is the interface to this data, which is stored on NESI tape or disk, and on which you can run computing without having the data flowing over the internet. So the idea is that you compute locally on your data without doing any data transfer across the internet. So this is how we configure this. We use OpenStack for the moment, or we plan to go to OpenShift. So there is a container for Dataverse. There is a Jupyter Hub containerized for running the computation. And whenever the user uploads data to Dataverse, they go either to disk or tape, according to the choice, of course. And when Dataverse sees data sitting on NESI disk, it activates the possibility to run computation on data. So we start with one real data, so we don't like just fake examples. So this is a real data set which is actually it's a big project at Harvard and NASA. And we prepared these two versions, the NESI version, sorry, the NESI tape version and the NESI disk version. So if you want to upload data into Dataverse and you want to go to either NESI disk or NESI tape, you can use the Globus. This is one of the options that you can do. So you can expect authentication. I mean, I want to skip all this part, but the idea is that you essentially start from your local, say, Globus directory space, and you move data into Dataverse the way you like. So you can organize in directories, you can assign different permissions to the files, and so forth. And then once the upload is started, Dataverse receives notification when the process is finished. Of course, for petabytes of data, it might take some time, and that's the reason why we use Globus API for this. But you can do an S3 to S3 connection if you want. So once the data are there, this little icon appears in Dataverse, and you know that these data are now on tape. If you want to access them, there is clicking there is a particular way to access tape data. So data sitting on tape. Or if you are on an NESI disk, say storage, and you have a Python notebook, for the moment only Python, but we will add R support, then immediately the assessed dataset drop-down menu will show you the compute on data option. At that point, you click on this menu, and you're sent to a Python notebook. So some magic now appears. So of course there is a way that Dataverse informed the Python notebook where to take this data from. And they are taken from an NGH PCC, of course, endpoint. And also there is another important fact that this data exists on an S3 bucket somehow. In this case, it's tape. But you need to remap correctly on the fly. The file names which have been used by the notebook, by the author, which were running this notebook on his own computer, and now you want to run it on SE disk through Dataverse. So this mapping happens completely automatically, and then you have the results. So you can do everything. So everything is seen as a local file. Files do not go across the network. I mean, they of course they are loaded just into the memory of the Jupyter notebook for this use. You can explore the data, and then eventually, if you need, you can download the data later on, and even the notebook. So this is how we implemented so far connectivity between the data and the compute in Dataverse. So because we talk about, part of the slides are not here. Anyway, so there are a few challenges which still remains in terms of how we make this model scalable more than it is now for this demo. So the first thing is that, of course, we need to ask, there are some technicalities that we need to solve. So for example, now when you spin the Jupyter container, it's just a container pre-configured. And of course, you want to allow the user to be able to choose CPU, GPU, RAM, VRAM, whatever it is needed for that particular workflow to be executed. We need to find, as Emma was saying, we need to find a way to charge user for the computing part, because apparently this is the hardest part at Harvard, asking for money to offer services. And Dataverse is an open repository. And so we need to establish this part. And this is probably where MOC can help, like an interface between the technological part, which is the infrastructure, the software part, which is us, and the researchers who want to run the analysis and need some kind of billing. And so this is where MOC probably can help us in defining both the cost model, and I agree that there should be a part which is for everyone and a part which is to be paid by who wants to use it, and also all the administrative part. And yeah, and the other thing is that the promise when you put data in Dataverse is the data remains there for a very long time, let's say, if not forever. So we need to, in the business model, we need to include also the sustainability, I mean the long-term sustainability of having the data sitting there. And this is an open problem now with big data. It was not for, say, up to two years ago, but now it's becoming a real problem for every repository. And that's it. So thank you very much. I also had some AI thing, but it didn't flow into the slides, so I don't know why.
Thanks for the talk, and it seems like a really pragmatic thing to do to make it so easy to get at the data. I just had a very minor question about it. What if you were trying to research 2 data sets at the same time? Is it easy to sort of spin up an environment that contains both for you to sort of join them together?
Yeah, that's a good point. It's a good idea and a good point. So in this demo, we didn't do this, but in practice, yes, it is possible. It is even possible, I think, in the future to, I mean, the way we built this interaction is totally agnostic to the computing part of it. So you can actually spin the container somewhere else, and in that case, you have to move the data. So yes, this kind of possibility is still available.
So you had the word providence in there, and I think I know some of the stuff you may be talking about the future, but is there a notion today, and how do you capture that providence today if you do?
The provenance, I mean, when you create, this is specific to Dataverse. So when you create a data in Dataverse, you have to specify the provenance. So there is no way you can publish data until you fill up a certain number of metadata fields. And one of these is the provenance. Then you have licensing, you have all this stuff.
I see, so it's what a user specifies. There's no automatic collection of provenance. I mean, so if you do what you're talking about here with having compute that can then, say, mutate and create new data sets, do you view that as something you could automatically capture?
It is possible. It is possible. I mean, technically it is possible the way Dataverse is built. Now, when you publish the data, you are the owner of the data, and you have to decide whether you want this to happen to your data or not. And what happens in Dataverse, every time you you change one number into a data set, you have a new version, and this is done automatically. So all the metadata are automatically updated whenever you touch anything in your data set. So there is a collection in Dataverse which actually update the data, I think every month. So they use the same collection. Some external process update the data, and so this information is automatically captured by Dataverse. So the new version of the data is kept. Yeah.
So maybe I missed it, but how do you deal with data that not comes once a month, but comes once an hour or once a day, right? Is that a new data set? It's the same data set? I mean,
it's up to you to decide whether a new release is a new data set or it's a new release of the same data set.
But you're appending, right?
Sorry?
You're appending all the time.
Yeah.
Right. So every append could be a different data set, but if it's the same data set, it's a different version. How do you deal with appends?
So, for example, the GeoScam group is doing something like this, but on a yearly basis. So they update petabytes of data, and they essentially recalculate all the benchmark data every year. It's the same data, but it's updated with new information. So it's retuned, let's say. And in that case, they want to release as new data. So it's a new data set. In some other cases, you can just update the version.
I guess one more question, so you said there's hundreds of Dataverse instances around the world, and they're sharing information about which data sets they all collect. So if I'm sitting on the MOC and I want to access a data set, it'll identify, say, that data set exists in a Dataverse in Ireland or something.
Yeah.
It seems like there's a natural mapping to say that if I discover it that way, and other people are computing on that same data set, say in the NERC environment, I should be able to identify, instead of fetching it again, I should be able to get a cached version, for example, in an environment. Is that consistent with your?
This is up to each installation to activate a cache or not. It is possible. So when you search within Dataverse, you can get metadata information about some data set which is in Ireland, for example. Then if you want to access the data, you have to download the data. And of course, if another user do the same thing, you have to re-download the data. But unless the installation in Ireland creates some kind of caching system, which is possible to activate, in this case, you don't.
Well, I'm more thinking that
I think I understand what you say, but it's not yet what you expect it to be.
Yeah, I mean, if we can identify the name of the object being something, it's hash or something, we can incorporate, like there's community cache you'll hear about later on.
Yeah.
It feels like we could sort of look it up to see if we already have that thing.
You can, because every file every single file is hashed. So you have this information. This is stored, and you can retrieve this information. You can check whether you already got this data or not, existing in your data lake, whatever. Yeah, this is possible. Yeah.
Hi, folks. I did have a couple of people ask me, all of these sessions are all being recorded, and they're going to be available on our YouTube channel, which will have links from our event page. And the slides that are here will also be available on our event page. So just keep that in mind as we go forward. We always can go back and learn some more. We will be approaching our break right now. We'll have a short break, and if you could come back at 3:40 as we continue our afternoon session. Thank you. Oh, and Aiden Jackson. Alden Jackson. Will you please come up to the front for a minute? Just have a quick question for you. Thank you.
to get my slides up, maybe?
Yep.
Fantastic.
Here we go.
Oh, wonderful. Perfect. Thank you.
Correct. You can.
And which way is it? This one?
So this one.
This
yep.
one. Okay.
And then if you want a handheld mic, just.
All right.
we have it
Thanks.
for you. And then, do you have speaker notes, or you're just going to be looking
No, I
at
don't.
your
Speaker notes.
Okay.
Fine, thanks.
Is that big enough? or-
Actually, can you make it bigger? It doesn't matter, but I might look at the screen. Okay,
Is that
thanks.
good? Okay.
Yep.
Great. And then I think, Nancy, do you want that to handhold just for a second?
Hi.
Just pull everyone in. Yeah.
Okay, folks, we're going to start the last half of our session here for this afternoon, and we're going to start with Rory McNeil. Thank you.
Thanks, Nancy. I'll just wait until everybody sits down and it's quiet, if that's okay. So, hi everyone. This is quite exciting for me. I stood here literally 4 years ago to this day and made a similar suggestion as I'm going to make, and I don't think I really understood what I was talking about, and I'm absolutely confident nobody else in the room did. And I think 4 years on, we might be able to talk together. So this is really exciting. So let me explain. I'm Rory McNeil from ResearchSpace, which produces a product which is a digital research platform called RSpace, which I'll talk about briefly later on. And I'm based in Scotland. So I'm kind of have two differentiators, I think, from most of the people here. First of all, I'm coming from a European perspective, which I hope will be interesting. And secondly, building on some of the earlier Larry's comments and others, I'm a data guy, not a compute guy. And I'm kind of here, I think, as an ambassador to some extent for both Europe and for data. So let's see if we can engage here. So the title of my talk is about research commons, which is a concept which has been mentioned earlier, the Norwegian research commons in particular, as a possible model for NERC. So that's kind of the way I'll get started. So I'm going to talk about, this is just a summary. First of all, what are research commons? It's already been touched on today. Then there's a new important global open research commons international model on which the proposed Norwegian research commons is based. And then I'm going to raise the question, could NERC be a research commons? And then I'm going to move on to talk about Dataverse, which you've already heard about extensively, and RSpace as a potential core of a NERC research commons. And then just briefly at the end mention federation possibilities, which is also very important. So again, I think this is how data people think about the world. It's the research, just ignore the thing on the left, it's the research data lifecycle. And that's how non-compute people, if you will, the long tail of I think, many disciplines of researchers as well as research data managers think about things in terms of this data lifecycle. So what's the problem? And this is actually, thanks to Emre and Scott, this is really stealing what they said. So the lack of data-centric tools and the lack of interoperability between tools leads to siloed data, which impedes the FAIR principles, which we've heard about, and also creates friction for researchers. So again, with apologies to Scott, who unfortunately, as you heard, is not well and couldn't be here today, but and they used to call this at Harvard a research commons. Maybe the name is changing, but the concept is still the same. So what did Scott say? He said we need to bring together data with cloud computing infrastructure and commonly used software, services, and applications, and that's what I'm going to be talking about, for managing, analyzing, and sharing data to create an interoperable resource for a research community. I think that actually expresses it really nicely. So who's going to provide research commons? Well, universities, we've already heard about Harvard, but also, and this is what I'm going to be talking about today, national organizations like Canada's National Digital Research Alliance, and indeed in Europe's European-wide supranational organizations like in the European Open Science Cloud, the EUDAT Collaborative Data Infrastructure. So there was a really important development which is actually stimulating a huge amount of energy and activity. Whoops, it looks as if that got a bit crushed. But anyway, the Global Open Research Commons International Model is a model which was developed by the Research Data Alliance. I realize many of you here probably aren't familiar with the Research Data Alliance, but for those in the data world, it's the most important kind of source of innovation and ideas for people involved in research data management. So it's an important body. And there was a working group there that released something called the Global Open Research Commons International Model last November. And as you can see from the slide here, there's 9 elements to this model. And the most important one is actually services and tools, which is kind of the technical core of it. But it also involves other things, and it involves compute. So the things in blue are kind of the technical underpinning, if you will. But it also involves the things in white, human capacity, which we've heard a little bit about, as well as things like governance, engagement, and sustainability. So this is just a graphic, but it's supported by a few hundred pages of detail. And it's intended to be a model or a guideline for Research Commons. So I'm going to talk a bit about the proposed Norwegian Research Commons, which I was involved in developing. But there was a meeting last week of this working group, and it was really amazing. I mean, I would say virtually every country in Europe is thinking about developing a Research Commons, actively thinking about it, and using this model as a reference. So I think it's very significant. And not just countries, but Elixir, which is the Europe-wide life sciences research infrastructure, which has had billions of euros of investment, is also looking at it, and again, using this model. So it's very much the topic of the day, I would say. So let me talk now a little bit about the proposed Norwegian Research Commons. So this is an interesting one. Actually, it was invented right here in Boston, in a way, because it started out as a proposal to the Norwegian government, which provides funding for research infrastructure, and Dataverse NO, Dataverse Norway, was going to put in a proposal to basically upgrade Dataverse. And because we work closely with Dataverse, I was involved a little bit, and I said, hey, this isn't really very exciting. Are you really think the Norwegian government's going to give you 12 million euros to upgrade Dataverse? Maybe not. Why don't we propose a Research Commons for Norway? And by the way, this new model exists. So that was really the origin of what became the proposed Norwegian Research Commons, which has been called Reason. And this was built, the technical core is built around a few components which will be familiar to people here, or to some people here anyway, because it's basically Dataverse, iRods, and RSpace, which already have a lot of integrations which allow good flows of data. And the proposal is to, in effect, work on further integrations, further upgrades to the integrations between these existing tools and services, and then also integrate them, again, relevant to our talk today, integrate them with the existing Norwegian underlying storage and compute infrastructure. And I don't know if you can see, I think you can see it fairly well. So you can see from this, from the graphic, you got the underlying infrastructure at the bottom, and then you come back to the research data lifecycle, the way that research data managers think of these things. So you have a planning phase, collect and process, share and reuse, and then publish. And you can see some of the tools which are proposed to be involved in this. So I think the last part of this got cut off at the bottom, but the objective is to create an integrated infrastructure that facilitates streamlined flows of data and metadata. Well, to me, that's very reminiscent of Scott's definition of what a research commons should do. So this wasn't directly inspired by Scott's articulation, but I think it's actually very close to it. So could Reason be a model for other research commons? Well, I think there's actually, it has a lot going for it in that respect. First of all, it's the first attempt to walk the walk as well as talk the talk of the GORC international model. So it actually, it's several hundred pages of detail around that graphic. It's got a number of, I think, very strong elements. It comprehensively uses all of the GORC elements, so all of the 9 elements are described in this proposal. It's not just the technical core. But it has, as you can see from the graphic, it has a detailed instantiation of the services and tools elements of the GORC model. So we're not just talking fluff here, we're talking about actually very specific set of tools and services and how they can be built and how they can interoperate. It's built around a group of complementary generalist tools, and I'm thinking in particular of RSpace and Dataverse and iRods, that are all designed to enhance verification of data. The focus is on interoperability of tools, data, and metadata. And it recognizes the challenges and the need to interoperate with existing generalist and domain-specific research infrastructure, including storage and compute. So I think all of these elements make Reason a good reference, let's say. I wouldn't say it's a model, but I think it's a good reference for others who are thinking about building research commons. And in fact, when we had this meeting last week, and there were people there from Sweden and the Netherlands and Germany who were also thinking about putting together research commons, and I think they found the detail that we were able to provide when we described Reason extremely useful. So that's the beginning. And then since then, we've had conversations with, again, a UK initiative. It's called BioFair, which is the Elixir, the life sciences, the UK node of this European life sciences research infrastructure. And yes, they're thinking about producing a research commons called BioFair. And yes, now they're interested in using Reason as a reference as well. So, okay, how about NERC? Could NERC become a research commons? Well, here's the graphic you've seen before. This was this is on my presentation 4 years ago. And again, it was, to be fair, it was, if anyone remembers, it was literally the beginning of COVID, so things kind of died down after that. But I really don't think, NERC wasn't ready for this 4 years ago. RSpace certainly wasn't ready for it. I don't think Dataverse was either, so it was premature. But my question today is, well, maybe the time has come to think about it again. So let me talk more specifically about Dataverse and RSpace as initial core elements of a NERC research commons. You've already heard Stefano describe Dataverse in general terms, as well as talking in particular about the compute work that's been done on Dataverse. So again, just to kind of repeat, Dataverse is a generalist data repository. Its two great strengths are the fact that it's supported by Harvard, it has always been actively supported by Harvard, and there's a vibrant global community that works with and develops Dataverse. It's one of the recognized generalist research repositories, and GRAY is an initiative of the NIH to try to help the generalist research repositories to co-opetition, as it's called, to improve each other, but also to compete. And finally, as you saw from Stefano's presentation, Dataverse is also cognizant of the importance of having good support integration with compute. So that's Dataverse. So RSpace, which is my story, RSpace started out life, and again, I realize this may not be familiar to all the people in the room, but as what was called an electronic lab notebook. So somewhere where life scientists and other researchers who used to use paper lab notebooks could transition to digital note-taking. Over the years, it's evolved. It now includes a very modern and sophisticated physical sample management system. so you can manage your physical samples as well as your experimental data together. And it's got, in a way, the ecosystem has overtaken the tool. So really RSpace, it's not really RSpace, it's the RSpace ecosystem now. So we have done integrations with, I think, more than 20 different tools now to support this flow from preparation to active research to storage and reuse of data. And the blue ones are kind of the research integrations, if you will, research integrations with the ability to integrate with storage, the ability to integrate with specific tools which are used in particular workflows like animal colony management systems, equipment scheduling systems, protocols I/O, et cetera. And then, as well as Omiro, which is a open microscopy environment, which is widely used by many scientists everywhere. And then the ones in purple are kind of a research data management flow. So we integrate with data management plans and also data repositories. So data can be exported from RSpace to Dataverse and other repositories, and then it can be made available for reuse in the way that Stefano was describing. We also integrate with data management plans, which can be incorporated into RSpace, associated with the data that's actually produced in the active phase of research, which is where RSpace comes in, and then exported to Dataverse and other repositories at the end of the cycle. So it's a research and a research data management platform. It's kind of where research meets research data management. And of all the integrations we've done, the one with Dataverse is the most, I would say, the most intensive. And it's also the one that we are probably see the most promise in, and we are continuing to work on. I'm going to the Dataverse community meeting from here next week in Mexico City, looking forward to that. But again, don't know how well you can read that, but we've got the, I mentioned the DMP integration, mentioned a few other things. So you can export data from RSpace to Dataverse, and you can also associate persistent identifiers in RSpace, which are then passed on along with the data into Dataverse. So you can export metadata about the data from RSpace into the Dataverse metadata categories. And if you associate a controlled vocabulary from a particular domain, that could be associated with the data set in RSpace. And that could also then be, when the data is passed on to Dataverse, that controlled vocabulary information also gets passed to Dataverse. And we're looking at additional enhancements to the integration as well. So here we go now. If NERC wants to think about developing a research commons, I think Dataverse and RSpace could be the core of it, and that could happen pretty easily. So it doesn't need the full panoply of services in Reason just to get started. And here's what it might look like. So I've just put the you can see here the kind of all the things, but let's just concentrate on RSpace and Dataverse. And instead of the Norwegian research infrastructure beneath it, you have the NERC infrastructure and what lies beneath MERC. And I have some exciting news, thanks to Aran. And we didn't quite make it. We're not quite there, but I think we're about 2 days away from having RSpace being deployed on the NERC. So that's a nice development, and I think that will stimulate some further activity. So finally, there's been some talk of federation, and it's clearly an important issue. And given all the activity that's going on in Europe, in Australia, in Canada, around research commons, I just raised the thought that having a research commons element to NERC might be a good trigger or a good handle for starting conversations about federations with some of these other initiatives which are developing. And lastly, thank you very much. So this is here in case anyone's interested in learning more about Research Commons or the GORC International Model or Reason. I've put some links. Thank you.
I guess I'll ask a question. So I'm just trying to get my head around it. I don't really fully understand the relationship between Dataverse and iRods. I don't quite understand, because they seem to have some overlap, and I'm not sure. Can you sort of give a thumbnail description of the difference? What each one does that the other doesn't?
Well, I think they're quite different. Dataverse is a repository, and iRods is a policy management system. Or a virtual file system. iRods is like Starfish, if you're familiar with Starfish. I don't know if you're familiar with Starfish, but so in the RSpace context, we currently use iRods. So if you link from, you can make a link between an external file store and RSpace, but if the location of the file moves, the link breaks. So we put our iRods in the middle, and it tracks the files. So you solve the broken links problem. The second thing we're working on at the moment is exporting data from RSpace to iRods, so it's going the other way. And then you have, if iRods is able to see a huge pool of data, then you can, and again, because you have metadata associated with the data, when the data goes into iRods, for example, if this is one of the aspects of the Reason proposal, data could also be exported from Dataverse to iRods. And then you have a larger pool of data which would be discoverable, and you could make associations.
Okay. So I just get confused because there's so many layers in some sense. We have the, from the Dataverse to iRods to the S3 layer underneath these things. It feels like we're introducing a lot of layers, but I think I understand. So just going to another thing is that there's clouds. If you look at Amazon, there's Amazon's cloud. It offers, it says services, period. When people talk about federation, they often talk about distinct academic clouds that provide some degree of federation, some set of rules between them. If I have to look at the ultimate, if we were successful with where we're trying to go with NERC and MOC, is not really about federation. Federation kind of implies possibly multiple clouds that then have some rules of association between them. We kind of like to create a collaborative cloud, a cloud where there are, where we actually can hit the scale by having entities like, the group controlling NERC. We add more people to them as more institutions become involved, but it's one service scaling to more data centers as this goes. So creating a Uber cloud, which is a collaboration between research rather than a whole bunch of distinct clouds that federate. And I'm trying to get my head about if that model is successful, what does that mean for this? Like if we're successful in creating a research cloud where institutions around the world are collaborating in that research cloud rather than a cloud that's federated with other research clouds, does that mean that the data commons is the world's research data commons? Or would there be many instances of it, say, for different curated data by different entities?
Well, certainly in Europe, you could run, it's not going to work at all because of the data sovereignty is one of the primary driving issues in Europe. So they would never have their data be on a cloud which is outside of Europe.
Well, so, no, I mean, we're talking with our Irish colleague over there about having another data center in Ireland that was, we would be having services where we're working together. And clearly there's regulations around data, both compliance and of course, things like that. But if we could span this thing, if it could grow to be a collaboration between many research organizations to create a larger research cloud, with, of course, there would be rules about where data had to live inside that thing. Should I just think about this as a data commons for the research community, or?
Well, that would be ideal. As I say, I think there could be a lot of regulatory as well as technical issues to to achieving that. But in the US, it would be a lot simpler to start with the US in that case, because you don't have the data sovereignty issues.
Apologize for missing part of that, but effectively, doesn't some of the technology you're describing, IRODs in particular, probably help solve this problem for a federated data community that has where some data has to be resident in a certain location, but individuals can be authenticated to access it, or groups in a secure manner, wherever it is?
Yeah, I think that's the approach. Absolutely. Yeah.
So what's the next step? I mean, it's a really cool idea. I think that if you look at some of our colleagues that were discussing AI, if we were hosting a massive amount of data from the research community, I think that would be an incredibly powerful thing for it. Where do we go from here?
Well, I don't think I should be advising you on that. But I think I was just chatting with someone from Dataverse this morning. I mean, on the RSpace Dataverse, I think what would be nice if we have ParSpace and Dataverse, which are already integrated, up on the NERC, which will be happening soon, that can then be a showcase or a window for people to discover that and to begin to use it and to explore possibilities. So that's a start. As to the broader kind of where you want to take NERC and the MOC, I don't really think I'm well placed to advise on that.
If one wants to create critical mass of a data commons, one can we've got those elements in place, and maybe it'll just grow organically to that. There's also representatives of the Commonwealth here. Is there something we should be applying for or doing to sort of get this thing to grow?
Well, absolutely. I mean, we could talk about that maybe. If you look at Reason is it's to get funding. It's to make all these workflows more seamless, to make them add value, to make it easier for researchers to do more things with all the things that we're discussing, and that takes resources. And so Reason is one way to do that. And we don't even know if we'll get the grant until the end of the year. But absolutely, why don't we talk about applying for some funding to do some of the specific things that we would like to do, and also that was in a different context as well, so there could be some different things. So absolutely.
Do you have the clicker? Or is that? Okay, thank you. All right, hello everyone. My name is Mark Roth, and since I work for a high-tech investment manager, I'm obligated to tell you not to listen to me about anything that's financially related advice, so don't take anything I'm about to say as solicitation or anything to go invest. All right, so J.R.R. Tolkien wrote The Lord of the Rings, and in that novel, he created a creature called an Ent. He's actually a linguist, and he loves creating languages. If you look at his works, he's created, I think, 2 different languages for elves. He's created languages for dwarves, and the Ents actually had their own language called Old Entish. And this language was very peculiar in that the names of things in that language refer to their full story of how they came to be. And because of the deep lineage of these creatures, saying the name of one of these creatures could take you several minutes. And when you hear that name, though, you know exactly who it is you're talking about. There's no ambiguity. And so the Ents would say, don't be hasty. It led me to wonder, what if we actually used Old Entish names to talk about our data sets? Would that kind of built-in provenance about the name of the data set make it so that it would be more likely we could reproduce research? Let's find out. So Memento was created by 2 Sigma as a way for remote researchers who were helping us to submit their data pipelines. And Memento is not so much an implementation as it is an idea. It's a set of ideas about how to organize your research. And when you use Memento, you get a few things out of it. First of all, you get the ability to more accurately maintain and communicate provenance about your data. You get better reproducibility for your data sets, so it makes it easier for someone else to continue your research from where you left off. And you get better ergonomics. So it's possible to make more efficient use of your time, and also to reduce the amount of cost that you have in paying for your research, because you never have to compute the same data twice. Now, I'll make a claim that on some level, these 3 things, provenance, reproducibility, and caching, actually all have to do with naming. And I'll explain why in the following slides. But first, it takes me to my first point, which is that naming is hard. It's a hard problem. In fact, most of us know that there are only 2 hard things in computer science: cache invalidation and naming things, and off by 1 errors. And Memento helps with 2 out of the 3. So to describe Memento, it helps to look at it in the context of a realistic research problem. In 2013, New York City created or launched its bike sharing program called City Bike, which is now the nation's largest bike sharing program and an essential part of New York City's transportation infrastructure at this point. Those who are Bostonites will point out that, yeah, but we had it first with Blue Bikes coming out in 2011, which is not the nation's largest, but still a very important part of Boston's transportation infrastructure. But you may ask yourself the question, are these bike sharing programs equitable? And to answer that question, you might, if you want to do it scientifically, you might start with a hypothesis, which might be zip codes in New York City with higher median incomes show higher city bike usage. And you could then prove or disprove this hypothesis by starting with the data and then forming a data pipeline and doing your research. So let's take a look at what a data pipeline might look like for this hypothetical research scenario and see how Memento would apply to it. But first, let's start at the end of the data set. Imagine that you have a paper talking about or discussing this hypothesis, and it's accompanied by a data set. And you take a look at the data set, and it's a data set called 2020.csv. The name of that data set isn't very helpful by itself. Now, you might open it up and look at the column names, and if you're lucky, maybe it's in Dataverse or something, and you can get some additional information about provenance and things like that. But if you're tasked to continue this research, to sort of pick up where it left off, you're going to need more than that metadata, and you're going to have a bunch of questions. First of all, you might ask, what are the original data sources? What methodology was used to process this? Where are the intermediate artifacts, not just the final one, but all the ones that led up to it? Can I reproduce this data? And how am I going to generate data for 2021? So let's take a look at the pipeline step by step. And I'm going to ask some naming questions along the way. First, we start with the raw data. So if you're looking at city bike data, it exists in an Amazon S3 bucket called trip data. Now, first of all, I think this is a little bit presumptuous of City Bike to grab the name trip data, as S3's namespace is global. So they're basically claiming the name, saying, we are the world's providers of trip data. But let's take a look to see if we can do a little better with the naming in our own pipeline. I'm going to do a quick audience poll here. I'm going to give you 3 names for ingesting the City Bike data. So the first one might be more technology-centric, like ingest S3. You pass a URI and a path regex. Second one might be pipeline-specific. So we're going to say, step 1, ingest data. And the third one might be more dataset-centric, ingest City Bike. So how many of you here would choose A as your name? How about B? Okay, and how about C? Wow, a lot of C's. How about it depends? Yeah, of course, yeah. So it does kind of depend, right? And, but I'm actually pleasantly surprised to see lots of people. I think this audience really understands the importance of naming. If we name it based on the data set, there's some advantages, but of course there are some trade-offs as well. I'm going to pick C as well. That's the one I decided to pick. We have to name the CSV files as well, which is a challenge in and of itself. Actually, the raw data set files as well, which is a challenge in and of itself. And now we're going to go to the next step where we're going to process the data and turn it into just raw structured columns. They're not raw, but structured columns. They're taking the raw data, turning it to structured columns. So I'm not going to poll you this time, don't worry, but we have 3 other possible names here. And the point that I'm really making is that as you're building this pipeline, there's lots of things going through your head as a researcher, like what am I going to name this? How am I organizing my research? And one thing that we noticed when we were building Memento is that researchers who are better organized in how they name things in their notebooks and how they organize their research tend to produce results that we were much more easily able to reproduce in 2 Sigma. So in this case, I'm going to pick C again. And we've got a couple of CSV files here. And what I want you to notice is that in this particular workflow, I'm not saying that they're all like this, but as the pipeline progresses, the naming actually gets less and less informative. Even though we're making an intentional decision here to try to capture things, we're choosing C every time, the data sets are becoming less and less informative in their name. And this is especially so in the last step, where we're joining these 2 data sets together. And the only thing they really have in common is that they're both for 2020. So whoever wrote this pipeline wasn't even trying, and they just named the last stage 2020.csv. This is inspired by a real-world example, but it wasn't exactly the same. Okay, but let's take a look at the pipeline as a whole, and you can see that 2020.csv doesn't tell you nearly anything about the rich history of what went into this data set. And this is a very simple pipeline. Pipelines can get much, much more complex than this. Now, of course, once the pipeline is done, we're done, right? There's nothing to worry about. Well, we all know that's not true because the only constant is change. So what if IRS.gov, in this case, where we're getting our median incomes, they decide to issue a correction to the data? How do we know whether 2020.csv has incorporated that correction or not? What about if we fix the normalization logic at one of the stages? Or we have a new tolerance parameter. I mean, the name is in the CSV, but why not the tolerance parameter? What if I chose 3 different values of the tolerance parameter? Which one did I end up publishing with? What if there's a new file format upstream? Or what if one of the stages was run on an AMD machine instead of Intel, and that produced quantitative differences in our pipeline? All these kinds of questions are not captured at all by the name. So there's got to be a better way, and I think that our friends, the Ents, might be onto something here. So I've been at 2 Sigma a long time, and I've had a chance to see a lot of different clever research hacks, I'll call them. And one day I saw a request come in. I was managing a storage system, and they said, can we increase the length of the column names in the file? And I said, why? 256 characters should be enough for anyone. But then when I sat down with the researcher to see what they were doing, I was shocked. They had a column name that looked something like this. Imagine this was a column name and not a CSV name, but the same idea. But as I sat down with them, it started to make more and more sense, because what they had done is devised sort of an RPN-style naming scheme where every single stage of their pipeline was captured in the name of the data set. If you wanted to know whether this data set was used with a 0.7 tolerance join parameter, it's right there. There's no guessing, there's no ambiguity. So I would call this sort of the Entish name for their data set, if you will. But I don't see many people doing this. Why? Well, it's not very practical, is it? It's like kind of difficult to write this way. But I'd say that this researcher, and Ents in fact, would have saved themselves a lot of time if they knew about hashing. And so let's talk about Memento's approach. So Memento does this in a little different way, as you might guess. But what's interesting is that Memento doesn't have you deal with data sets at all. The philosophy of Memento is that the function is the data. In other words, the computation that you provided that you did on the data represents the data itself. This is a very functional approach. So if you want to know where is the data set with the 0.7 tolerance join parameter, just call the function again with 0.7 as the tolerance parameter. If it was ever computed before, you get the answer immediately. If it wasn't computed, it's going to go off and compute it with that tolerance parameter, and now it's available for anyone in the world, or in your team at least, to be able to see the results of that computation. Now, the name join city bike wealth is actually just a symbolic name. It's not a real name. The true entish name for this data set is its hash. But we all know that hashes are a one-way function. So if we use this hash as the name, how do you know what actually happened? Well, what we do is that every time you call one of these functions, you get a keepsake, or a memento, if you will, of what the value of what were all the criteria that went into that calculation at that time. So let's take a look at how the memento approach would work for this pipeline. We start by just basically nixing out all the data sets. We don't really need them anymore. In fact, they're kind of a liability. As soon as you serialize the data to disk in that way, they can get out of sync with your pipeline. So we take them out. And it already simplifies the pipeline quite a bit. Then we have durable storage to worry about. This is something I didn't really talk about before, but when we ingest the data, when we pull in data from S3, from wherever its raw source is, you don't know as a researcher whether that source is going to be there forever. You don't know the durability of that data. And so I would argue that as we publish research papers, it's important not just to include the names of the data sets, of the final, it's important not to just to include the last stage of the data set, but also any of the raw data sets you consumed as part of your research should be made available with your research paper, just in case those data sets disappear. So Memento does this for you. Whenever you ingest data, it gets copied to durable storage. The other thing that Memento does is it hashes all of the code in your pipeline. It assigns hashes to these things in such a way that whenever you change the function, you automatically get a new hash for that function, meaning if you change the source code for that function. It also changes the hash of anything downstream that consumes that data automatically, because this joining function will produce different results if one of its dependencies produce different results. Now, when you actually go to call the stack of functions, the other thing we hash is the runtime environments, just in case the architecture changed. So if you go to join this data in the end, if you want to call the join function in the end, what you end up with edges, which are actually the calls to these functions. And these edges are also given a hash. And it's these edges that are actually the true entish name of the data set, because it contains the bound parameters in them as well. And these are the things that the mementos are generated from. Let's take a look at what goes inside of a memento. So the memento is effectively a document, and it contains metadata, including the time of invocation, the runtime, who ran it, the lineage. It also includes the inputs, so the version of the function, the parameter map, the dependency set, runtime environment, and the outputs. Not the output itself, but a hash, a link to the output. The output wouldn't fit in the little box. These mementos can actually be signed, giving them integrity, so that you know who performed the computation. And in fact, because it refers to all of the dependencies, you can construct a signature chain all the way back to the original raw data source. So now that we looked at this, let's take a quick look at what Memento can do for you. So as I mentioned, all these things are really about naming. So provenance, I would claim, is about naming. To understand provenance, we want to know what raw data was used, when was it ingested, which parties were involved in the ingestion, what was the methodology. And it turns out that all these things are actually accurately named by Memento. Mementos provide high fidelity end-to-end provenance by capturing all the information about what would make provenance different. And I'll point out here that Memento is not just an implementation. The idea translates beyond its current implementation. We can consider this as a standard. And I dream of a day where whenever you request a data set, you also want to know the memento that comes with the data set so that you understand where it came from. And in fact, because you can adopt this to multiple frameworks, this can really be done in a hybrid way, where you might have different stages of your pipeline using different technology stacks, but you can still have one chain all the way back to its raw data source. Reproducibility is also about naming. So to reproduce data, you need all these things to be accounted for. The only thing that Memento doesn't handle here is the use of non-deterministic libraries or hardware, but it does give you some tools to deal with that. So Memento accurately names all the things that are involved in reproducibility, and it records everything you need to know to reproduce research. And the results can be signed and validated by third parties. But what's interesting is that it doesn't stop there. There's more. It provides some ergonomic advantages and economic advantages as well. You can relax and make good use of your researcher time by just writing the functions, and Memento will take care of the serialization, the storage, the naming, the true naming of all this information, and keep your research organized. It also allows you to, whenever your kernel restarts, to continue your research from where you left off. You don't have to worry about which cells to re-execute and which files to sort of
Check, check. 1, 2, 3, 4, 5. There you go.
Bring it down
Yeah.
to be safe. But
We have microphones, but they're purely for the recording. So please, close your comments better. Mark, sorry for the delay, but
No problem. Can everyone hear me in the back? Am I speaking loud enough? If you can hear me in the back, just raise your hand. Okay, great. I'll use my teacher voice even though I'm not a teacher. I come from a family of teachers. So, okay. So I guess nobody will forget this talk. Apologies. Yes, you'll all have a little memento keepsake of this talk in your eardrums. So thank you so much for bearing with the AV issues, and I've only got a few more slides, and then I'll take some questions. But as I was saying, so Memento gives us several ergonomic and economic advantages. So first of all, Memento helps you be more productive by keeping you organized. And you can just relax, sit back, and write some functions, and Memento will take care of serialization, it will take care of organizing your artifacts, and it will also ensure that when you restart your notebook kernel, it will automatically restart your research from where you left off. So you don't have to worry about which cells to execute, how to store your data in files and kind of read them. At least when I've done research, that's been always a point of like just organization overhead, right? So the interesting thing here is that Memento, in order to cache things, you need to invalidate your cache. And if you remember, caching is the other hard problem in computer science. And that's because of cache invalidation. You don't know when you need to invalidate your cache. But if you think about when you need to invalidate your cache, it's whenever the code changes, whenever the parameters change, whenever the dependencies change. And if these things sound familiar, these are all the things that go into the entish name of your data set. And so what we can do is anytime the data set hash changes, that becomes a new cache key. So the surprise here is that Memento already tracks all these things in the invocation hash, making it possible to do high fidelity automatic caching. And the caches, the other nice surprise is that you can share those caches with your team members, or in fact, if you put it in distributed storage, maybe even beyond. Imagine a world where anyone in the world can sort of reshare your data as long as they get to the same invocation hash. So let's take a quick look at how caching works in Memento, and then I'll close with some final thoughts. Imagine you have a function invocation with some arguments that produces a result. Well, we can start by taking the result and computing a hash on the contents of the result itself. We can take that hash and the results and place it into an output cache. So if you look, and this is content addressable storage. So if any two functions are invoked with the same parameters, you get the same result hash, and therefore you don't need to reuse the storage twice. You can actually use the same block of storage. Then we can take the source code for the function, the arguments themselves, compute hashes on those, and put them into what we call an invocation hash. That invocation hash gets packaged in the Memento, along with metadata, and then in addition to the metadata, a pointer to the result. The pointer to result is just the result hash itself. And so now you take all these things and you place them in a federated catalog of some sort, and you can imagine several catalogs that would be possible to store these kinds of mementos, maybe one day Dataverse or something else. But all you need to do is store that memento in the catalog, and the invocation hash can be computed by someone in the future who happens to try to want to compute the same function with the same arguments. They'll arrive at the same invocation hash, and therefore they'll be able to find the memento in the catalog and use that to look up the result. So this is how caching works in Memento. All right, so I've talked about Memento and how it works, and so let's take a look at some next steps. First of all, I'm pleased to announce that thanks to this conference, I finally got the approval to make Memento open source, which I'm very happy about. Thank you, thank you. And so anyone in the world today can do pip install 2sigma.memento, and you can go to github.com/2sigma/memento to see the source code and to contribute to the project. The project right now is an implementation of Memento, but we think it can go much, much further than where it is today. We think that there's potential here for it not just to be a Python implementation that works well with pandas and Jupyter notebooks and as standalone Python scripts, but to really extend it beyond that. So Larry and I are collaborating right now in a white paper that talks about the standard of Memento and how we can extend it beyond its implementation. And that opens up a whole set of research areas around this technology. So first of all, the implementation itself can be caught up with the ideas in the white paper. So this includes things like context parameters and durable storage and signature chains. Not all those things are in the current implementation, but we believe they can be added by a collaboration with other developers. In addition, we can develop new distributed compute and storage plugins for major cloud providers to make it so that your storage doesn't just go to your local disk, but it can go to S3 buckets and to other stores automatically. Then there's this idea of what if we go to major cloud providers that provide data warehouse technology, like BigQuery, for example, and see if they'd be willing to create mementos. Every time you create a new table in BigQuery, maybe you can get a memento alongside of it. That would be a really interesting area of research as well. We haven't done any cache replacement policies, so today these caches just build up and up and up. But garbage collection and replacement policies would be an interesting direction. And then more language bindings. So Java, Julia, Rust, R, you can imagine lots of technologies that could use the same standard. And then finally, there's this area that I think is really interesting. We've started to create some proof of concept around this. But the idea of creating a functions as a service that's memento aware, so that when you run a compute, it's not just about an RPC call to some code, but the functions as a service is actually aware that you've called this function before, or someone else has with the same parameters. And so I can give you the answer, a pointer to the answer immediately. So doing this would require an investment in doing better monitoring metrics and management to make it more production grade, containerization of functions to make sure that they're really reproducible. They grab in all of their environment. And it also opens up this idea of something that I'm calling the federated web of data, which is if you could take a bunch of these memento servers, functions as a service, and federate them around, you can imagine almost a World Wide Web style web of data where it's not just that you have data at rest, but you actually have live compute attached to the data, and you can end up hosting all of that live compute to go with the data. So lots more potential here. I'm really looking forward to collaborating with people here and elsewhere on Memento. I thank you for your time and your patience with the AV issues that we had, especially, and I would love to answer some questions. And I think even though the mics are not on in this room, we still would like people to use the mics for questions for the AV feed, for the live stream.
So one thing you showed me a long time ago with this system, before it was open source, is that you could automatically return back the provenance, the exact thing. And that's a super powerful feature you didn't talk about. I think it would be useful to just say a few words about that. Sure.
So the question was about provenance. And so yeah, Memento, as I kind of hinted at some of the previous slides, and it's hard to get into all of this in a 20-minute presentation, but when you call a function in Memento, what the system is actually doing is wrapping the function, and it's intercepting your call to the function. And if that function calls other functions, other Memento functions, then those are too intercepted. And so as you're making this call chain, Memento is tracking the parameters that you pass in, the functions that you call, and it's tracking all of the other information about your runtime environment, which version of Pandas, which version of Python, what operating system. All this is being collected into this Memento object, which contains the provenance. And since the Memento objects refer to each other, you get this chain all the way from your final result all the way back to the original ingestion functions that pulled in the city bike data or whatever it is that you're pulling in. So Memento sort of gives this to you as a property of the system itself. And again, it's not just about the implementation here. This is sort of an idea right? That as we're doing compute, we should be recording metadata along the way so that we're tracking provenance in some higher fidelity way than we do today with just English text. Does that address your question?
Yeah, I just wanted you to say that so you can just do a query. Can I? Yeah. I just want to. So there's a language element to this, and the collecting the hashes and stuff. In some sense, there's, if you assume, which of course is not true, but let's pretend for the moment that containers were reproducible environments that were deterministic. Well, then can this be totally language agnostic in some sense? So if you're saying, well, hey, we had this container read this data, like if you look at what Rudolph talked about, well, if he has an input and an output data, right? Well, and then there's the container, and let's imagine for a moment that it ran on always the same CPUs and that we had a hash of the container. Why do I need? Could I build into the system just what you're talking about without necessarily the language? I understand how this ties Jupyter Notebook, and I'm talking too long. But just like there's part of me that just divorcing this from the language and just thinking about this from the system, how much of this can we just do?
Yeah, it's a good question. So, like, how much do you need the language, in other words, to make this happen? Or how much do you need the implementation? Could you approach it from the bottom up instead of the top down? And I've thought a bunch about this. I think the answer is maybe, or it depends is kind of the answer. So first of all, one very big caveat that I didn't fully get into is that in order for any of this to work, you have to code in sort of a functional approach. So if you have state, or if you have some ability to have non-deterministic results, perhaps you're using a cryptographic random number seed as your function. Of course, you're not going to get the same results each time. And maybe you could pretend that you could get the hardware to reproduce thread ordering and other things. But there are going to be certain circumstances where reproducibility is just not in the cards. That's increasingly true. Like LLMs are not reproducible today, right? If you make the same query, even with a what do they call it? Not noise, but temperature. Even with a temperature of 0, in some cases, you don't always get the same results, and models can be updated and so forth. If you rely on external services, if you store state and then call the function twice, but it relies on some external state. So I don't think that you can do this without at least some support from the top down to put a little bit of guardrails in what you're doing. But I'm happy to be proven wrong. If we can figure out a way to do this, I was talking to someone before about like emulating 6502 processors, and there you've only got like 64K of RAM to deal with. And if you could just capture the whole state, every single instruction, maybe you could reproduce that. But at some point you also have to balance with being pragmatic about it and figuring out how to work. But I think it's a great research area to figure out just how do you ensure the reproducibility. One thing we're finding as we try to do this practically within 2 Sigma is that sometimes the modelers don't want that kind of reproducibility fully. They don't care about it. They care that it's close enough, and that's good enough for them. And so in fact, it's a bit of a weakness of this framework that the hashes can be too sensitive. Right? If the hashes are very sensitive, maybe I don't care that it was run on AMD. Fine, it's like 6 orders of precision off or something. For my research, I didn't really care about that. So we do offer some knobs in Memento to tune these things, but it is true that this can be a source of problem. So like if you go all the way to the system level, those knobs might be harder to tune, perhaps. I don't know. I think it's a really good question, and it's worth further investigation. I think we've got a question over there. Oh, sorry. Yeah.
You talked about cache invalidation. How does that actually work? Like, say with a root data set or an intermediate data set is updated. You find there's an error in it, or you need to do something to change something that has dependencies. I assume that then things get recomputed sort of down the chain to adjust for that.
Yeah, so and that's a little bit different from cache invalidation. So there's two things here which I want to keep separate. One is what you're talking about, which is, hey, I modified the normalizer, and therefore the joining function is going to produce different results because the joining function depends on the normalizer. So you get sort of a cascade of changes, and that's handled actually by Memento through this entish name, right? Through the name of the data set, through the kind of hash that gets generated, that's automatically handled. And actually a really neat result of this is it works really well with version control. So because it's not like a sequential version number of your data set, but it's a hash, you can actually create branches. And I've got a cool example where we have a researcher, like several researchers collaborating on the same repository, and one creates a branch, and they start making changes. Well, the changes that they make will only affect the computation from that point onward in the graph, and they can reuse everything from the upstream, from the main branch, for the earlier computation. But because there's no like sequential version numbers, that just like flows nicely. The cache invalidation that I was talking about in the final slide is really more about, well, Memento's recording the result of every single computation that you've ever made. And over time, that grows and grows and grows. And so, first of all, is it always worth it to cache? Sometimes maybe not, right? Like maybe if you have 1 + 1, like you can figure out it's 2 faster than you can read a file that says, hey, the answer was 2. So, you can hear me now through the mic. Nice. Let's hope that sound doesn't happen again. I'm going to have nightmares about that sound. So the cache invalidation, it's really more about can we actually evict some of that, that was worth storing, because we can tell that nobody's using it anymore because there's a new version and whatever. The nice property of Memento is that because these functions are pure, the cache is literally a cache. The reason that we store the ingestions as durable data is that everything past ingestion can be reproduced, right? Ingestion can't. You don't know if you pull the same data from a vendor twice if you're going to get the same results. But everything then onwards can be cached. And because it's a cache, you can actually wipe the whole thing out, and you should get exactly the same results. But in some circumstances, maybe you don't want to just record and just keep growing the cache. So you need an LRU, or you need some way to evict the cache.
Thank you.
Yep. So I don't know how we're doing time-wise. I'm happy to answer more questions as long as anyone doesn't give me the signal.
Yeah. So my question is, if you have a DAG essentially of a composition of functional transformations on your data, right? You're pretty much like 90% of the way to MapReduce, aren't you? Right. So can you pretty much apply this same idea of realizing all the intermediate results and then memoizing them essentially? Like, is that idea extensible to stuff like MapReduce?
Yeah, that's a very good question. So yeah, MapReduce is interesting. One of the things that we're trying to do is see if we can map the concepts from MapReduce, the concepts from Spark RDDs, the concepts from the sort of distributed computing technologies that are in very common use today, and see how they would be implemented in this pattern. In many cases, it's fairly straightforward, and in other cases, it requires some thought to figure out how to do it. The main disconnect is that, especially in things like RDDs for Spark, those are stateful. They're sort of like you have a data store that's going to be manipulated in place effectively, and because you're recording state, you don't know that the second time you invoke a function, you're going to get the same result. So as long as you can structure it in a way that each stage is functional, meaning that it doesn't have side effect, it's side effect free and the functions are pure, then it will work. But as soon as you introduce state to it, that violates one of the principles here, which is really that everything is immutable, right? And everything is purely functional. So it requires a little bit of thought, but we've started looking at that, and I think the answer is that we can get to the same results as MapReduce, but it requires a little bit of attention. Does that answer your question?
Yeah.
Right.
And if we have time, a small follow-up to that is, right, if you have purely functional, like stuff like the Haskell compiler would happily do, more exotic transformations that map, that merge multiple functions together so you don't realize every single intermediate result, right? It's like, because you have to realize every single intermediate result in order to do the memoization. Like, is that a trade-off that you find commonly worth it, to realize all of your intermediates, or is the trade-off, sometimes not there?
So first of all, Haskell would be a great language for this, actually better than Python, because Python is not functional and you can really get yourself into trouble with Python. But yes, if you're using that kind of, as long as you're using that style of programming, this works quite nicely, and all the intermediate results actually collect quite neatly into mementos, and you can get the provenance and everything else. So there is, in the current implementation, there is this idea of a function returning a partition, which is kind of interesting, and it lets you implement a lot of these MapReduce style patterns. And happy to connect later. I want to be, I want to pay attention to the time here. But great, excellent question. Thank you. All right, thank you very much.
How does that work? Which button does it? Right. Thank you. See there. Check. Is it? Check. Okay. Well, this talk is going to be, I think, in the nature short, hopefully, in the nature of a status report on D4N, which I think. Probably most people in this room are familiar with, because it's a research collaboration led really by the research professors of Mass Open Cloud, so Ron Krieger and Peter Disneyer, and their students. My name is Matt Benjamin. I'm one of the collaborators from industry. I originally, for the last, from 2015 to 2022, I worked for Red Hat as the engineering manager for Ceph object storage, which on which D4N is based, and I'm speaking with Amin Masebzadeh, I've been working with him since 2019 on D4N, and we're going to try to focus on things we've done in the last couple of iterations of that, and also Amin's new work. Just briefly, D4N is a cache, an intermediate cache, materialized intermediate cache for S3 object data primarily, and its purpose is largely to accelerate computation in large data lakes, and it's gone through a number of different dimensions. The original D3N is a more static topology for such a cache. D4N added a distributed directory, allowing us to do more sophisticated things, and it's kind of the foundation for everything we're going to be talking about here. My part is going to be about D4N upstreaming, and it means it's going to be about the locality piece. So I've kind of said everything I want to say here. As a storage engineer working on Ceph, the Mass Open Cloud collaboration has offered an opportunity to incorporate data center scale workload intelligence directly into the object storage layer, and that was what excited me about this project. It remains exciting to different strands of development and deployment within my two organizations. Ceph had been widely, and Ceph object storage has been widely used as a databasis for a variety of kinds of computation, from Hadoop then into Spark, and sort of on into other data lake functions, Presto and Trino now. So technology like D4N enables a bunch of different kinds of workload intelligence to be added into the storage directly, as opposed to bolting on another kind of cache, and a lot of our interest is in incorporating that. And so some of what we've done here in the past, S3A, is describe some of those workload integrations. S3 select is a sort of primitive form of S3-enabled predicate pushdown. So you can inject queries into the S3 storage service and then return consolidated results. And this one's by Amazon, and some of our work extends that. And so among those things, we have an Aeroflight interface to the SEP object storage, and we also have flight SQL experiments going on. And specifically the things my team is working on this last, I don't know, 12 or 13 months, is incorporating all of the D4N research work over the last, I don't know, 4 years into the open source Ceph project. That's involved the work of something like 7 different members of my team, plus work by all of the folks that work with Mass Open Cloud. So I'll skip past some of this stuff, but that's some of the stuff that's in there. In order to basically take all the research work that was done by Mass Open Cloud researchers and put it into an open source Ceph project, we really had to sort of rewrite a large chunk of the object store. We did that, and we now have a sort of a pluggable architecture for incorporating different layers of functionality. Cache is a kind of a redirector layer, and there's now flexible backend, so we can put data in different locations and stuff like that. Okay, and that's kind of a picture of some of what that is. Okay, so I'm going to kind of skip past this, but this is detail on how we've actually gone about that. Most of it's stuff that's already in the research D4N, but we're incorporating it in a new way. As I say, it's mostly about internal software interfaces. D4N started off as a read cache, or D3N did. D4N as a write-back cache has a lot more sophisticated capabilities around that, and we're incorporating that in the new work. Okay, I'll turn it over to you, Amin, for the next part.
Okay. So Matt, thank you. So Matt discussed about the engineering side of our collaboration. I am going to discuss about the research side of a collaboration. So in our initial design, we had a write tier expanded to several racks, and we exploited Ceph's internal structure to replicate data. The problem was that we didn't know where is the data. So we changed the design to have a read and write cache on top of each rack. And we use RGW's internal logic to replicate data. What does it mean is that read after write requests always will be served locally. And this is important for machine learning applications because they have a significant amount of intermediate results. Now that we have the locality, we want to expand this cache across data center. Why? Because as Larry explained it, the vision is sharing. And we want to provide a community cache that provides sharing. So an example here is training data sets for machine learning training models. The training data set usually is the same, while training models are different. So sharing is important here. We have several options to develop this idea. From starting S3 protocol, which provides a standard interface, to NVMe over TCP, to RDMA, which probably will need hardware support, but will provide better performance. Now that we have extended our cache across data center, we want to make sure that each application is able to access its data from nearest RGW. Previously, we did this by controlling switches, but now we want to use Kubernetes topology-aware routing to do that. Here, each pod in Kubernetes cluster that can be extended to several racks should be able to get its data from its local RGW. A D4N, a community cache across data center, can decrease inter-rack network traffic, increase performance, decrease runtime. So it has different use cases. One of these use cases is analytical framework, which Matt will discuss in the next slides. Another use case is machine learnings that, as I said, have a lot of read after write requests, which are perfect for caching. Another use case is to caching snapshots of progress stages of machine learning, which helps us to reduce the restarting time in case of a failure.
Okay, so yeah, I've covered a couple of things, but I have a group of, I sort of have two groups of engineers in my team. One is working on the upstreaming of D4N itself, and well, there's more groups, but the other one that's working on convergent activity is my BDAS team, Big Data Analytics Support, and we're working on things like workload integration for Spark and for Presto and some other technologies based on that. The goal of some of this work is to improve on the efficiency of S3 Select, and both in terms of the query capabilities and also in terms of the data set translation or transport model. S3 Select is pretty efficient about that. Arrow is a natural format for doing that, and has very good bindings to network transports. So that's some of that. Arrow and Arrowflight are natural, as it states, a natural format for returning and for doing computation in core and in different computational locations, but also transferring it over, back and forth between compute nodes or back to clients. And there's all kinds of work going on to sort of incorporate new capabilities there. Flight SQL is one that's got a bunch of personalities and putting different kinds of parameterized queries into data requests and getting back Arrow. There's some summary of what things people did and might be doing. A summary of the research that was already done on D3N and D4N, and some of what we've already covered. A summary of some of the people who worked on all of this. Some people started back as early as I think 2017 or 2018. Or Kenar and Mania Abdi, both the dissertations that focus on different aspects of D3N and D4N, and in particular, both worked on workload integration for Hadoop, I think for Pig and for Spark and similar frameworks. These are some of the members of my team that worked on this project just this year. And take questions.
So first I want to say this is a super cool example of what we've been able to do of having graduate students work on research, but actually working with a team that then can actually integrate it so the thing you're doing has an impact. And one of the other things that we've decided to do on our side here is, this was motivated by real problems we had of the performance of the shared storage. And we have high capacity drives, we have NESI, it's on the other side of a network with limited bandwidth. We're now have a concrete plan where we're going to have on every rack in the MOC NVMe storage, and with this approach that we talked about of using the topology-aware routing from Kubernetes, all requests will always go to the rack local instance. And this is going to be an experimental service. And one thing I'm really curious about for the community here, we think this will give much higher performance, or we strongly believe that. We have the NESI storage, but we also have a couple of petabytes of research storage that we're putting into this, as well as these rack local things. How many people would be willing to use an experimental service that, you'd have to explicitly copy your data back to the reliable production service? This is something we'd like to start doing, is offering new features that are high risk, but hopefully higher performance. But you as a researcher would have to manage your data and copy it back to something that's actually guaranteed reliable. Well, that's exciting. Hopefully we'll get more reception once we actually do it. What's that? Who wouldn't do it? Much better response. Okay.
Chapter 5.
Yeah. I mean, this is one of the things I'd like, so it's going to be a long period of time until it's fully upstreamed, until it's released back in product, until we can incorporate it as a supported feature, in the production cloud services. And one of the things we're trying to figure out is how to speed up that loop to at least offer things as experimental features to get things into people's hands faster, but also to get experience then for the teams that are doing the upstreaming and the production work of real usage of what they're doing.
Hi, can you guys hear me? And is the echo worse or better if I use this microphone? Okay. I'm the Director of Product Development for the Mass Open Cloud Alliance. Ron spoke this morning about the MOC Alliance playing a role of coordination between all the different groups. And if you use this one instead of this one? Oh. Okay. This one or this one? Can you guys hear me now? But the echo's worse. Oran spoke this morning about a coordination role that we play. About a coordination role that we play. And what you see up there is sort of a chart where all the different groups that are providing engineering resources comes from. And I'm going to move to my notes here because I didn't realize I was going to need two hands. The Red Hat and MOC engineering teams are now on the same sprint cadence. And we work together and we plan together and we collaborate to ensure that we're delivering high quality results. We plan our sprints together, we hold regular check-ins together to stay on track and to make any necessary adjustments. The operations team of necessity is working on a slightly different cadence, but we constantly collaborate with them. We have weekly meetings with them. We're frequently reviewing each other's code. When I say we, I should say those folks are frequently reviewing each other's code. And I promise this will be quick because it's late in the day and I don't want to threaten the gods and get that jet engine noise again. But I would like to ask that the engineers who are up there and in the room, if they could quickly stand up just so that everybody can see them. And so the one other thing I want to say is this was pulled together very late in the process. So if I forgot anybody, I deeply apologize. There are so many people, as you saw earlier in Oran's talk, as it rolled through all the names of the people who we've been working with and depending on to actually make this thing a reality. Last but not least, not one more thing, but two more things. The Open Cloud Testbed Advisory Board is currently meeting up in 3:15. Probably if you're on that board, you're already there. But just in case, I wanted to make sure I mentioned that. And also, please join us on the 17th floor in the Center for Computing and Data Sciences, otherwise lovingly known as the Jenga Building, which is just up the street. It's at 665 Commonwealth Avenue. It's on the same side as the GSU. So when you go out of the GSU, walk towards Boston. Thank you, and we'll see you all in the morning or tonight.